Andrew. Bye.
Hey. Okay. Hello, everyone. Good morning. Welcome back to day 2 of SBC 2019. I'm Taj Draja. I'm the session chair for the first session, which is payment channels and locks. So just some overhead stuff. Like, if you want to do questions, try to come down this center aisle, and I'll give you the microphone after. And try not to yell it from the back. And if you do, I'll try to repeat it because yesterday. Okay, cool. So without further ado, the first talk this morning is Pedro Moreno Sanchez, privacy-preserving multi-hop locks for blockchain scalability and interoperability.
Okay. Thank you for the introduction, and thank you everybody for coming to my talk. As you said, my name is Pedro Moreno Sanchez, and I'm going to talk today about privacy-preserving multi-hops for blockchain scalability and interoperability. And this is a joint work with my colleagues Giulio Malavolta, Clara Schneiderwind, Aniket Kate, who is in the audience, and Matteo Maffei. Probably it's not a surprise if I tell you that permissionless blockchains have a scalability issue. And it's that the permissionless nature of the current blockchains actually limit the transaction rate that we have. It's really low. We have at best 10 transactions per second. And this actually limits a more widespread use or adoption of blockchain technologies like Bitcoin or Ethereum. This scalability problem has been tackled in the community, in the research and industry, and we can roughly group the solutions into groups. One is the on-chain or layer 1 solutions. Yesterday we saw fantastic talks about advances in this area. And the other group is off-chain or layer 2 solutions, which is going to be the focus of my talk today. The technique that is most widely deployed today for layer 2 solution is called payment channels. Probably most of you know already how it works, but just to make sure that we are all on the same page. I imagine a setting in which we have two typical two users, Alice and Bob. Bob has some books, and Alice wants to buy them with some Bitcoins. One thing that Alice can do always is pay for each book with an on-chain transaction. But this will add more load to the blockchain, to the Bitcoin blockchain. She will have to wait for more time for every transaction. So instead, she can use a payment channel. For that, the first thing that she has to do is create what is called a deposit transaction. So she takes some of her Bitcoins, 5, let's say, and puts it in a multi-sig, in a deposit account, which is shared by Alice and Bob. And just to make sure that she can recover the coins in case that Bob goes off-chain or goes crashed, after some time, Alice alone can get this money back, can get the refund back. Once this channel is open, she can now perform off-chain as many payments as she wants. For example, she can just create a transaction that tells Bob, look, out of the 5 deposit coins, I take 4 back to me and I give you 1, and I sign such transaction. So Bob is happy because the only thing that he has to do now is sign on his own, and that he can always do. So he accepts that as a payment, but it's off-chain, it's not in the blockchain yet. And now Alice can repeat this process again and again to buy as many books as she wants. And at the end, Bob will actually want to have his money back, his coins back. What he does is what is called a closed channel transaction. So he signs the last state, puts it on-chain, which means that Bob recovers 2 coins out of the deposit, and the remaining 3 goes back to Alice. This technique is nice, but actually works only for 2 users, so it's only between Alice and Bob. What would be even nicer if we could have a system in which everybody could pay to everybody, which is called a payment channel network. And the first solution that one can think of is let's try to create channels between every 2 users in the network to create a clique of payment channels. However, this has several limitations in practice. And the main one is that we need to lock coins in each of the channels. So people might not have enough coins to lock coins for each of the channels that he has to create. So instead, what we can do is that users can open a few channels with their friends or with their main shops or wherever they want to, and rely on the fact that there might be other channels open that connect them to the intended receiver. In a bit graphical example, imagine that Alice wants to pay to the cat. However, Alice does not have a direct channel with the cat itself. But Alice might be the case that has a channel with Bob, and Bob has a channel with the cat. So what she can do then is pay off-chain 1 coin to the Bob, and then Bob will relay that this coin to the cat itself, what is called a multi-hop payment. And this basic idea is the core idea of what we call payment channel networks, and this has been deployed already in practice in some of the cryptocurrencies today. So we have examples in Bitcoin and some altcoins in the form of the Lightning Network, Sea Lightning, and Eclair. In Ethereum, we have the example of the Lightning Network itself. Zcash is starting to create a network called Vault. And I believe that eventually every blockchain will need a layer 2 solution, a layer 2 scalability solution. So in this panorama, in this current situation, in our work, and also the purpose of this talk, is mainly three points. So first, we actually formally describe which are the security and privacy notions that we need in such a network. We then go to the actual implementation of the payment channel network and show which are the security and privacy problems that they have today. And then we provide novel cryptographic constructions that solve this problem and have formal proofs for security and privacy. So let's start first with security. So if I ask here around, most likely we all agree that we need security in such a payment channel network. Probably we don't agree in which is the actual meaning of security that we need. So in our work, we define security in the notion of balanced security. And intuitively, we say that we require that honest users do not lose coins in a multi-hop payment, in an off-chain payment. Graphically, what we mean is that imagine that there is a path of multiple users from Alice to cat, to the receiver, and the intermediary node has a certain balance, which is denoted by this delta, which means the number of coins that he has in the payment channel network. What the payment channel network should ensure, if it has security, is that after a payment goes routed through Bob will not have less coins than before. Or in terms of probability, the probability that this bad case happens should be negligible, should be really, really, really small, really rare case. So once we have agreed in the notion of security, let's see how it's implemented today. So basically, they use a tool, a contract called hashtime lock contract. And the basic idea is that Alice is going to pay to Bob, but not directly, but under the condition that Bob is able to reveal the preimage of a hash function. And this in cryptography is known to be a hard problem. If you don't know the preimage, you cannot come up with it on your own. So graphically, now Alice will not pay directly from the deposit to Bob, but will also attach a script that says, Bob, you have to come up with some value such that when you do the hash of that value, this has to be equal to y. And Bob has to come up with it. And how we do multi-hop out of it is we chain several of these has-time lock contracts from the sender to the receiver. This is the core of the Lightning Network. I put here as an example, but also the core of other payment channel networks that we have today. So example, imagine that we have an example path from Alice to Kat that they want to pay through the intermediary Bob. Okay? So the payment goes in three steps. First one is called setup, the second one is lock, and the third is release. In the setup, Kat thinks on her head two values, x and y. And she says that h of x, or the hash of x, is equal to y, and gives the value y to Alice. This is how the payment is actually set up. And now they go into the lock phase. So what Alice does is creates a has-time lock contract, one of these conditional payments, to Bob. And Bob forwards this payment under the same condition y. Here, you should notice two things. First is that if Alice wants to pay to the Kat 1 coin, she actually pays 1.1 to Bob. And this is in the concept of routing fee. So it's a fee that is charged by the intermediaries by providing the service of routing payments between two nodes in the network. The other important aspect is that these time locks have a timing to make sure that you can recover the payments if the payment is not successful. And this payment has to be correlated such that the payment in the channel before you should be higher than the time in the payment channel after you. This is to make sure that Bob knows whether Kat has money or not before he has to solve the payment channel from Alice. So if the Kat has money from Bob, he should have enough time to go back to Alice and say, look, this is the condition, give me your money. When the payment is locked, the release part is pretty simple. So Kat knows the preimage of the hash because she created it, gives it to Bob. Then Bob forwards this preimage to Alice to get the money back. So principle, this has been implemented. People starting to use it, seems to be fine. However, we took a closer look to how the system works, and we found what we call a Wormhole attack. And the idea is pretty simple. The idea is that the intermediate, so we want to exclude the intermediate honest users, Bob in the previous example, from the successful payment operation, from finishing the successful payment. And the idea is that if adversary manages to do that, he's able to steal the routing fees from the honest user. Let's see that through an example. So imagine that we have a longer path now, Alice and Kat, and the payment is routed through the adversary and Bob. And imagine that we are ready after the lock phase. So every payment channel in the path has been actually locked already. Now in the release phase, the Kat reveals the condition to the adversary. Now the adversary, instead of forwarding it to Bob, he decides to tell Bob, look, the payment failed. I'm not going to ask you money. So for Bob, it's OK. So he doesn't pay to the adversary. He doesn't get the money from the adversary in the left. So for him, the balance is the same. But now, because the adversary knows that the same condition has been used in the whole path, now the adversary in the left can use the same opening condition to continue the payment in the rest of the path. So the adversary can use the same X to claim money from Alice. And if you think a little about it, the adversary doing this actually get coins. So the adversary gets 1.3 coins from Alice, and he has to pay only 1 coin to the Kat. Means that at the end he got 0.3. In practice means that he got 0.2 for his routing fees, which is okay because he actually routed the payment. But he also got the fee from Bob. And the main issue why this attack is possible in the current payment channel networks is that the same condition is used along the whole path. So if I'm sitting at two nodes in the path, I know I can use the same condition to release my channels. And as you can imagine, here I used only one intermediary, only one Bob. But if there are many intermediaries between the two adversaries, the benefit for the adversary is higher. So the more intermediaries, the more benefit. And this is an important attack because the fees are the main monetary incentive for the intermediate users to route payments in the payment channel networks. So if now with this attack, we get rid of this monetary incentive, so we get rid of the main purpose for them to actually use the system. And the other important point is that for Bob, it really looks like no payment was done. So it looks like the receiver was crashed. He never revealed the release information, so he believes that the payment was not successful. So he cannot pinpoint the adversary as somebody that did something wrong. He doesn't have a proof for that. This is about security. What about privacy then? Again, probably privacy is a big term. We need to first agree on what is the notion of privacy. Here, we define it in terms of relationship anonymity. And intuitively, again, means that the adversary should not be able to tell who is paying to whom in a multi-hop payment. In a more graphical definition, imagine that we have such a setting in which there are 2 senders and 2 receivers. And for the sake of the example, imagine that the blue Alice is paying to the blue cat and the green Alice is paying to the green cat. When these 2 payments happened, the adversaries will not be able to tell whether the blue Alice actually paid to the blue cat or to tell whether the blue Alice paid to the green cat. Or in terms of probability, the probability that the adversary is correct in his guessing should be really, really, really close to the probability that the adversary is wrong in his guess, which actually means that the only thing that he can do when he is part of such a payment, he's part of the path, the only thing that he can do is guess. He doesn't get more information from the payment itself. That's the privacy notion that we use. Once we have agreed on what privacy means, let's look again how privacy is implemented or how privacy is implemented in the current payment channel networks. Again, imagine that we have the setting as before, and imagine that we have a payment where the Alice on the top has paid to the cat on the top and has been routed through the adversary Bob and adversary. For the adversary at this point, it's really easy to see that he got a payment from some Alice with the condition Y, and at other point in the path, he forwarded this payment to a cat using the same condition Y. So for now it's really simple to determine that the blue Alice paid to the blue cat. The probability is 1, so he always is correct if he does this guess. And again, the problem is that the same condition Y is used along the whole path. Apart from security and privacy, we also looked at other practical considerations with the current networks. The way that the conditional payments work has some scalability issues, in the sense that we need 2 keys to define the deposit. And the payment condition now requires to attach a script to the output of Bob, which requires some extra bytes in the transaction and eventually in the blockchain when we close the channel. This also has privacy issues. So when we see such a transaction, we see the 2 keys that share the deposit, and we see the 2 users that are sharing the payment channel. So we can determine that these 2 users are doing business together. Finally, this has problem with interoperability in the sense that only payment channel networks that support the hash function that is used in this mechanism can be compatible with the current payment channel networks. If you want to use them, you have to use the hash functions that they are using in their system. So in summary for this part, payment channel networks are a great technology that has definitely improved upon the scalability issue in the current blockchains. However, there is still a long way to go. In security, we have seen the Wormhole attack. Privacy, we see that it's possible to determine who pays to whom. And in terms of practical aspect, we still can do better than using a unique hash function and have extra bytes in the transaction that might not be needed. So in the second part of the talk, let me try to tell you how we can try to fix some of these issues. And here we looked at the transactions, and we saw that in many of the cryptocurrencies, if not all, the digital signatures are used to authorize transactions, and they are there already. So we thought, can we use digital signatures for something more than authorizing signatures, authorizing transactions themselves? What we can do with them? And there is a paper by Lindell in 2017 in which he defined what is called a 2-party ECDSA signing protocol. And the idea is that we have a setting in which there are 2 users, Alice and Bob, and they have their own private key pairs. The idea is it's possible for them to jointly compute a signature on a message, let's say a transaction, a Bitcoin transaction. And they do it in such a manner that this requires the knowledge of both, the secret key from Alice and the secret key of Bob. This makes sure that both of them have to participate in the protocol. And the other interesting aspect is that in order to verify such a signature, we require only one public key, which is the joint public key or the combined public key of both of them, PKA and PKB. So if we transport this directly to how the opening of a channel will now be defined, we go from a setting in which deposit requires 2 keys to a setting in which we have the deposit defined by a single key, PKAB. And with that, we save some valuable bytes that we no longer have to put in the blockchain. Similar, if you remember, for the off-chain payment. So in every off-chain payment, we have to define the deposit, which has 2 keys. Now we can use it with a single key. So again, we save some bytes for the blockchain. This is good so far, so we can do a bit better. However, if you remember, for the multi-hop payment, we also need the conditional payment. We need to embed a condition itself. So what if we can encode the condition itself in a public key, in the signature itself? So how we can do that? For that, there is a technique called Scriptless scripts. It's a technique that was originally proposed by Andrew Poelstra. And the idea, as I said, is it's possible to encode a cryptographic condition in the public key itself, in the creation of a digital signature. But the technique that he proposed requires to have a Schnorr as a digital signature in the cryptocurrency. And they have done excellent work on how to expand this to more functionality. Fortunately, we don't have it yet in Bitcoin. What we have in Bitcoin is ECDSA. So what we will require is a similar technique in which we can encode conditions inside ECDSA signatures itself. So in our work, we first formally define the technique for Poelstra and show that it actually achieves security and privacy properties. And we then propose the scriptless scripts version of ECDSA. And what I wanted to point out is that this is not an easy task. It has been an open question in the community for a while. And the main challenge to make this work is that in Schnorr, the signature has a kind of nice structure. So it's like the randomness plus the secret key times the message. So if you have 2 of these signatures, it's kind of easy to combine them. So you can do a linear combination of them, and it works. The problem is like in ECDSA, the structure of the signature is a bit more complex. It requires the inverse of numbers. It requires the x coordinate of a point. And when you combine 2 signatures, this is not any longer a nice linear combination. So you need, as I said, like the inverse, the x coordinate of a point. The secret keys are shared in a multiplicative form, which in practice, if you don't know what it is, but in practice means that we require interaction between the users, and it's a bit more complicated protocol. So if you're interested in the details, we have the full protocol sketch actually defined on the paper, and there is the formal description and analysis. I don't have time to tell you the details, but I'm going to give you a brief idea or brief overview of how it works. So again, basically what we want is to have 2 users, Alice and Bob, in which they want to perform a payment, under the condition that Bob comes up with the secret key associated to the public key of C, public key of the condition. And we want to achieve 2 goals. So Alice can create a half signature that can give to Bob, such that Bob can finish only when he solves the problem, when he comes up with the secret key C. And the other thing that we need is that if Bob actually managed to do that, if Bob managed to finalize the payment and solve the condition, Alice should be able to look at this signature and extract the secret key of C, secret key of the condition itself. Let me give you a little more, let's deep a little more on the details and the protocol overview. So the first thing that they do is create what I called before the joint public key, the combination of the public key A and public key B, and create a combination of the randomness, which combines randomness from Alice, randomness from Bob, and the condition itself. And this intuitively means that, or this intuitively ensures that Alice must use her secret key, Bob must use his secret key itself, but also they must use the secret key that's associated to the condition, secret key C in this case. Once they have that, Bob gives his 1/3 of the signature to Alice, Alice gives her 1/3 of the signature to Bob. And eventually, when Bob learns the secret key of C, he can put the 3/3 together and create the whole signature for the transaction. Now, if Bob wants to close the channel, he might put this signature in the blockchain, or if he collaborates with Alice, he might just send the signature to Alice itself. And now Alice, when she sees the whole signature, she can take out the 2/3 that she knows and get the sigma C, the third corresponding to the condition. And from that, it's really trivial for Alice to extract the secret key C itself. So if you look at it a bit more in detail, you can think of it as the first messages had been a lock mechanism, as we have seen before. So they extract enough information such that the state between them is enough up to the point in which Bob requires some release information, some extra information. And once he learns the extra information, the SKC, then we enter in the release part of the protocol. So he can release the payment by creating the whole signature. So basically, the first part is we can use it as a lock in a multi-hop lock, and the second part we can use it in the release phase. In fact, we define how to use this building block, ECDSA, to create a payment channel network. And we use, again, the three same phases, the setup, the lock, and the release. The setup, Alice will, in her head, compute two keys, the public key D and public key, which will be part of two conditions, and also a combined public key from them. So she combines both of them. And now Alice gives to Bob the combined public key plus the public key D plus the secret key for the other one, for the third one. And in the next phase, you will see why this makes sense. And for the receiver, she just gives a condition, which is public key D, and the opening of that condition, the secret key associated to that public key. Because CAD is the receiver, so what she wants is she actually managed to open and start the payment if everything is successful. Once they have this set up, they go into the lock phase. If you remember, for Bob, it's OK to lock the incoming payment channel in the combined public key, and the outgoing one in the public key D. Because he knows that as soon as the cat reveals the secret key D, he can combine that with the secret key E that he knows, and this combination is already the opening information for the combination of P key D E, for the public key D and public key E. So he knows that if the cat starts the payment, he could always take this information, combine it with his secret E, and be able to release the previous payment channel. The interesting point here is that this public key DE and D are randomized, so the public key D is a random key, and public key DE is the combination of two random keys, so they are randomized conditions. And intuitively, this is what gives us the security and privacy notions that we need. The release part of the protocol is pretty simple. So the cat reveals the secret key D to Bob. Bob computes secret key D plus E and give it to Alice, as simple as in the Lightning Network. And here there are some points I wanted to discuss. So I show it only with one intermediate user for simplicity, but as you can imagine, we can extend this to many of these hops. So every hop will have a combination of n-1 keys. It solves actually the security problem that I showed. It solves the Wormhole attack and also the privacy issues that I showed here, and improve the interoperability of the system. So now the cryptocurrencies that want to use this payment channel network only require ECDSA. And we also show in the paper that it's possible to combine ECDSA payment channels with Schnorr payment channels. So you can have a multi-hop path, which one channel is ECDSA, the next one is Schnorr, and still you can do a multi-hop payment. Obviously, because it's based on ECDSA, it's compatible with Bitcoin and the current payment channel networks. And people from the Lightning Labs, Connor Frognetz, has implemented this scheme in the current Lightning Network, and they're testing it. If you're interested in this link, they have more details. So in summary, we have improved the state of the art in the payment channel network in the sense that now we have security. There is only one secret per user. We improve into the privacy, the notion of relationship anonymity. And we improve also interoperability and the transaction size. We reduce the transaction size. So we need only one public key that encodes both sender, the receiver, and the condition itself. So in the last 1 minute and a half, let me show you that we are working now on what we call atomic payments. So one problem that I have hidden purposely during my whole talk is the problem with the timing itself. So I said before, the timing from the channel on the left of Bob has to be bigger than the timer in the payment channel of the right of Bob. But if you think about it, if the payment is not successful, the time that the coins are locked in the payment channel between Alice and Bob is the time prime, the time in the right, plus the time on the left. So it's a long time. And if you think of a bigger path, or a path with more hops, the time that you need to lock the coins is actually grows linearly with the number of hops that you have in the path. So what we instead would like to have is an atomic payment in which every channel locks the coins to a same constant time. So it doesn't matter how long is the path, you have to lock your coins a shorter time, or the same time as any other channel in the path. But for that, we require payment mechanisms that make sure that all the channels are as successful or updated, or none of them are updated, which is called atomicity. And the advantage of this is that if the payment is not successful, it will be faster to recover the coins. We have to wait a shorter time to make the payment expired and get the coin back to use it for a further payment in the future. So to conclude, the take-home message from this talk would be that, yes, the current payment channel networks is a great scalability technology, but it requires further work. In this work, in this talk, you have seen that we have created the first formal security and privacy analysis for an attacks on the current payment channel networks. We propose some cryptographic protocols to improve half of them. In particular, we do the Scriptless ECDSA-based locks to improve in security, privacy, and interoperability of payment channel networks. With that, I would like to finish. Thank you for your attention, and looking forward to your questions. Thank you very much.
You have time for like 1 or 2 questions?
So in the wormhole attack, you say that the intermediaries who are surrounding some other payment intermediary are stealing fees from them. But aren't they really just routing around that intermediary? So like, why are they entitled to fees? They're really just getting disintermediated there, right?
Yes, so they could routing around if they create a payment channel between them, but this will require to lock some more coins to create such a channel.
If they trust each other, they don't have to create a payment channel. Why can't they just, like actually make the right payment between them?
They could, but then, you make the honest, the point is like you make the honest user to participate, you harm his liquidity because you put some coins locked there, and because of this service, he should actually get money, and he doesn't get because you get routed out of it, or you get the guy out of the path. If you want, obviously you can route around, yes, it's not, because the condition is the same. With our technique, you cannot do it anymore, because if the honest user is part of the path, you require his secret part to finish it, actually. Yes.
Any other questions? Can you come up? Do like 2. Okay.
Hi, thank you for your talk. I'm not sure if you mentioned it, but what are the limitations on applying the sprites technique to unlock all the HTLCs in one round in this work?
Yes, so sprites, for those of you who don't know, is like a way to create what they call atomic payments in Ethereum, or in a system in which you have a more expressive language itself. In order to do that, you will have to have enough expressiveness in the language of Bitcoin to support what sprites require. If that's the case, you could actually use it. What we are trying to do it here is do the same functionality. You have atomic payments with as much reduced language as possible. So have the minimal operations that we need and still achieve this property. That's what we are trying to do. Yes.
Hi. For SS-ECDSA, have you considered using BLS?
Yes, so we showed actually in the paper that any one-way homomorphic function actually would suffice to have the properties that we want. And you can definitely do it with BLS as well. We used to do it in ECDSA because it's compatible with the current Bitcoin blockchain. Yes.
Okay, great. I'll thank Pedro again, and next speaker. Thanks. Okay, so I'll introduce our next speaker, Daniel Robinson from Paradigm, with the talk, HTLC is considered harmful. I'm just fighting words. Okay.
Hi, everyone. So I'm here to talk about a design pattern that I don't like. It's something that you see a lot in a lot of designs. That was the previous talk. We had a great description of them. Talk a little more about how they work before I talk about why they don't work. You see them in a lot of protocols for cross-chain atomic exchanges. You see them in protocols for payment channel networks like Lightning. But they have these downsides, some of which I think are familiar and some of which aren't that familiar. So when I started working with HTLCs about a year ago, I had a lot of headaches until I was convinced by Evan Schwartz and Interledger that they're a bad idea and that they'd actually developed a better way to do it. So I'm not affiliated with Interledger. This isn't an Interledger talk. We're not going to cover most of the Interledger protocol or things, including things I like about it. This is about one specific design decision that they make that replaces HTLCs, and that I think is really cool, and that I've considered it for the past year my mission to elevate the people's familiarity with this. So what is the problem that HTLCs solve? A lot of people talk about it solving the problem of atomicity, but really atomicity is the means to an end. What HTLCs actually solve is the problem of fair exchange. So if you've seen Raiders of the Lost Ark, this is a scene where Indy is trying to get across a pit, and his guide tells him, if you throw me the idol, the thing that they've rescued from here, I'll throw you the whip so you can get across. And obviously, Indy doesn't really have a choice there, but he has no way to guarantee that when he throws over the idol that his assistant will throw over the whip to him, and of course he doesn't. So that doesn't work out so well for the assistant in the movie, but in a payment channel network, often if you would be able to steal money from somebody by having them make a payment to you, and you don't make a corresponding payment either back to them or to someone, or to another currency or to someone else. So this is the problem that we're trying to solve. Now, if we're all on the same ledger, it's actually very trivial to solve this. And back when I used to be a traveling blockchain salesman, this is what I would always tell people is a huge benefit of blockchains, is that, look, you can have all your assets on the same ledger, and then here we can do just a DAI to ETH trade where it's all in one transaction, and you know that it won't, part of it won't complete unless the other part completes. But it turns out that's not even realistic, even in the blockchain world. In fact, in blockchains, we have a lot of ledgers that are completely unrelated to each other, and you have assets that are only on one ledger and not on another. And so trying to actually do atomic transactions across these different ledgers is a problem. So in order to illustrate exactly how that works, I'm going to, just in keeping with the destiny of that currency, use Litecoin as the example and talk about a cross-chain atomic swap between Bitcoin and Litecoin. So here we have, let's just suppose we're doing an on-chain payment from Alice to Bob in Bitcoin that's being traded for Bob's Litecoin. So Alice could go first and make a payment of one Bitcoin to Bob, but then obviously Bob could cheat Alice by not making the payment. Bob could go first, but then Alice could cheat Bob by not making the Bitcoin payment. So we need a protocol to make sure that both of these, this value is exchanged fairly. So what people came up with originally for cross-chain atomic swaps, and this ends up being used for other kinds of atomicity, is HTLCs. So HTLCs stands, I think, for hash time lock contracts. People use it differently in many different ways, and honestly, I'm here to bury them, not to explain them. So I'm fine with whatever that. We're just going to call it HTLCs. It's like the SET. It doesn't stand for anything anymore. HTLCs are a means for providing cross-ledger atomic transactions where either of these transactions both complete or neither do. And note that I'm not saying cross-chain atomic transactions, I'm saying cross-ledger, because these ledgers can be payment channels, they could be different kinds of ledger, but what matters is it's providing atomicity across these multiple things. So this is a smart contract language we developed at Chain called Ivy, and this is just an illustration of what an HTLC does. And I like James Presswitz's explanation of how HTLCs work, which is there's two ways that they can be completed. Either the recipient of the HTLC, one of the parties, can complete the HTLC and receive the payment by revealing a secret, or the sender can cancel it after a timeout. And this is like an example of one HTLC, so there's going to be one of these on each chain, and they're used as part of a two-phase commit protocol for these two transactions to happen atomically. So the way this works, and a lot of you I'm sure have seen this before, first someone creates an HTLC on the Bitcoin. Alice creates an HTLC on the Bitcoin network that's going to Bob, but Bob will need to reveal Alice's secret to retrieve it. Bob sees that, and then he's able to lock up 100 LTC on the Litecoin network, completely unrelated network, with the same hash, but a shorter timeout, a 24-hour timeout. Alice now has 24 hours to reveal her secret to complete that HTLC, and then Bob now knows the secret that he can use to retrieve the Bitcoin that Alice put in the HTLC on the Bitcoin network. So this is the happy case. This is what happens when Alice actually does reveal the secret, but what happens if Alice doesn't reveal the secret? Bob has to wait 24 hours and then can retrieve the money from the HTLC, and then Alice gets her money back after 48 hours. So these timeouts can be a little different. I'm using the default Lightning HTLC timeout of 24 hours, but you really can't go that short. It's not 24 hours, it's like 144 blocks, but yeah, you can't go that short on it because someone needs time to actually see something on one chain or from one payment channel closing or anything like that, and to have time to actually go close it on the other and be able to get it included in a block. So there's really sort of a limit on how short you can make these timeouts, and that's important. So how do we, how else can this be used? So right here we used it to do a cross-chain atomic swap, but if you just change a little bit about this thought experiment, you can, by changing the ultimate recipient from Alice, who's also the ultimate sender, to Charlie, this now becomes a cross-chain atomic payment where Alice is paying Charlie, but Alice is sending Bitcoin and Charlie's receiving Litecoin. So the example I like to use for this is kind of like a decentralized or trustless shapeshift, where there's the payment currency doesn't have to be the same as the receipt currency. And these don't have to be on chains. These can be, HTLCs can be embedded within payment channels. And the mechanism for this isn't a talk about payment channels, but the mechanism for this, somewhat complicated, but you can have, do these ledgers, these ledger updates where the ledgers themselves are payment channels. And the payment is happening atomically. So this is how Lightning works. These multi-hop payment channels where, here in this example, Alice is sending a payment to Dave, and it's one Bitcoin payment to Dave, and it is just hopping across a bunch of different payment channels. So the way this works in terms with the HTLCs is first Alice creates an HTLC with Coinbase, Coinbase creates one with Kraken, Kraken creates one with Bob. This is where Alice and Coinbase have a payment channel, and Kraken and Bob have a payment channel. So somewhat realistic example here. You can imagine how a payment channel could look like in practice. Then, to complete the payment, Bob reveals a preimage, receives the money. Kraken reveals that preimage to Coinbase, receives the money. Coinbase reveals the preimage to Alice and receives that money. And at any point, if there's a dispute here, you can actually exit the payment channel and go to the main chain and settle it there. Again, it's a little complex there, but what really actually matters here is this dynamic where you see sort of all this money gets locked up along this chain, and then when Bob reveals it, it all sort of ripples back. And so I don't know if this is why the Lightning Network is called this, but I always like to use Lightning as an example of this because I think it's really cool. If you don't know, Lightning doesn't really go down. You can see here these I knew this would happen. Oh no, well. Yeah, so you can see here that, well, this, unfortunately, the video's, oh, yeah, here it is. So when you see these paths of the ions going down, this isn't the lightning strike. This is just sort of like a pathfinding thing. Lightning actually strikes up. Lightning goes backward, and it's just like this payment here, where you're locking up payments. You can see just the lightning kind of going down and forking all across the HTLC network, and then the payment completes backward. So that's one way. That's the way to remember it. I don't know. I've never asked Joseph if that's actually why they call it Lightning Network, but I think it's a good way to remember that. So what is Lightning? One thing I've realized is a lot of people who are pretty familiar, people who use Lightning, don't really think of it the way that I think of it. And I think this is a helpful way. Is that Lightning is really composed of two ingredients, and they're composable, but they're separate. Payment channels give you off-chain bilateral ledgers between two parties, and HTLCs give you any cross-ledger atomic transactions. And so what this gives you is these cross-ledger atomic transactions where the ledgers are not public chains, they're just payment channels. And HTLCs are the part we're talking about here, not payment channels. I love payment channels. HTLCs are the problem, and that's what we're going to be talking about. So why I keep saying HTLCs are a problem? Why am I saying that they're a problem? So there's a lot of reasons, and I could get into a lot of detail about some of the more particular ones, but I think there's three big categories of problem with HTLCs. So the first one is the free option problem. This one's gone mainstream actually pretty recently, which I'm excited about. People have been sort of like realizing it more. The So the problem here is, remember, we had Alice, the path of an HTLC is that Alice first locks up hers, and then Bob locks up his. And when we're doing a this matters when we're doing a multi-asset HTLC. So usually Alice is supposed to complete the payment immediately, but what if instead Alice just sits and watches the price of, just sits on CoinMarketCap and watches the price of BTC versus LTC for 23 hours. They now have a choice. If they see Bitcoin rise relative to Litecoin, that means that the trade is no longer economic, but potentially, at the price that they made it at. So they can actually just let the HTLC time out and cancel the trade. In the unlikely event that Litecoin actually rises, Alice can complete the HTLC and get the original price that she was quoted. So Alice has basically entered into a financial agreement with Bob called an American-style call option, where she has this, she gets this right to complete the trade or not based on how the price moves, and that's worth something to her. That's worth a premium, but that's that she's not actually paying typically when she's doing an HTLC. In fact, on Lightning, if you fail an HTLC, you actually don't pay any fee for it at all, which means that you can really sort of do this effective attack on this. So people have been recognizing this. My good friend Zimineskipja said this on the Lightning dev list like about a month ago, and he put it as an argument for a single asset Lightning network because this problem doesn't really affect it when you're only dealing in a single asset, because the price of Bitcoin versus the price of Bitcoin doesn't really change. It's a very good analysis. I'd recommend going to look at it. He doesn't propose the solution that I like in it, but and he doesn't also talk about one of the other problems, and this is one that affects even a single asset Lightning network, and that's the griefing problem. So let's remember how these arrows go. Again, Lightning going down, there's the path being found, and we're like just waiting for the Lightning to strike, but what if it just doesn't? And Bob just says, I'm not completing the HTLC, I'm just holding on to my pre-image. Now everybody's money is stuck all day. Like this is money. Now Alice maybe knew what she was getting into sending this payment to Bob, but we now have this relationship between Coinbase and Kraken where they maybe have this payment channel that's doing a bunch of routing. They have one Bitcoin stuck in this payment channel that they can't use for any other payments for 24 hours. That's just a feature of the system. And this doesn't necessarily look that bad. Look, maybe Coinbase and Kraken, they got a lot of money, they can sort of wait it off, but this doesn't have to be just a 2-hop payment. This could be just a 20-hop payment. And Bob could have constructed this path specifically in order to mess with everybody that he wants to mess with along the line. And this is a way that someone could take down the Lightning Network, only locking up like one of their own Bitcoin for about 24 hours, but causing 20 times that amount of loss because it happens on every hop of the path along the way. And this is something that someone in the middle here just says they don't know Bob. They're just routing this payment, and they didn't sign up to have this one Bitcoin locked up for a full day, and they don't even receive a fee for it because it gets canceled. So that's the griefing problem. There's one more problem, and this is one that I think really was the one that affected me most because I was trying to actually implement HTLCs in something, and that's that embedding HTLCs in payment channels and using HTLCs in general is kind of complicated. One of the things is that it depends a lot on what kind of features you can support in your payment channel. It depends on what kind of features you can support on the base ledger. And it's a bit of a pain to actually settle them. And it's expensive. On Bitcoin, you have to do a few transactions in order to settle an HTLC. And that costs around, by the default, with the default values for HTLCs, I think that can cost around 50 cents on Bitcoin, depends on really on what transaction fees you're paying. But that means that one thing this means is that doing smaller payments than this with HTLCs isn't economical, and that's why that's something I'll get back to in a second. So okay, I've just broken you all down. Now I'm going to build you back up. What am I proposing as the alternative? And that's packetized payments. This is a piece of what's been developed in the Interledger protocol. The Interledger protocol is a very cool protocol. Again, I don't have enough time to talk about it, but it was developed by the people at Ripple. But it's an independent protocol for doing essentially a Lightning-like payment channel network, but potentially across a much wider set of assets. And this particular design decision that I really like, again, is called packetized payments. And you can maybe tell from the name that it takes some inspiration from packet switching networks, which is part of the history of the internet, when the internet was originally being developed, a lot of file sharing was done over connections, over dedicated connections between computers. And you'd imagine, you could sort of think, again, this is way oversimplification because I don't have a computer science degree, so I have no idea how this actually works. But if you imagine just like someone sends a file, you just be able to send a file, you try to send the whole file to somebody, you know, and you have a dedicated connection across maybe a bunch of hops to this party, and you're sort of sending the whole file in a row to them. Instead of sending in one big chunk, we split it up into tiny packets. We sort of switch them around, and it doesn't matter what order they arrive in. It doesn't matter if some of them get dropped because you can just restore them. I don't know how well I did there. I was terrified of that. But in Interledger, we do this, but we do it with payments. So let's go back to what the cross currency atomic swap problem was. That's again that we didn't know whether Alice was going to go first or Bob was going to go first. Well, this is a big problem because a Bitcoin is a large amount of money, right? And if Alice makes this one Bitcoin payment to Bob and Bob doesn't pay her, just exit scams her, that's a huge loss. But what if it was just like a really tiny amount? What if Alice just pays 0.001 BTC or even smaller? What if Alice just pays a Satoshi to Bob? In that case, Bob doesn't care if Alice doesn't care if Bob doesn't, just disappears now because she's only lost that amount. So what we just do is we just do that. We just do it over and over again. Like, you just make these really tiny, economically insignificant payments, and by doing them all in sequence, just going one bit at a time, you eventually make the full payment that you were trying to make, but at no point were you exposed to higher counterparty risk than you were comfortable with. So that's the protocol, that's the basic idea. This is, again, a very small piece of the Interledger protocol, but the part that I'm focusing on. I'm simplifying a lot of the ways that protocol works as well, but more or less, you just split it up into really tiny trades, and you execute it each of those at a time so that if at any point somebody tries to cheat you, you can just exit. There's a little more going on at the higher layer when you're doing a multi-hop payment here, but it's basically the same principle. It just happens for each of these hops, they're only trusting their counterparty to actually complete this payment. So none of it is enforced by the ledger, but that's fine because it's so small, it wouldn't even be worth it to have it enforced by the ledger. So what do I like about this? Because the payment amounts are so small, and including on these multi-hop payments, the griefing risk is very small because you can only be griefed by a really tiny amount. You can have very short timeouts on these packets, which means the free option, there can be very small packets and they can have very short timeouts because they don't have to be enforced by the ledger, which means the free option problem is also not a big deal because you do give someone an American-style call option, but it's for an extremely short amount of time. And as for complexity, and what really matters to me is that this works over basically any payment medium that you want, as long as it supports small and cheap payments. So it works over payment channels, but it also works over just trust lines. It works with bank accounts. There's my relationship with my bank. We could have do payments that way. It works if you're tossing pennies across the Grand Canyon. Like, it's literally any way, if I can pay you in it and it doesn't necessarily cost that much, then we can actually just do Interledger over it. So first question, isn't it expensive to do that? Not in payment channels. Payment channels are really cheap. And if your money's not in a payment channel, why isn't it? Like, it's just as easy to put your money into a payment channel on the main chain as it is to put your money into an HTLC. So instead of saying, oh, let's do an HTLC with someone across chain, just say, I'll make a payment channel with you, you make a payment channel with me on the other chain, and we'll do the trades that way. Doesn't it require some trust? Like, barely. You can have literally you can be literally just a Satoshi if you wanted. I don't think that's actually probably the right value for most of these relationships, but you can set it based on the relationship between the parties. If it's someone who's completely anonymous, you probably don't want to have a very high one. If it's somebody if it's somebody that you know very well, you might have a very high trust limit with them. Only your immediate counterparty can cheat you. Unlike in griefing, where somebody way down the line can, with HTLCs, can grief everybody along the line, only your immediate counterparty is actually able to steal from you, even in a multi-hop payment. And Lightning actually, because I mentioned before, it's expensive to settle an HTLC. It costs, again, I use a number like 50 cents. If the payment's below that amount in Lightning, it just wouldn't make sense to put it in an HTLC, so they don't. And this is a dirty secret of theirs. I'm sorry to out it here, but when you're making payments, like these 1 Satoshi payments in order to use Satoshi's place, it's using Lightning, that's fantastic. You're not using HTLCs. It's actually, everybody along the line is just sort of trusting their immediate counterparty in that. It's very similar to how how Interledger does it. And some slight differences that aren't really relevant here, but that shows you that look, people are basically willing to enter in this amount of trust. After all, in a payment channel, your counterparty can grief you for the fees that you have to pay to close the channel, maybe depending on which party bears that burden. So you just say, let's just factor that into the calculus of what am I willing to lose from if this payment channel counterparty cheats me. A lot of people make a big deal about atomicity, what happens if a payment fails halfway through. So one thing is, if it's a liquid enough network, you can just find another way to do it. You can have them send the money that they've already received back to you. Or in the worst case scenario, you can just go to the main chain, if you're on the same chain, and just make a payment to them there, which is the same as the failure case, by the way, of HTLCs, where if there's a problem with the HTLC completing, you may have to actually settle something to the main chain. Personally, I don't think this is a big deal. I think we just need to actually have transport layers and application layers that are able to tolerate and don't freak out about partial payment completion, or maybe at least temporarily until it's able to be completed. I also think if you have a liquid enough network, which is easier if you have these really small payments and nobody's griefing the whole thing, it's maybe possible to be able to find something, in almost all cases, find another route to there. Lightning people, because they love atomicity, they make a big deal about atomic multipath payments, which is this really complicated protocol for making this work. I think that's bad as well. I think atomic multipath payments is the wrong design choice because the way it works is if you have if you want to make an HTLC that's too large for your channels, you make part of it on one and part of it on another path. And in this, when the way atomic multipath payments works is that as part of the protocol, the recipient doesn't complete one of the HTLCs until they've received the other one, until the other one has been routed to them. But in that case, we're essentially asking them to grief the network. We're asking them to do that griefing attack where they hold open an HTLC that they could close. And we're doing it because, they'd be confused if they got a slightly smaller payment than they wanted to get. I think it's the wrong trade-off there. So the biggest objection, and I think this one has a lot of merit, is that large payments take more time. So the amount of time that a payment takes is proportional, in the happy case, is proportional to the size of the payment. Again, and it depends also on what the amount of trust is between these parties. So just back of the envelope, if you have a pretty fast payment channel, and again here you're working with the speed of light, by the way. Like if you've got computers that are really close to each other, then most of the work in a payment channel update is done just by the communications. So you can get very fast. So you suppose you can do 20 payments on this updates on this payment channel per second, and you're only willing to trust your counterparty for 50 cents. That's still a bandwidth or throughput of $10 per second, which I think isn't that bad. If you're willing to go much higher with the per payment amount, which I think people often should be, you could get a lot more. And the other thing is that I'm not sure Lightning is that good an idea for really large payments anyway. So this is just a completely back of the envelope chart of what it costs to do a Lightning payment over a payment channel network versus what it costs to do an on-chain payment as a function of how large the payment is. And the thing is, as a payment gets larger, it's just harder to route that over the Lightning network. There's more risks, and especially if you're using HTLCs, there's griefing risk there. You run out of the low-hanging fruit of liquidity, so you actually have this curve that slopes upward in how much it costs and how difficult it is to settle a payment on Lightning the larger it gets. Eventually, it's probably just worth it to go to the main chain or to find some other way to make that payment. So I think this is the prediction. I think mostly the use case of payment channel networks is primarily for small payments. It doesn't have to be necessarily be micropayments, but relatively small payments, because those are the ones that, again, it's uneconomical to do on the main chain, but are most effective on these networks. So other downsides, it doesn't work if you've got non-fungible assets or indivisible assets. So here I've got a visualization of a CryptoKitty being sliced into tiny bits. It's disgusting. it wouldn't work. The other thing is you couldn't put a CryptoKitty in a payment channel anyway. So you could put it in a payment channel. It wouldn't be very useful. You can't have a payment channel network for a single CryptoKitty. You really need a liquid fungible asset for that anyway. So I don't think it's necessarily that big a problem, but it does matter for some protocols. There's more complex protocols if you're trying to support something like gambling. You're trying to support certain kinds of atomic exchange of information where it often makes sense to do something like an HTLC. But for the basic use case of payments in a liquid asset across a payment channel network, I think the packetized payment approach is much simpler and tends to be better for that. So look, this is the part where usually people, I was gonna say, I like HTLCs, we can all live together. I'm over it. I don't want to write HTLC code ever again. But the Lightning work, it does support it. I'm not saying they should abandon it. And we can experiment with both approaches on top of it. You can do a packetized payment on top of Lightning just by making a lot of really small payments on it. That's one of the beautiful things about Interledger is that, again, it doesn't care what the substrate is. It can just work on anything where you can make these small payments. And in fact, there is a beta ILP Interledger protocol plugin for Lightning. So you can actually have an Interledger router that is making Interledger payments, and it's being settled on Lightning. But again, the larger network there doesn't care. It's just one of the hops in this network. And so I don't think the use of HTLCs precludes this kind of usage of these payment channel networks. And I'm predicting that I think these kinds of uses will, and these small payments will sort of become an increasing share of them because of their greater efficiency. That said, while I would love for this packetized payment approach to replace HTLCs on Lightning, I think the biggest advantages come when you're using it for cross-currency payments, and that's where you have the free option problem. And I think and a lot of complexity when you're trying to support other ledgers. And I think that's what makes Interledger great, is that it isn't nearly as opinionated about what layers it's able to be built on top of. So, and I want to say thanks again to Evan Schwartz from Interledger Protocol, who was the person who convinced me, one of the co-inventors of Interledger with Stefan Thomas, who was the person who convinced me that that's the right way. None of the ideas in this talk are original to me, actually. This is almost all from Interledger, from other people I've heard this from. And I also want to thank Lalu and Connor from Lightning for, I had just a critical error in this talk like a couple days ago that that I was arguing with them about something, and they convinced me to fix. So I appreciate that. And generally, I think they're absolutely brilliant. If I was as smart as them, I would probably be writing HTLC code all the time. But I think the different approaches, they totally work. So yeah, thank you, everyone. I hope I've convinced everybody. Does anybody have any questions?
Okay, so questions, maybe line up here.
So is your claim that if you're attempting to, let's maybe redefine this griefing attack and maybe call it like a liquidity DOS?
Sure.
Is that fair? Okay.
Sure.
Is your claim that if somebody liquidity DOSes the network, that it's 24 hours until the network can clear again?
It's 24 hours until that liquidity that's been locked up. So if the payment was 1 Bitcoin large, each of those hops has that 1 Bitcoin locked up.
So there's nothing, if you go back to like the routes in that flow, there's nothing preventing any of those parties from saying, hey, I'm not getting any new updates. I haven't gotten a pre-image, so can you just rebind, some new coins to a new hash? So I guess I don't see how it's possible that you're going to liquidity DOS those channels for the full amount of time.
So the intermediate nodes is a great question. They can't do that because they don't know what Bob is going to do. Because if Bob actually does complete that, then everybody's going to have to complete it, or they could get cheated by their immediate counterparty.
Sure. Okay.
So you have to trust your counterparty if you wanted to do that.
Yeah,
yeah.
And one of the things that I think was missing from the free option discussion on the mailing list was that as priced, there's a free option problem, and really there's a solution where it's just add some premium, right? Like in traditional options contracts, you just add some premium to.
Yeah, but I'm trying to make a payment, right? I'm not trying to enter into an American-style call option. I'm trying to actually just get money from A to B, and I don't necessarily want to pay an option premium or have to think about that.
Sure, but it's unavoidable, that value there. So that's how you solve that problem. And
well, no, but that actually does. If you do that, that requires the party who is paying the premium to actually exploit the full value of the option. So that would actually force them to wait 23.5 hours and get the maximum delta vega that they can from the option over that period of time. So I think that actually doesn't work economically.
And I guess
we can definitely talk after. I'd love to get to some of the other questions. Thank you.
Really enlightening talk. So the question that I had, because you could not go into details regarding packet statement, but how can we find out the loopholes that let somebody taking the money, how you determine that on such a large path, where is that person, or stop them, right?
Yeah, so this is my dirty secret, is that Interledger does solve this problems, and the way that it solves it is using HTLCs, but it does it at a higher layer. So it doesn't have the HTLCs enforced on the ledger. The HTLCs are just a concern of essentially the way that payments are routed, so you're able to identify and attest exactly which party was the one who cheated, who actually stole the money. But none of the HTLCs are enforced on ledger inside the payment channels. Yes, David.
Yeah, so you mentioned in your slide that packetized payments cap out at, maybe $10 a second. But you can, if you ramp that exponentially, so like say add 1% every trade, you can cap your losses to a total of 1%, even if you get interrupted multiple times. And so if you're doing that, you can transfer like the whole GDP in 3 minutes.
Absolutely, and I think over these long-term relationships, you can, very mathematically, reach a very high amount of payment and fight while capping your total losses as a percentage of the time of your relationship. I think that's sort of a formalization of the general idea that your channel counterparty is generally you're playing a long game. You're playing a long-term game with them where your goal is not necessarily to exit scam them immediately. It's to keep this channel open for as long as possible in order to collect as many fees on it as possible.
Oh, no.
Thanks, David.
I've lost my mouse.
Cool. Okay, thanks a lot.
Thanks.
Oh, no.
Okay. And next and last speaker before we have a break at around 10:30, maybe 10:35-ish, will be Patrick McQuarrie with State Channels as a Scaling Solution for Cryptocurrencies.
Awesome, thank you for that. I'm just setting up a timer. Yes, awesome. Yeah, so hi guys, my name is Patrick McQuarrie. I'm an assistant professor at King's College London. And today I'm going to present some work we've been doing for 2 years. And I couldn't have done this without the support of many collaborators, including Andrew Miller, who's actually in the audience, so that's really exciting. Surya Baxi, Edo Bentov, Chris Buckland, Sarah Meiklejohn, and Cara Rust. And I've also got to thank the people who support this research as well, so the Research Institute, the Ethereum Community Fund, and the Ethereum Foundation, because without that funding, it's quite difficult to do research. So the real question is, actually, let me ask one question. Who's heard of state channels before? About half the audience have, okay, that's really exciting. So hopefully I can remove some misconceptions around them as well. So the real question is, why do we need state channels? Why are state channels a necessary thing for cryptocurrencies? And as most people in the room are aware, cryptocurrencies do not scale. Bitcoin supports 10 transactions per second. Ethereum supports 12 transactions per second, sort of. It depends on how big your transaction is going to be. So the real question is, why do cryptocurrencies not scale? And at the heart of it, it appears to be this public verifiability property. And what do I mean by that? So let's look at the Bitcoin world. Today, the blockchain is 180 gigabyte. I can download it to my computer today, and I can validate every single transaction that's ever occurred. I can validate the entire network. So I can actually hold the miners accountable. Everyone in this room can probably still do that today. But the trade-off is, once we reach that throughput ceiling of 7 transactions per second, as we've seen last Christmas, the fees go from 2 cents to $20. So we actually reduce the diversity of peers who can afford to use the network. To the other extreme, let's pretend we could support 5,000 transactions per second. If we could achieve 5,000 transactions per second, we should have more users, because transaction fees should be really low. But then we lose the one thing that makes cryptocurrencies really beautiful. Most people cannot, we actually reduce the diversity of peers who can validate every transaction and hold these miners accountable. So the question is, with this public verifiability property at the back of our mind, how can we scale cryptocurrencies? And there's 4 different ways to do it. The easy approach is, let's forget about public verifiability. Let's have some single trusted authority who signs blocks and he just pumps them out. And then we get this 5K per second quite easily. But we don't want to do that. We're cypherpunks. We're sick of trusting people. We want to be able to hold them all accountable for maintaining the ledger. The next approach most people are looking at is, let's tweak the consensus protocol. Let's tweak the blockchain protocol. So that's sort of like Thunder, as we've seen yesterday, with Affinity's doing that. We could throw a DAG at it. We all love DAGs nowadays, although they blow our minds. And maybe we could achieve 5,000 transactions per second. But then we run into that public verifiability problem. So it doesn't solve the problem at the heart of scaling cryptocurrencies. So what other people are looking at is sharding. So the idea is that there could be a shard for hotel bookings and a shard for train bookings. If I only care about hotel bookings, I just validate this one shard, and I don't care about the rest of the shards. So now we can distribute that task of validation against different subgroups. But at the end of the day, if you care about cross-shard communication, or if you care about hotels and trains, you still need to validate everything. So we can distribute it, but we don't get rid of the, the underlying problem. So what I'm interested in is this off-chain approach. And the way it actually scales the network is not by increasing the network's throughput. It simply just reduces the load. So instead of sending every single transaction to the network, we send one transaction to set it up, then a group of parties can just locally execute the smart contract amongst themselves. They do thousands of transactions locally, and at the very end, they send one transaction to close the channel with the final output. So that's what I'm really excited about. How can we do this local computation with the same security guarantees as running it on the global blockchain? And there's lots of ways to do this. So there's approach first emerged in Bitcoin with Spielman channels, duplex micropayment channels, and Lightning channels as well. And then in the Ethereum world, we also have write-in channels as well. So these are payments. They're typically between two parties, as Dan just demonstrated for a channel. And the only thing they can really do is financial transactions. Maybe at the end of the day, that's all we need. But I'm more interested to see, can we push it a little bit further? So instead of just doing financial transactions, could we execute a smart contract locally between parties? Could we do gaming? Could we do voting? And can we do auctions as well? And now there's several different state channel constructions out there on how to do this. There's Sprites by Andrew Miller there. There's Perun channels, counterfactual channels, and Kassoon channels as well. So we know how to build state channels. But in the summer, what I arranged was this master workshop for people working on state channels. Because there's 7 different teams in the world. They're all doing slightly different things. And I wanted to work out what they were doing. So we all met up in Berlin, and we all did our presentation one after another. And what I learned is that we all disagree on what a state channel actually is. And we all have completely different terminology, which is why there's this language barrier between the teams. So I'm going to give you my biased opinion of what a state channel is. And a state channel is fairly straightforward. The idea is that we have a group of parties, and they've locked coins into the blockchain. And now they can install a smart contract off-chain. Let's pretend it's a battleship game. And then what they do is, every time there's a new state update, everyone has to agree to this. So, I play my move, the new state of the channel is that I've played my move. And everyone has to sign the new state update. And that's basically how a state channel works in a nutshell. Now, the state channel should give us 2 guarantees. Well, the underlying blockchain should give us these 2 guarantees. First is safety. I should always get the coins I deserve. If the channel breaks down, I should always be able to get my 10 coins from the channel. And then what really pops up in state channels and for HTLC payments is this new liveness requirement as well. What if I have a conditional transfer set up? What if I'm playing a poker game and the counterparty just stops responding? The blockchain should guarantee that transfer or application should always progress. So I can destroy the channel, redeploy the application to the blockchain, and just finish its execution there. So there's a safety guarantee and a liveness guarantee for these state channels. Now, as I've mentioned, there's 5 or 6 different constructions on how to build state channels. But so far, they've eluded real-world use. I mean, there's some dummy examples out there, but no one's really using state channels. So at the IC3 bootcamp in the summer, me and my little team thought, let's go build a state channel. Let's go build an application. And let's actually work out a real experiment of how this is going to work in practice. We had some questions we wanted to answer. So given an existing smart contract, what are the minimal modifications we need to make so it can be deployed in a state channel? What applications make sense in a state channel? And I'll get to this near the end. And finally, what are the inherent weaknesses? So what's really beautiful about a state channel is that we get instant finality. So once everybody has agreed to the state update, we can consider that final. And what's even better is that it's free. We can run smart contracts for free, locally between parties. There's no transaction fee to the blockchain, and there's no central hub that we need to reward either. So these smart contracts are free, and that's what makes it really exciting. So to do this, we built the 2-player game Battleship. So raise your hand if you know about Battleship. Who's played the game as a child? Half the room, okay, that's not too bad. Now, I always get this criticism as sort of, why do we build Battleship? It's a bit of a weird application to play on a blockchain. And the reason we did this is because every time you go to a state channel talk, the use cases are rock, paper, scissors, tic-tac-toe, the Go game, like that Asian one, and chess. And we wanted to work out, are these actually real applications? Well, they really work on the blockchain. You know, we're going to call their bluff in a sense. So we went and built it to see how it would work. So that's basically the idea of our experiment. And our experiment has two smart contracts. The first is the application contract, and that is just the battleship game. And it would run as normal on the blockchain today. The second contract is the state channel contract, and is simply responsible for the dispute process. You know, so it locks the coins in, and if the state channel breaks down, we can work out what the final state was agreed off-chain, and then redeploy the battleship game. So that's all the state channel contract will do. It's very simple. Now, for the experiment, we assumed the battleship game was already deployed on the blockchain. And you could continue playing battleship on the blockchain if you want. Now, Alice and Bob, they come along and say, let's cooperate. Let's take this off-chain, let's put it in the state channel, and let's start playing battleship off-chain. So they both sign the lock message, they send that off to the blockchain, the state channel is deployed, and the battleship game, all of its functionality is frozen. So it's still there on the blockchain, but it's completely frozen and no one can interact with it. So it's locked, in a sense. And now we have a state channel. So the question is, how do we play battleship off-chain? So let's assume the first state is 0. So every state has a counter or a version. And the initial state of the game is as Alice's turn to take her shot. So if you guys squint hard enough, you know, Alice is going to shoot from a real battleship, you know, bam. This is what it's like in Alice's mind as she plays this blockchain game, because it's so exciting. Okay, so how does she perform her attack? What she does is that she proposes the attack command. So she wants to attack a battleship. She gets the current state of the game, and then she just executes the command. And then she computes the new state of the game where she has taken her shot. She signs the new state, and she signs this over the Bob. And now Bob has to do the computation again to verify that that really is the new state. So he gets, you know, the current state of the game, the attack command, he executes it as well, he computes the new state, and then he simply checks, does this state match what I got from Alice? Yes, it does. So he signs that, and he passes his signature over to Alice as well. And by the end of it, they should hopefully both have signed the new state, and now this is the latest state of the game, state 1. And this keeps going. We get state 1, state 2, state 3, state 4. Whatever has the largest counter is the latest state we agreed off-chain. Now the question is, you know, this looks a bit too good to be true. So the question is, what if Bob stops responding? You know, what if he stops cooperating in the channel? And there's good reasons why he would do this. You know, maybe Alice just sank his last battleship, and Bob has lost a $100 bet. You know, why would Bob ever sign away $100? He will cooperate and just be really, you know, horrible until he gets his $100 back. So what if he doesn't respond? So every state channel has this dispute process that allows Alice to self-enforce the application's execution such that it will always progress. So how does she do this? So in the example we used, it's the most straightforward state channel that can probably ever exist. Alice will trigger a dispute on the blockchain. So you'll say, Bob's not cooperating, I need to trigger a dispute, I want to close the channel, and I want to redeploy the battleship game to the blockchain. Now, the smart contract will provide a fixed time period for both parties to respond. Alice will send the latest state of the game where she is just about to beat Bob. And Bob obviously can't send anything because that was the latest state. After the time period, Alice can resolve the dispute. Now what the state channel will do is it will accept the latest state, it will unlock the battleship game with the state of the battleship game. And now Alice and Bob can just continue the battleship game via the blockchain. So that's basically, at a high-level view, how all this would work in a state channel. But even that doesn't come for free, which is really frustrating. Because now we introduce the always online assumption. Both Alice and Bob must remain online and synchronized with the network. They have to watch out for disputes. And I want to give you an example of this. So let's just say Alice and Bob have played 4 battleship games. Let's say it's high stakes. Alice wins $1 million. And then Alice gets really excited. So Alice goes offline, she goes to a Lambo dealer, and she tries to buy a Lambo with her $100 million winnings. So while she's offline trying to be a Lambo bro, Bob decides, I want my $1 million back. I want to reverse that execution and get my money back. So what he does is that he triggers a dispute. He sends an older game state where he still has his $1 million. So he's reversed all 4 games. And now the blockchain keeps ticking. There's this dispute process, and if Bob's really lucky, the dispute process will expire, the Battleship game will be unlocked, and he can get back his $1 million. So now it's tense. Is Bob going to get away with it? Is Alice going to come back online? And she is. She's going to come back online. She's going to save her $1 million. So he sends the latest state of the game where she still has her $1 million. And this is what we call an execution fork. Because while they agreed off-chain the execution of the program, Bob just tried to revert it by using the blockchain and being taking the opportunity while Alice is offline. So this time last year, we were working on, how do we help alleviate this new security requirement? And this is where PISA comes in. So PISA is this leaning tower. I'm really bad at Photoshop, so it's supposed to lean towards the moon, because it's going to the moon. But anyway, it's this leaning tower. And the whole point is that it's a accountable third party. So before Alice goes offline, she could hire the third party to watch the channel on her behalf. And these are the goals we tried to satisfy. The first is state privacy. So when I hire this accountable third party, they should not be aware of the internal state of the channel. The second property is fair exchange. So when I hire this accountable third party, I get a signed and ratified receipt, and at the same time they get paid. So they get a micropayment for every job they accept. The other one we wanted was order one storage. So ideally, this accountable third party should only store one piece of information for every customer, the latest job that they received. And finally, recourse as a financial deterrent. So if PISA and Bob collude and they cheat Alice, Alice should have some recourse. She should be able to get revenge and at least penalize PISA for doing this. So what was our goals when designing the protocol? There's 2 contracts again. We have the state channel contract, which is the cute little robot, and we have the PISA contract as well. And the PISA contract really only has two pieces of functionality. It accepts a large deposit, and then it just waits around for evidence. If there's any evidence that the accountable third party has cheated, PISA will then strike and punish the accountable third party. So setting up PISA, how do we do this? We have the accountable third party. He has a smiley face. He's really excited to make lots of money watching channels. And he just sends over the little deposit, or big deposit, I guess. And now it's been accepted, and now he can start watching channels. How do we achieve state privacy? So this actually comes from how we construct the state channel. So as I mentioned, every time we sign a new state, we don't actually sign the state. We sign a hash of the state with a blinding nonce as well. So the idea is that all the accountable third party will receive is a signature from every party, a hash, and the largest counter so far. So that's how we achieve state privacy, because the idea is that they should not be able to brute force the state. Then fair exchange of payment and the cryptographic receipt as well. So I don't have enough time to dive into this, but it's actually really straightforward. So if you're familiar with Lightning and conditional transfers, what I do is that I get a receipt from the accountable third party. It's been signed, but it's not yet ratified. I set up a conditional transfer with the accountable third party, where if they reveal a secret, my receipt will be ratified, and at the same time, they will then get paid. It's very simple HTLC payment that I guess Dan doesn't like, but I like them. They're okay. And finally, what if PISA cheats as well? So, the idea is that there's Alice, Bob, and this accountable third party. Alice hires the accountable third party. Alice goes offline. And then PISA and Bob collude, and they steal Alice's money. If there's evidence that, PISA has cheated, Alice will come back online, so you'll see that the channel is closed, and it wasn't based on the state that, the accountable third party was hired for. So, PISA cheated to Alice, and that's really annoying. So is it too late? Can Alice do anything about this? And she can, because she has this signed and ratified receipt that she has hired this accountable third party to watch the channel on her behalf. And there's also a record of the dispute on the blockchain where the accountable third party could have responded, but they never did. So all Alice has to do is send the PISA contract, this signed receipt, and signed and ratified receipt. The PISA contract will verify it and say, yep, this was indeed a signed receipt from one of the accountable third parties. It will then talk to the state channel and say, state channel, give me the disputes that have happened in your channel. The state channel will return maybe one or two disputes, whatever list there is. And then all the PISA contract does is say, okay, I've got this receipt, I've got the dispute records. Was there a dispute within the time period? And what counter did it finish on? So it's very straightforward for PISA to verify that the accountable third party did not respond on behalf of Alice. And so what happens next is that the PISA contract says, well, sorry, you cheated, you broke the contract in a sense, so I'm going to freeze your entire deposit, or I guess burn it in a sense. So now he's sad, he's got a tear, he lost his very large security deposit. So revenge is sweet. So the whole point here is that PISA should only collude if by colluding they make more money than they will lose with the security deposit. Now in this scenario, Alice doesn't get compensated. There is a version where Alice could be compensated, and I can talk about that at the end if anyone has questions. And what I want to highlight is that PISA is not the only solution. So in fact, TADS presented Monitor at Scaling Bitcoin in 2016, and to the best of my knowledge, the focus was state privacy. I'm a customer, I encrypt a blob, and I send this to the monitor. So the monitor should never learn about the internal state. The issue was that because of the way the Lightning channel is constructed, you basically have to sign, for every new payment in a Lightning channel, I have to give a new encrypted blob to this monitor. So there's order and storage. So Watchtower was an improvement on this. The whole idea in Watchtower is that one, as a tower, I should be able to verify that whatever encrypted blob I receive can be used to resolve a dispute. I should also have order one storage as well. But the issue is that relies on a new consensus rule in Bitcoin. I think Rosabeef's somewhere here. I think it's for sig hash no input. So right now it's not deployable in Bitcoin, which is quite frustrating. And PISA, and it took me a long time to realize, what made PISA really distinctful? Why was this really important for this type of work? And it's mostly around accountability. There's evidence that the tower has been hired, and now you can do some recourse to punish the tower as well. So that's basically how all the three different solutions compare. Now I'm going to have some final thoughts and start, wrapping up. So state channels are really exciting, as I said at the start. There's instant finality, there's no latency, and there's no transaction fees. In the best case scenario, there's 2 transactions on the blockchain. We set up the state channel, we close the state channel. But for Battleship, there's a really, 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 really bad worst case. And this is sort of the heart of what this experiment came out of. Because in the worst case scenario, Alice and Bob, they set up the state channel, they set up the Battleship game, and now they're committed to playing the game. A Battleship game has over 200 transactions. So what Bob does is Bob says, well, I'm not going to cooperate, Alice. I'm not going to sign any future state update. So now Alice is forced to trigger a dispute and redeploy the Battleship game. And now that both players have to finish the game on the blockchain. Now, why is this a really bad worst case? First, there's a transaction fee for every move, because now you're forced to play a Battleship game on the blockchain that you thought you would play in the state channel. And now there's blockchain latency as well. So Battleship's a turn-based game. You have to give a grace period for a transaction to get into the blockchain. So that might be 5 or 10 minutes, for example. So my questions to the audience. Okay, let's pretend you set up a state channel and there's a $100 bet. And now the counterparty has forced you to play this on the blockchain. Would you spend $24 to play the entire Battleship game? And in the worst case, would you wait around for 16 hours? Raise your hand if you would do that for a $100 bet. No one here would do it. Okay, one, you're dedicated, to the Battleship game. But that's the whole point, is this is human behavior. Bob's a bot, and in our experiment, it was actually 2 bots playing Battleship. That's the fun about this. So this is why it doesn't scale out. Because in the worst case scenario, you just take advantage of human behavior, you go back on the blockchain, and there's no way people are going to play Battleship on the blockchain. So what are the outstanding research problems because of this? So some questions I've had in the past is, have a reputation system. Maybe you'll only play Battleship with other people with good reputation. The problem in a state channel is that, and actually all channels together, while we can identify who triggered this dispute, but we can't identify why the channel was closed. Did Bob just refuse, or is Alice pretending that Bob never signed the state update? So we can't attribute blame to why the channel broke down. So in that case, you have to punish both parties for that. So reputation systems are non-trivial for the layer 2 channels so far. I don't know of a proposal yet that would be viable. The next question is, how do you induce cooperative behavior? So how can we set it up where both players just don't want to close the Battleship game, or they both want to continue off-chain? For smart contracts, like Battleship, it appears this can only be achieved if the smart contract is already reasonable to execute on the blockchain. If you're willing to execute the smart contract on the blockchain, you're willing to execute it in a state channel. Payments are slightly different, and this sort of comes back to Dan's talk. So Dan, you had a very good talk. You mentioned 3 times. What's interesting is that, let's just say I have a micropayment channel with YouTube. Every kilobyte they give me, I send them a Satoshi for that. Every intermediary transaction, there's a positive utility for both parties. I get my file, and they get paid. So because every intermediary transaction has a reward, there's possibly some way that could scale out, where we could do more payments that aren't typically doable on the blockchain. So for payments, there's some intuition to say we could induce cooperative behavior. For smart contracts, it's not clear yet if that's going to be the case. And finally, there's one outstanding research problem that is still unsolved. So one issue with a channel is that I won't use the dispute process if there's blockchain congestion. If the fees go from 2 cents to $20, it's no longer reasonable for me to resolve the dispute. So some ideas around that is, could the blockchain self-inspect congestion and say, well, out of the previous 1,000 blocks, only 200 were reasonable in terms of fees? That would be a really cool new opcode. And I've got some ideas how to do that, but that still remains an outstanding research problem. So I guess I'm going to summarize now. 2 years later, we are on the verge of practical and deployable state channels. There's so many constructions out there. We did an experiment. We can actually demonstrate how they work in practice. Magic unicorns need no longer apply. They're not this weird magical wizardry trick that people can't do. Most people here could do it within a few weeks. So thank you for listening. This is sort of a summary of the work we've done over the past 2 years. So Sprites, spearheaded by Andrew, actually has one of the first state channel constructions. I always find that's like in the Sprites paper, there's 2 elements, the preimage manager and the state channel. The state channel doesn't get as much attention, but actually was one of the first state channel constructions that ever existed. The M-Pesa was this accountable third party who you could hire to watch the channel in your behalf. Kitsune was this really basic state channel for playing Battleship and the Battleship experiment. And just in the past few weeks, me and Chris have been thinking of this idea called a state assertion channel. So one prominent state channel is, when I want to trigger a dispute, I have to eventually send the full application state. And for Battleship, that's like $1 or $2. So how could we do it where an honest party never has to send the full application state? And if an honest party does, they always get refunded for doing that. So that means a dispute has a near constant cost of around 20 cents, or around 70,000 gas in Ethereum. So I just put that online today. It just got accepted at a workshop. We wrote it in about 5 days. I was really excited about it. So that's basically the summary of our work. And again, I have to thank my collaborators, Sarah, Ido, Syria, Andrew, and Chris, and the sponsors for our research. Without them, this would never be done. You can only do as much work without your collaborators. So thank you for listening.
Okay, thanks a lot. Any questions for Patrick?
Oh, don't die.
So how do you achieve fair exchange off-chain?
What, for the receipt?
Yes.
It's a really cute little trick. So the idea is that as a customer, I give the Pisa Tower the information that should be in the receipt.
Yes.
The Pisa Tower will then compute a secret, and the hash is part of the receipt. So now they send over a signed receipt with this hash.
Yes.
But it's not yet viable. It's signed, but it's not ratified. So as the customer, I now set up this conditional transfer. I say, Pisa, if you reveal the pre-image of this hash, you will get the payment. If they reveal the pre-image, my receipt is now ratified because I have the receipt and Pisa's secret, the pre-image of their hash. At the same time, because it's a conditional transfer, they also get paid.
Then this payment should be an on-chain payment, right?
A what? No, it's just a normal HTLC conditional transfer. It's exactly how you would do it in Lightning. So, because the idea is that off-chain, if there's a condition, they give me the secret, and then we both cooperate, and we just remove the condition altogether. In the worst-case scenario, I can broadcast the conditional transfer to the blockchain, and then the payment sent.
Yeah, okay.
Awesome.
So I feel like for the application agnostic state channel, I like the idea.
Sorry. How do I shut this up? There you go. Okay.
It sort of makes an assumption that the users on each of the application that they use are verifying these states.
Yep.
But are there primitives for users to be able to build these verification tools that they can find correct in verifying the state? And how
Well,
does
the
that-
idea, so there's two elements to this. So right now, there's just a single smart contract. So what I do is that I just use a smart contract that's already on Ethereum, and I just run the function myself. So we're both running the exact same code that's already on Ethereum, for example. What would be nice, and what I'm really excited about is, if this was like a zero-knowledge program, then we could just, every new turn, like every time we send a new state update, it just has a new proof that says this is the new state of or at least that the game was run correctly. So with the zero-knowledge proofs like Starks and Snarks, we could scale out of the computation we can do, and the state channel is just enforces, that everyone agrees to the new proof.
Thank you.
Okay, cool.
Other questions? Great. Okay, well, thanks a lot. And now we have a break till 11.
Yeah.
Thanks.
Okay, everyone, we'll get started, so please be seated. We'll have a short session now of 2 talks, and then followed by a lightning talk session before lunch. And we'll start with David Vorik from Obelisk, who's going to tell us about ASICs. Thank you.
Hello. Okay, so my name is David Vorik. I've been paying attention to Bitcoin and cryptocurrency since 2011. I'm the lead developer of Saya, a decentralized cloud storage platform. And I bring that up because I come from the coin developer side of the world as opposed to the hardware side of the world. So as I work with hardware, I'm constantly thinking of it from the terms of coin devs and what we care about when we build cryptocurrencies. And I'm also the Obelisk CEO, which is a cryptocurrency ASIC manufacturing company. And so I was asked today to talk about cryptocurrency ASICs. And so that is a really broad topic. And the format that I've chosen is that I'm just going to blast through as much as I can. And I'm going to try and leave some more time for Q&A at the end. And kind of have something closer to an open forum. So hopefully we'll get like 10 to 15 minutes of Q&A at the end. And so yeah, we'll see how it goes. So I think the place to start with ASIC manufacturing would be at the foundry. So a foundry is a company that is capable of manufacturing or is actively manufacturing cryptocurrency ASICs. And then you have these things called fabs, which is essentially a facility that is capable of manufacturing ASICs. So there are just a couple dozen foundries in the world, maybe 100 fabs. And then as far as, so within a foundry or within a fab, you have these things called processes, which is essentially a methodology for building a chip. And these processes have names you might recognize like TSMC 16 nanometer or Samsung 7 nanometer. And as an aside, the name 7 nanometer or 16 nanometer is less a description of the process itself. For example, 7 nanometer is like really your feature size is in the 40 nanometer range. Instead, when TSMC says 7 nanometer, what they mean is this is the thing after our 16 nanometer version. And 16 nanometer itself, was after the 28 nanometer version. So you can nano marketing is a term I've heard before. But it is a pretty good indicator of which level each thing is relative to the other levels. So in cryptocurrency, there are really only 2 foundries that matter, which is TSMC and Samsung. There are other foundries that are sometimes involved, but for practical purposes, it's mostly TSMC and Samsung that we care about. And then pretty much everything is at either TSMC 16, Samsung 14, or some more advanced node. And so if you see 28 nanometer, 65 nanometer, generally that's not going to be a cryptocurrency ASIC, at least not a competitive one. So after you have a relationship with a foundry and you know what process you're targeting, you have to do chip design. And so generally the foundries aren't the ones who design the chips. You have chip design houses or chip design teams that come together and they decide what circuit or what physical structure the foundry is going to assemble, and they pass instruction sheets off to the foundry, and the foundry uses that to assemble manufacture your chips. So there are 2 major design methodologies. One is digital, one is analog, and I'm going to break those down. So digital design is what most of the industry is today. It's what you use to make CPUs, what you use to make GPUs, AI, machine learning chips are all digital design. Digital designers work with ones and zeros. They work with, a standard library of full adders, half adders, XORs, ANDs. And so they're not really working at the physical level of the chip. They're working at this abstraction layer, kind of like a programming language, and they'll often program in Verilog. And so then they use a tool called place and route to take their high-level gate designs, and then that tool will translate it into a physical design on chips. The advantage of this is that when you're not worried about currents and resistance and like all these physical features, you can move a lot faster. And so that's why pretty much everyone today uses the digital design methodology, is because if you were to use analog, it'd just be too slow. So most chips today are quite complex and are really only possible using digital design. Analog designers don't really work with gates as much as they work with like signals and physical features, and it's like a lot more intense and a lot more hands-on, and it's a lot slower. However, because instead of thinking about gates, you're thinking about the actual wires connecting the gates together, the actual like fins on the process, you can do a lot more optimization. So analog chips tend to be a lot better, but they take a lot longer. And so even, I forgot to say, a complex digital design might take 1 to 2 years to make. A simple digital design might be 2 months, or even just a few weeks if you have a highly coordinated and pipeline process. But in analog world, simple chips will take 6 to 12 months, and complex chips are just not feasible. The whole industry will have moved on to new processes. We'll be at 3 nanometers before you finish an Intel CPU in an analog design, for example. So in the cryptocurrency world, it's pretty much mostly analog, actually. So all Bitcoin chips that are competitive are analog, and that's because the SHA-256D circuit is relatively simple, and it's also a static target. So for example, in the GPU world, NVIDIA is not trying to make like a theoretical GPU. A GPU is trying to hit a target set of use cases. And as the world grows, that set of use cases is a moving target. If you're spending too long optimizing a chip, it doesn't work. In Bitcoin, SHA-256D is not a moving target. It's static. And then on the ASIC resistant side of life, that's mostly digital. It's usually about getting to market fast. Usually you're going to be bricked anyway. So you don't spend as much time optimizing, and you more worry on the digital or on the ASIC resistant side of just being fast. And for that reason, a lot of ASIC resistant chips end up being digital, or they're just too complex. So now I'm going to take you through a couple of like layers of optimization that you can do in chip design. So the biggest and like most classical would be algorithmic optimization. And I think this is something that anyone in software can do. A good example would be early termination in Bitcoin chips. So in SHA-256D, you have 128 rounds of SHA that you have to do. You get a result. You look for a bunch of leading zeros. But actually, if you work backwards, there are enough leading zeros that you can work backwards through the SHA algorithm, and it becomes apparent as early as like round 121 whether or not you got all of those leading zeros. And so there's no reason to do all 128 rounds. You can usually quit at 121, and that's an algorithmic optimization. The next level down, you do circuit level optimization. And so I'll use the adder as an example. So if you're adding two 32-bit numbers together, there are maybe 20-ish. It's a large number of different commonly used ways to add two numbers together. And some of the methodologies will give you a chip that is very energy efficient. Some of the methodologies will give you like an adder that is very tiny. And in the chip world, area equals money. So you like small things because it saves you money. Some of them are very fast, so a circuit optimization would be looking at like all the different things that your chip is doing and all the different maybe high level or business goals that you have, and picking the types of circuit constructions that optimize for your end goals. So once you have your circuit, the next thing down would be place and route optimization. In the digital world, sometimes this means that instead of letting your chip compile for 3 days, you let it compile for 2 weeks. And it just takes more time and tries to optimize better. If you're going to go into the analog world, that's where you start to do hand routing. And so you'll have designers who will just place the wires by hand and try and figure out the best way. And usually, the people doing it by hand will be 2 to 5x better than what the machine can do. Although there are situations that are much more brute force, and of course the machine is better at just brute force optimizations. So if we go down one step further, even in the analog world, designers will often use standard cells. And so you have your XOR gate or your NAND gate, or I'm going to use a half adder today as my example, which has 2 inputs and 2 outputs. And generally, the foundry will give you a set of cells somewhere between like 30 and 90 depending on the maturity of the process, cells that you can use that are pretty general purpose. And so they have reasonable trade-offs between how much electricity they consume, how fast they are, what voltages and temperatures they can run at. And so they'll be qualified in a certain range of physical conditions. If you know that you are going to be running things at low voltage, for example, most foundry cells will be qualified at around 0.6 volts. Bitfury, I believe, runs their chips at 0.27 volts. You can't use the foundry standard cells anymore. You have to make your own. And so you can actually take these XOR gates, and you will, at this level, you are taking physical features of the chip. You're talking about fin distances and just other really physical stuff, and you're running simulations that are trying to emulate physics to optimize your gates. And so if you want to get into the Bitcoin world, you're going to have to actually do some standard cell optimization. This is a place where it's pretty rare that people get involved, although I do think most of the major AMD, NVIDIA, Intel all do standard cell optimization for their chips. So one of the things that's like really interesting to me is that I saw a spec sheet for a half adder, and it had different timings depending on what the inputs were. So if you have a 1 and a 0 as an input, the time it takes for the computation to complete is going to be different than if you have a 0 and a 1 for an input. And also the amount of power that it consumes is going to be different. And so if you know that within your circuit you have a lot of gates where you really need to reduce the time that you get the second output, the second input's going to be really late, and you need the second output to be ready as soon as possible, you can actually reconstruct the physical components of your gate to optimize that. So once you have your chip laid out, you have all the optimizations in place, you're ready to go, you do something called tape out. You essentially, you produce something called a GDS, which is like a bunch of images. Your chip is a bunch of layers, and so you'll have a different image for each layer of the chip. That image is something that the foundry can turn into manufacturing steps. They make these things called masks, which are essentially, for a single chip, you might have between 80 and 150 really high purity pieces of glass with chrome on them that etch out these really fine-grained features. These masks genuinely cost millions of dollars. The precision is extremely high on the chrome etchings, and the glass is very pure, and there's a fair amount of them. But basically, after you tape out, that's like the chip is complete and the actual manufacturing is started. So a big element in cryptocurrency is turnaround times. And so one of the big turnaround times that you really need to focus on is the time between taping out, the time between sending all of the instructions to the foundry, and the time that you get your first chips back. And so at 16 or 14 nanometers, this is going to be typically between 75 and 100 days. And that's something that you really look to optimize over. Some of the, I don't know if I would use the word sloppier, but some of the less sophisticated foundries will have longer turnaround times at the same process. And so that's one of the reasons that TSMC and Samsung become really important, because they can be days or weeks faster than the competition. And in ASIC races, every week counts. So on the whole, if you're doing a simple digital chip, you can get a design done in maybe 2 months, 2 to 3 months. If you already have a design completed and you're just tuning it to match a new algorithm, you can get it done in as fast as 2 weeks. And then you have to tape out. If you're taping out at 16 nanometer or 14 nanometer, it's going to cost you between $3 and $5 million. That's just to make the masks and to get the foundry interested. And so in total, a really streamlined process, at least at 14 nanometers, is probably going to take around 6 months. If you have a more complicated chip design, the design phase is going to be longer. And so that's going to push your timeline out. So beyond chips, you have the machine construction. And just to highlight the importance of it, if you, the Bitmain S15 chip, if I read the spec sheet correctly, is capable at standard operation of doing 42 joules per terahash, which sounds insanely good, but then when you put it in a rig, when you put it on a hashing board and connect it to a power supply and plug it into the wall, you add the overhead of the fans and everything, their whole machine is actually running at about 57 joules per terahash. So they're losing something like 35% from the chip to the wall. And this is a highly sophisticated machine. And so I say this because we've seen a lot of people trying to compete with Bitmain, where they'll get a chip down to, their chip level efficiency will be similar to what the S9 efficiency is for the whole rig, and they'll miss the part that they're going to lose another 40% power when they put that chip onto a board. But that's like, Bitmain's at the head of the industry, and even they're losing as much as 35% power. Another thing that Bitmain's been really good about, one of the big innovators in the space, is cost reduction. So a traditional approach to put 63 chips on a board might cost like $5,000 per machine. So if you were to give a standard designer like 189 chips and tell them to put it on a board, they might give you a bomb that comes back at $5,000. But Bitmain, I would estimate for the S15 is closer to $1,200. This is of course not publicly released information, and I don't have any inside source or anything. That's just my appraisal of what it probably cost them to produce the thing. And that is just something they've spent a lot of time optimizing. So this is the part where I'm going to open the floor to questions. If there's not too many questions, I'll just ramble about these topics. But these are more things that I wanted to put into my presentation, but felt that I'd rather open the floor. So if we could have people line up.
Yeah, so we can take questions here.
Was curious, like, what your perspective is. I've heard that in industry there's kind of a trade-off between chip size and failure rates, and kind of like the variance in you can do a lot of little chips, and your whole board isn't going to get nuked if like a couple of them fail, versus like having a more efficient, larger chip, but you have a higher catastrophic case.
Yeah, so it's actually, yields are less of a problem in the cryptocurrency industry. So in the rest of the chip industry, you got these CPUs and GPUs, which end up being pretty big. Chips are really hard to make, and if you have like one atom of contaminant in your chemical bath, then that might result in one bad chip. And so just lots of chips come back poorly. If you have a bigger chip, the chances of one of your transistors being broken go up, and the chances of that being a critical transistor go up. In the cryptocurrency industry, because our designs are like a SHA-256 ASIC isn't one SHA-256 like engine. It's like a bunch of them. And so if one transistor goes out, you're maybe out like 1/30th of your chip is not performing anymore. So yields tend not to be an issue. When you see cryptocurrency manufacturers go for really tiny chips, it's for heat, because we have some of the hottest chips in the world, and you can't cool. If you were to put it on a big die, it would just overheat.
So one of the things I've been wondering about is why are we using ASICs instead of FPGAs? Because there's a turnaround time advantage to an FPGA in that in 24 to 48 hours you can adapt to a new algorithm, and they also run extremely fast and are very low power. So what are your thoughts on that?
Yeah, so FPGAs are typically between a factor, I want to say it's like a factor of 100. It's 10 to 100 behind an ASIC. So if there's no ASICs on the market and everyone's FPGAs, that's good, and you can come to market a lot faster. But the moment that first ASIC shows up, the FPGAs are done.
I was wondering if you had any thoughts on the PROG POW proposed algorithm for Ethereum and whether that's going to be successful in resisting ASIC development.
Yeah, so I have a disagreement with the PROG POW proponents. I believe that there are lots of corners for optimization. I believe that when NVIDIA or AMD makes a GPU, they have a wide range of considerations that they have to care about, and when we're making cryptocurrency mining machines, we have a much narrower range of things we care about. And every time you reduce the scope of things you care about, for example, NVIDIA wants a certain level of yields. They want their chips to be running fine at a wider range of temperatures. If we have to mandate that our data centers keep the chips, at 80 C or 90 C, this is kind of already a mandate anyway. And so I think that ultimately there will be, if PROG POW gets adopted by Ethereum, I think there will be PROG POW ASICs. And then it's an open question whether it'll be like 3x, 8x, or like a 25 or 50% improvement. But I think you'll definitely see them.
I'd love to hear more about selective hard forks, what they are, what you think the degrees of freedom are for designing for those.
Yeah, so selective hard forks is a really interesting thing that I originally heard about from Greg Maxwell, which is basically when an ASIC manufacturer makes an ASIC, they add a little surprise gate in there. So they add a switch that they can flip. And so instead of mining SHA-256D, you're mining SHA-256D prime. And the difference is like 3 transistors. But to everyone else who's trying to guess which 3 transistors those are, as the manufacturer, not the devs, as the manufacturer, you add that in and you keep that secret. And then if the devs ever end up in a situation where there's some bad hash rate on the network, someone's using ASICs to 51% or something, you can take that extra little circuit to the devs and you can say, if you hard fork to this thing, all of our ASICs will still be mining, so you don't have to fall back to GPUs, which that's a longer discussion. GPUs are insecure, and I'll drop that there. But so you can fall back to ASICs without having to fall back to GPUs. You can break the bad guys without the good guys being broken. And if every manufacturer makes a little different carve out, you can actually, the devs can choose which manufacturers that they keep. And so if the devs have identified exactly which manufacturer is the bad actor, they can break just that manufacturer and leave everyone else alive, which is a political nightmare. It's politically very intense to do something like that.
Hey, thanks for doing the talk. Found it pretty interesting. So this is not specifically relevant to your talk, but I'm wondering what your opinion is on ASIC resistance, and if you think it's something that's sustainable in the long run. Do you think that there are any proof-of-work algorithms that can successfully defeat ASICs just by virtue of their general design? And thirdly, I know I'm piling these on, do you foresee commoditization of ASICs becoming practical?
Sure, I'll take the questions. So if there is to be an algorithm that is ASIC resistant, the strategy used by the ProgPow team is the most effective strategy. That said, as I kind of said earlier, I don't think it's sufficient, and I don't think ASIC resistance is possible. I think ASICs are inevitable. There's one strategy that is working right now reasonably well for some coins, which is to hard fork every 6 months. For over a year now, there have been at least 2 cryptocurrency ASICs, general purpose cryptocurrency miners in development. I don't know what the status is. I don't know when they tape out. But those will be better than GPUs and will be able to follow hard forks every 6 months. So the strategy, it's currently sound. We don't know how much longer it's going to be sound, but my guess is 2 years at most, probably 1 year at most.
So you don't really think it's sustainable for these coins to continuously fork or attempt to remain resistant?
No, I think that we got maybe another year of being able to depend on getting rid of ASICs reliably. And then commoditization. I do think that we will see commoditization of the really big coins. So once you get over $1 billion block reward per year, you get into the territory where margins are no longer so slim that there's just one monopoly, one winner, and nobody else can afford to enter the market. And so at least for Bitcoin, and we're already kind of seeing that, you're going to see more and more ASICs come out, and that's going to, as these manufacturers have to compete with each other on even footing, that's going to even things out. But even Ethereum is not at the block reward required to see that happen, I don't think. So all the small guys just have to deal with monopolies.
Thank you for your presentation. You talk about lots of ASIC things, but I'm a little bit wondering about how your PCB is designed, how many additional chips, gates, and resistance capacitor you need, or how big is your ground?
Yeah, so PCB design is super interesting because I think there are a lot of optimizations that the cryptocurrency industry has done. For example, in standard design, you take a buck, you might, your voltage, your input voltage will be 12 volts, and you're running all your chips in parallel, so you shift that down to, say, half a volt or a quarter volt, and when you do that, you lose a lot of power. Also, you add a lot of current. So you're gonna, if you have 60 chips on your board, you might have 2,000 amps running through your board, which is not reasonable. So what you do instead is you run your chips in series, which adds all sorts of engineering problems and noise and a lot of headaches associated with running chips in series, but instead of 2,000 amps, you're dealing with 50 amps. Instead of 88% electrical efficiency on the voltage step, instead of stepping from 12.5 to 0.5, you're stepping from 12.5 to 10.5. That might be 97, 98% efficient. And so you save tons of money, you save on electricity, and then you just do a lot of creative things, both chip side and PCB side, to manage the string problem. And that's like one of the fun, interesting challenges in the PCB world.
Hi, David. Thanks for your presentation. I actually wanted to piggyback on the question in regards to the hard forks every 6 months. And I wanted to specifically ask if you would comment or voice your opinion on cuckoo cycle for GRIN in the ASIC resistant and ASIC targeted proof of works.
Yeah, so I think GRIN just made it. So I think that we're still at a point where hard forking every 6 months is probably going to be okay for their ASIC resistant side of things. I also think that the GRIN, so right now we're seeing a nice hash problem. If your block reward is small enough that nice hash can point all of its GPUs at you, you're going to get 51% attacked and exchanges are going to get double spent. GRIN, and I've been watching, seems to be outside that threshold by not very much. And just because you make more money as a GPU miner by being on nice hash most of the time, that problem is going to get worse. But at least right now, it seems like GRIN is ahead of the curve. And so I think, again, this isn't a strategy I would recommend that people replicate a year from now, but it seems like it's going to be okay this time.
Thank you.
Hey, my name's Alex. Why chips? Why not whole wafer custom interposer ASICs?
Yeah, so for something like SHA-256D, there's no reason to do interposers. For something like Cuckoo-231, when you got all this memory that you have to deal with, then interposers do make sense.
No, my question is why break the wafer at all? Why not whole wafer ASICs?
I think because you just can't, I don't think the way that foundries work, I don't think you can make whole wafer ASICs. So you have this thing called a reticle. It produces a cut on a wafer that is 25 by 35 millimeters at most, and then your whole chip has to fit inside that little tiny square. And so that's why GPUs don't usually get bigger than 600 square millimeters. It's because the actual, the masks that we make don't do a whole wafer at once. They do a little tiny square 100 times. And then I don't think it's possible to connect the circuits between them. The precision on the stepper motors is not high enough.
Hey, I'd love to hear your thought on the difference when you design a chip which is for memory bound versus compute bound. Is there significant difference between the two?
Mimblewimble versus?
At hash for Ethereum, which is memory bound, or a SHA-266, which is CPU bound. When you design the chip, is there specifics when you want to design memory bound proof of work chip?
Yeah, so I think every chip is its own fun challenge. The trade-offs that make sense are going to be different, and we've looked at things like ProgPow, Ethash, obviously Cuckoo-2, and for everything, the optimal memory architecture is going to be different. And so basically, it's just a bunch of engineers in a room beating ideas against the wall and trying to figure out the most efficient way to get the data from one place to another. And get the computation done. So I think with any memory hard chip, you're just going to end up with a custom memory architecture that has to be refined over time.
I have two questions. One of them is, do you see any hope in alternative proof of somethings around memory size or other expensive operations that don't require spinning transistors through computation?
I do not.
Okay. And then the other, that's fine. I kind of thought so, but I just.
Okay. Yeah.
And then the other one was, do you have an opinion about in moving from proof of work to proof of stake, miners revolt? Economically, this is a big break function if that actually is working out from a miner perspective.
So that's a great question. I actually had a first slide that I took out, but this is my first slide. So with proof of stake and really any pre-proof of work consensus algorithm, you have to pick I'm going to use the word trusted setup. You have to pick a trusted setup. There's a set of keys or identities or signatures that govern all the rules. And so you have this tight little bounding box. And the goal is to get it so that tight little bounding box can grow and change and morph. But ultimately, it's a trusted setup, and you don't really have any great way to verify that, the state of that. Proof of work provides this great tether between the physical world and the digital world, and so we get to blow that bounding box up to all of physics. So if you have access to raw materials and lots of know-how, you can make your own transistors, you can make your own CPUs. And so I'm not a fan of proof of stake for a large number of reasons. I think on many sides it has significant issues with it. And I think that proof of work really is like super revolutionary, and it's like the best way forward.
Thanks for the great talk and Q&A. So let's thank David for this. So our next talk will be given by Ben Fish. Ben's my office mate. He's also a PhD student at Stanford University, advised by Dan Bonnet, and he's going to be talking about proofs of replication.
Proofs of space.
Proofs of space.
Yeah.
And replication.
And replication. Okay, thank you for the introduction, Florian. So this talk is about proofs of space, also about proofs of replication, but specifically about tight proofs of space, which will become apparent in the talk what that means. So first, let's start with what is a proof of space? Well, a proof of space is an alternative to proof of work, and applications have been proposed similar to the applications of proof of work for spam prevention, DOS attack prevention, or simple resistance and consensus networks, which is most relevant to this conference. And what is the basics of a proof of space? Well, you can think of it as an interactive protocol between, say, a miner or a prover who has some disk storage and claims that, hey, I am storing 1 gigabyte of data, just arbitrary data. And then there's an interactive protocol where the prover sends some kind of ID that represents this particular proof, some kind of commitment message, gets a challenge from the verifier, and then sends back a proof, and the verifier verifies the proof and should be convinced that indeed the prover is storing at least 1 gigabyte of data. Now, importantly, the proof for this to be an interesting type of protocol should be very small compared to the size of the data. Now, as is common in interactive protocols like this, we can make the protocol non-interactive using a standard trick in cryptography called the Fiat-Shamir transform, where instead of having a completely interactive protocol, the prover first chooses the ID and the commitment, and then basically generates the random challenge as a hash of the first message, and then sends a proof, which the verifier should be convinced of, and then concludes that at least at this particular moment in time, the prover must have been storing or using that much data, that much storage, say 1 gigabyte of storage, in order to produce a successful proof. But then we could also talk about a proof of persistent space, where you kind of move this interactive protocol or non-interactive protocol into an initialization phase, where the prover initializes its storage, fills up its drive with 1 gigabyte of data, and says, "Hey, I'm storing a lot of data on my disk," and then send a commitment to that, and then later, during a repetitive online phase, receive challenges from the verifier, and if the prover passes, then it indicates that the prover is still storing that same 1 gigabyte of data. And the reason why we split it up like this is because the initialization phase is a relatively expensive operation, whereas the online challenges become very cheap to just check that the prover is still storing the same data. Now, in order to have a meaningful notion of security here, the online phase actually needs to require some kind of notion of a time limit or a time-limited response. Otherwise, the prover can start over from scratch and generate everything from the beginning. So the idea is that if the prover deletes its data, then it will not be able to regenerate the same proof within the allotted time. Or alternatively, you can think of it as the prover will have to, and some constructions do not have this sequential time property, but the prover will have to expend a large computational, a large amount of computational work in order to pass the online challenge if it's not storing the data, which incurs some kind of time-space trade-off. And I'll talk about that in a moment when we talk about what it means for a proof of space to be secure. So first and formally, how tight is a proof of space? What do I mean by tight? Well, how much space can an adversarial prover save and still pass the protocol, right? Can the adversarial prover, say, pass with only 1 minus epsilon gigabyte of data? And the answer should be no for epsilon, or 1 minus epsilon, excuse me, as close to 1 as possible, and closer to 1 would be tighter. It should be able to save as little data as possible. So in terms of defining security for a proof of space, the strongest notion would be this parallel security, which says that, so the proof of space is epsilon tight if any online prover who stores less than 1 minus epsilon gigabytes in this interactive protocol will fail to respond within the time limit t, except with negligible probability. And typically we need t to be large, so t would be proportional to the storage size. And the tighter the proof is, well, that would mean that 1 minus epsilon is as close to 1 as possible. A weaker notion, which I just mentioned, was a time-space trade-off. And let's say this proof of space is not parallel secure, so it means that the online prover could actually pass within the allotted time the protocol while storing less than 1 minus epsilon gigabytes of data, but then the prover would have to still do a very large amount of work proportional to the storage size. So that's a weaker notion. And a weaker, even weaker notion yet would be a time-space trade-off where there isn't this kind of threshold where if the prover has to do a tremendous amount of work if it stores even less than 1 minus epsilon times the data, but rather that there's some kind of equation that gives a time-space trade-off where the required persistent storage would be something like, if S is the total storage and T is the total work, then you have S to the K times T would be greater than 1 minus epsilon N to the K. And this last notion of security can never be too tight because you could set S to be less than 1 minus epsilon N and T would still be kind of constant. So what would I call a, quote, tight proof of space? Well, one that's arbitrarily tight, meaning that I can tune the protocol parameters for any given constant epsilon less than 1 so that it is an epsilon type proof of space. Meaning I can tune the parameters of the protocol so that, you know, if I want to make sure the adversary can't even save a 1% of the data or a 0.01% of the data, I can tune the protocol parameters so that that's the case. And when I tune the protocol parameters in this way, I want to make sure that I'm not compromising on efficiency. So a tight proof of space construction would maintain efficiency even as epsilon is made arbitrarily small, and ideally proportional to 1 over epsilon, which is kind of the best you can do. If you make epsilon smaller, you do have to increase the communication or the proof size. But the best that you can get is proportional to 1 over epsilon. And that's actually what this work achieves. It achieves tight proofs of space that are the ideal tight proof of space. So before this work, what was sort of the scope of proofs of space? Well, there were no provably tight proofs of space. So the original proof of space was proposed in 2015, and that had a 1 minus epsilon of less than 1 over 512. Again, heuristically, maybe the protocol was more secure, but this is just in terms of what we could prove about the protocol. And we can't prove that the adversary is not storing more than a 1 over 512 fraction of the data. So it could save a lot of data. It's saving, it's only storing 1 over 512 gigabytes in that previous example. Then Ren and Devadas for 2016 moved this closer to 1. And in their protocol, you can only prove that that 1 minus epsilon is less than 1/2. And that's like a theoretical upper bound, but even the protocol becomes impractical at 1 minus epsilon is equal to 1/3, meaning that you cannot really practically have practical parameters and then prove that the adversary is storing more than 1/3 of the data. And then 2017, every year things get slightly different. But so this is actually the proof of space that Chia is using, and that has improvements in other regards. But it's even worse in terms of how tight it is. It uses the weakest notion of proof of space, which has the time-space trade-off, and theoretically it cannot be a tight proof of space. 1 minus epsilon has to be even less than like 1 over log n asymptotically. And then Pietrzak from just this past year had sort of the first tight proof of space, which I would call quasi-tight because the proof size increases proportional to 1 over epsilon squared, which makes makes the parameters or the proof size blow up quite significantly as epsilon becomes small. And moreover, well, I mean, this is, so from a theoretical perspective, it is tight, just not, it doesn't maintain efficiency proportional to 1 over epsilon, which is the ideal. But second, we don't really have any practical instantiation of that construction since it requires a very, very special type of depth robust graph. And I'll talk about what depth robust graphs are later since this work uses them as well. But it requires a very special type of DRG that we don't really have practical instantiations of even heuristically or experimentally. So why does tight proof of space matter? Well, first of all, we get better provable security for proof of space, and if we're, say, basing, blockchain systems or, any kind of Sybil resistance mechanism on proof of space, you want it to be provably tight. You want to know that the bounds are really tight on how much space the prover is actually using. There isn't a large difference between different adversaries with different strategies. But another reason, and sort of the motivation for this work, was that it's actually necessary for this other thing called proof of replication. And proof of replication, you can think of it as a useful proof of space. So what do I mean by that? Well, let's say that instead of just storing a lot of data, the prover, or say the miner, is encoding a movie on its disk, a specific movie that, say, a client would be interested in. You're saying, I'm storing The Lord of the Rings HD on my 10 gigabyte hard drive. And then they go through the dance of the protocol, and there's a challenge and a proof. Just the exact same characteristics of a proof of space, yet the verifier is convinced somehow that the prover is storing not only a lot of data, but like a specific piece of interesting data. Well, it turns out, though, that you can't really achieve this perfectly cryptographically, and the best possible security that you can achieve for this is some notion of rational security, and what I call epsilon rational security, which means that the adversary cannot save more than an epsilon fraction by not replicating the specific movie. In other words, the miner is saying, well, gee, I can't save more than just an epsilon gigabyte by not storing The Lord of the Rings, so I might as well store The Lord of the Rings. Now, you may notice a connection to tight proof of space, if something is epsilon rational secure, it means that you can't even save even an epsilon amount of storage, which means that the proof of space, or the proof of replication as the proof of space, is tight, right, for a small epsilon. And in fact, these notions are kind of equivalent. So in order to construct this proof of replication protocol that's epsilon rational secure, you need a tight proof of space. And in fact, if you have a construction of tight proofs of space, you can use that to construct an epsilon rational secure proof of replication. So they're equivalent notions. However, they're equivalent notions from the perspective of security. There's an extra consideration you might want when you're talking about doing a proof of replication as opposed to a proof of space, which is, well, this is interesting data I might want to actually extract. So, well, the verifier says, I'm tired just verifying proofs. I want my darn movie, right? So, okay, just wait for me to extract it from my POREP encoding. And then after some time, the prover will be able to actually extract the movie and send it to the verifier. Because the prover's not actually storing the movie, it's storing some kind of fancy encoding of the movie that allows it to do this proof. So a POREP with inefficient extraction can be built from any type proof of space, as I mentioned, but a POREP with efficient extraction is harder. Now, one more thing, a POREP with efficient extraction is kind of a double-edged sword, because efficient extraction also means that the proof of replication is not asynchronously composable. And what do I mean by that? I mean that, well, let me illustrate to you what a sort of a attack is. Well, if the prover is kind of producing different proofs over time for independent movies and claiming to use storage to store both of these movies, then if the verifier is not privy to the actual movie that's the prover is storing and is just verifying proofs of space, then what the prover can do is basically generate the encoding of the first file and then use the output of that as sort of the input to the next proof of space. And by this property of efficient extraction, the prover only needs to store the data that it's using for the second proof of replication and can efficiently extract from it the data that it needs to pass the first proof of replication protocol. So it kind of stores only half the data. I mean, this is prevented by focusing just on protocols where the prover commits to the total amount of storage or total amount of files that it's going to store at one period of time, and then the security would hold, right? So the way that you could use this in a system if you want efficient data extraction is to make the prover commit to all the movies that it wants to store at one instant in time, and then have to sort of every, say, epoch or period, make them, reinitialize all the movies that they want to store at any given point in time, and then challenge them on those. If you allow the prover to lazily claim or add committed movies over time, then you can't have both security and efficient extraction, which has serious practical implications. All right, so let's skip over to how we actually construct these things. And what I'll start with is sort of a basic technique that is sort of the basis of most proof of space constructions. When I mentioned that you're storing basically some kind of specially encoded data, well, the way that this is done in proofs of space is by basically labeling the nodes of a graph, okay? And so say every label is like a 32-byte label, so you have, let's say you have n labels overall for the total amount of storage of 32n bytes, then you're going to derive some kind of special label on every single node of the graph. And how do we label the graph? Well, specifically, it's going to be a directed acyclic graph. And what we're going to use for the labeling is a collision-resistant hash function that's going to be salted by the ID for the proof, so that if you wanted to do this for two different proofs, they would be completely independent. So let me walk you through how the labeling works in this simple example of just 5 nodes. So the first label is derived just as the hash of 1, the number 1. And then the next label will be derived as a hash of, well, its input index 2, but also any labels that it depends on, meaning that labels that belong to nodes which are direct parents of this particular node. So in this case, it's C1. So C2 would be the hash of both 2 and the label on node 1. And so on and so forth. 3 would hash in 3, but also the labels C1 and C2. And C4 would hash in 4, and then C3 and C1, its parents. And 5 would hash in 5, and then C4 and C1. And so what you kind of get is this dependency of labels down the road on previous labels. So it forces you to kind of do this sequential work in order to derive the labeling. And that will be important for why these things actually end up being secure. And in other words, why when you delete some or forget some of the labels, you will forcibly have to do a lot of sequential work in order to rederive them. So how do you use this labeling inside the proof of space framework we developed before? Well, I'm storing a gigabyte. You send a commitment to the graph labels that you've derived, and then you basically get a challenge set chosen from the labels. You open the labels of the nodes in the challenge set and their parents, and then the verifier checks that all these hash relationships between the labels on nodes in S and their parents were correctly derived. So another main tool that we will use is something called a depth robust graph. So a depth robust graph is a graph, a directed acyclic graph on n nodes, but it has a special property. And the special property is that any node, I'm picking sort of an arbitrary number here just to illustrate it. There's sort of more general ways of defining them, but I'm going to say that a depth robust graph is a graph where if you delete or look at a subset of 80% of the graph, so you delete only, say, 20% of the graph, and you keep the 80%, then the remaining 80% of nodes contains a long path. And what do I mean by long? I mean basically, proportional to n, right? So at least 1 minus delta times n. It's going to contain a long path. And in illustration, basically, I said I delete 20%, and the remaining number of nodes contain a long path, which are basically linear in the number of remaining nodes. And you can visually look at it like this. If I were to delete, say, the nodes in here, C4, C3 and C6, then sort of the other nodes still contain a long path of edges. And the reason this is going to be useful is because if you have to recompute the labels along a path, it requires sort of sequential work. So the next, So the building block for sort of the type proof of space that we're going to develop in the next few slides is basically a proof of space that's just based on this idea of a depth robust graph alone. And this was actually something that it was joint work with Joe Bonneau, and I presented it last year at BPACE 2018, and we were using it for a proof of replication. And there, you're just labeling a depth robust graph. And why does this immediately give you some kind of proof of space? Well, if the prover deletes 80% of the labels, right, then it will have to do a large, since the 80% of the labels it deleted contains a long path, it'll have to do a lot of sequential hashing in order to rederive those labels if challenged. To produce those labels in an online challenge phase. okay? But this isn't a very tight proof of space because it basically allows the prover to delete 80% of the data. So we're going to try to do something better. So the next tool that we're going to use is something called a bipartite expander graph. An alpha-beta bipartite expander graph, it has two sets, what we call the sources and the sinks. And the node set A of sinks and the node set B of sources, there's edges from B to A, directed edges, and any alpha fraction of A is connected to at least a beta fraction of B, okay? And we call these expander graphs when B is noticeably larger than A, meaning that if you look at the total number of nodes that are connected to this beta is noticeably bigger than alpha. So there's an expansion factor of beta over alpha if there's beta nodes in B that are connected to any alpha nodes in A. And so what we're going to do is we're going to kind of combine these two different graph tools together. We're going to stack depth-robust graphs where in every layer of n nodes, you put the edges of a depth-robust graph that satisfy this kind of minimal condition of being, depth-robust if you look at an 80% subset of the nodes. And then use bipartite expander edges to kind of connect the layers. And then finally, we apply the method I described earlier of labeling a graph to derive labels on the final layer, and we only store the labels on the last level as the proof of space storage. So let me try to give you some intuition of why this achieves a tighter security than just the depth-robust graph. Well, if I were to delete, let's say, some fraction of the labels on the last level, okay, then maybe it wouldn't take me if that was the only level that I had, then it wouldn't take me that long to rederive them because it's just a small fraction of the labels, and I have all the other labels which they depend on. But now, if I delete these, in order to rederive them, I actually needed labels on the previous level too, which I, in this example here, I have not actually stored. And the dependencies keep on expanding and blowing up with every level because we're using this expander graph. And so finally, on the first level, where we have the edges of a depth-robust graph, you basically have to rederive almost all the nodes, and since deriving almost all the nodes requires a lot of sequential work due to the depth-robustness property, you have basically a proof of space. Now, of course, when we want to prove that this is a proof of space, we can't assume that the adversary is only storing nodes, labels on the last level. We could allow it to store labels sprinkled throughout the layers, but we're able to prove that if the total storage that the adversary is using is, just less than 1 minus epsilon n, then we'll be able to find some blow up of dependencies on the things that he's missing. Okay? And so how do we kind of use this now just to build a generic proof of replication? Well, you take the labels on the last level and you just use it as basically a one-time sort of encryption pad, and you XOR it with your movie data file, and then you get an encoded movie data file. But extraction in this kind of very generic construction of a proof of replication is inefficient. It requires you to rederive the deterministic labels on the last level in order to decode your movie. So how could we maybe build something which has efficient data extraction? Given the caveats I said before about composability, we still may be interested in doing this. So we're going to start with kind of the same construction, but tweak it a bit. We're kind of absorb the expander edges between the levels, okay, into the layers, so that between the layers there's only just one edge between nodes. A node in a given layer does not have a direct dependency on many nodes in the previous layer. It just has an edge from the node at the same index in the prior level. and the edges or dependencies that were there before are kind of absorbed into extra dependencies within the same level. And then we reverse the direction of the edges on every level. And I'll explain in a moment the intuition for why we're doing that. But first, how this works is so the dashed edges basically correspond or indicate where you would XOR the prior level label with a key derived from the parents on the next level. So for an example, C6, the label C6 would be C1 XOR the hash ID of these labels C7, C8, and C9. And now, basically by XORing, if we start with the data on the first level, we're basically deriving some kind of encoding of the labels so that each label encodes the same index label on the previous level. And then the final level of nodes, the final level contains sort of an encoding of the data inputs. And the data can be extracted efficiently by reversing this process. And when we reverse this process, it can be completely parallelized, and so it's much faster. So why do we still have this property of a proof of space? Well, if you look at, say, let's say we do the same thing, we forget one of the labels. Now, let's consider both its targets in this level and also its dependencies. If we move to the level right before, the targets of this node sort of become the dependencies of the node on the previous level. So in order to rederive this label C14, we needed still to have the label C9 because C14 encodes C9. It's the XOR of C9. But in order to rederive C9, we need C10, which was, part of the target set of C14 in the last level. So the targets become dependencies of the nodes we need to rederive on the previous level, and the dependencies become targets. And they keep on switching, and the dependencies end up growing. Why? Because the way that we chose these edges that we absorbed into the levels came from this expander graph construction, and the expander graph construction has this expansion property, which now applies to the size of the targets plus the dependencies. So the size of the targets plus dependencies of any deleted set of labels kind of inherits this expansion property. So that's sort of very high-level intuition, but it's the whole kind of analysis is in the paper, which is online, and there's a lot more sort of details to think through in proving security. So in summary, what you end up with is kind of log. You need log of 1 over epsilon total number of levels, but the node degree in each level is just based on this 80% depth or less graph. It's independent of epsilon. You don't need to increase the number of edges in each level when you change the parameter of the tightness of the proof of space. You only need to increase the number of levels proportional to log of 1 over epsilon. So what you end up with is a proof size of d over epsilon times log of 1 over epsilon. Now, there's actually a further optimization, because I promised initially that we just get the ideal increase in proof size of 1 over epsilon, not 1 over epsilon times log 1 over epsilon. And the further optimization is you basically taper the number of challenges or labels that you need to open in each level as you go up higher in the graph. And I won't go into the details of why that's still okay, but you end up even removing from the proof size the factor log of 1 over epsilon. You just have something which is a constant times the degree over epsilon. So in conclusion, we have constructed basically the first provably tight and proof of space with practical parameters, which is necessary for proof of replication. There's lots of details and performance optimizations left out and room for improvement. In fact, I've been working with the Filecoin folks all year, and they've implemented this construction as the basis of the Filecoin mining protocol, and we've been taking this construction and sort of trying to optimize its performance and make the proof sizes as small as possible. And it turns out that this even benefits from the accumulators that other work that Benedict and I and Dan did, that Benedict talked about yesterday, which are useful for making these proofs even smaller. So thank you very much.
Thanks, Ben. I guess we can take 1 or 2 questions before the lightning talks.
Hi, thank you very much for
Sure.
this talk. I have 2 questions. So T is very finicky. I'm very curious to know what research you've done to establish a very clearly weighted T.
The time T.
Yes.
Yeah. Well, the time T actually isn't that finicky. The time T is we know what the time T is based on the parameters of the construction. Will be provably sort of linear in the number of nodes, in the graph. So it is possible to tune T further by basically adding making the hash function slower. In fact, one thing that we can do is use a verifiable delay function, or just an asymmetric an asymmetric function that's slow in one direction and fast in the other, so that we don't compromise on the efficiency of data extraction, but we can slow down T even further. But basically, the number of sequential hashes that you need to do if you delete some of the data, we can bound that, and that's going to be basically proportional to the number of nodes in the graph.
Well, to complete that question, my concern was more from a security perspective. How is that to prevent a manipulation of T to forge a proof? I mean, how did you? I mean, we're talking space.
Yeah.
So
So there isn't manipulation of T. What we do is, so basically we say that in order to, what we would say is the concrete security of this proof of space construction is that if the adversary deletes 1% of the data, then they'll have to do at least they'll have to compute, let's say, at least something which is order of n hashes in order to rederive the data, and actually has to compute them sequentially. So basically what you get is a minimum time that the adversary would need to spend in order to pass the protocol if they deleted too much data.
Okay, thank you. Next question. So when you say space, if we imagine a long distance of thinly distributed matter versus a small very condensed matter, can you define space in proof of space a little more accurately? I mean, I haven't read the paper. I'm sure I don't know if there's
right. So space is defined sort of in the computer science notion, or at least the theoretical notion. It just refers to the total number of basically of bytes of data that you're storing.
Okay, so it's very simple.
Yeah.
Okay, thank you very much.
Hi, thank you for the great presentation. I had a point about error correcting codes.
Okay.
The expander graph construction and the zigzag graph construction reminds me of the LDPC and turbo codes. Where in an error correcting code, you want that if one block is missing, like an erasure, or is just in error, a lot of dependencies break.
Yep.
So that evolution from expander to the zigzag is very similar. It seems very similar to a turbo code, where you have one pass and then you interleave and have a backward pass, and this creates, their
yes, yeah. Expander graphs are used to build error correcting codes, in fact. So that's a good observation.
Okay, so it's in parallel. Another question about the interactive proof.
Yes.
Whether it's susceptible to DDoS, or if my connection in the context of Filecoin or in a blockchain, if the prover or the connection between the verifier and prover gets DDoSed, because it relies on a time bound for you to respond.
Right. Yeah.
Would that be a problem?
Yeah, that's a very good point. In an interactive version of this protocol, you would have to consider that. somebody trying to sabotage the prover by preventing them from responding quickly. It also is one reason to consider trying to make the protocol as non-interactive as possible, and even the online phase you can try to make non-interactive by deriving the challenges according to basically a random beacon instead of sort of a non-interactive random beacon, which people are building using things called verifiable delay functions or other techniques or distributed randomness generation. And so making the proof of space as non-interactive as possible would be good for that reason. And in fact, Filecoin's pursuing that direction.
Great, so let's thank Ben again and move on to lightning talks.
Okay, it's not a, oh, okay. Okay, so next up we have the lightning session. So first of all, Philip, if you could come forward, please. Great, so the way this is gonna work, there's gonna be 2 minutes per talk. 2 minutes, that's all you get. So I'm gonna start a timer when you start speaking. And if you go over 2 minutes, I'm just gonna ask the audience to thank you, and they're gonna start applauding, and then you're going to leave. So before each speaker, we'll have the name and then the next speaker. So if your name is Albert Chan, you should probably come up to the front too so that you're ready to go as soon as Philip is done. And with that being said, our first speaker is Philip.
Yes, hello, thank you for having me. I would like to present my project briefly. We're trying to make the blockchain ecosystem in general more accessible. So what we have at the moment, many different protocols, many different contract languages, they aren't portable. The vision that we have is like a uniform operating system. So think of a terminal where you can log in with your user, you have a user folder, and all this happens like in a standard POSIX environment. This is the far goal that we have been pursuing, and the structure we have come to is a data structure. It's not about the protocol, but it's about the structure, and all the proofs that we're doing is related to this structure. It's a heap, so it merges, the protocol itself merges ideas of proof of work, proof of stake. A property of the protocol is you can add a work once and then use it at a later time as stake. The advantage of this is that we don't need an application layer in order to redeem stake. This makes the protocol simple. And thing we achieve is a very low-level protocol which combines like functionalities of reputation systems, prediction markets, and consent systems in one simple protocol. The blocks are 5 tuples, so it's really not very complex. The operations are in constant time, and the algorithm, in order to insert and get data out of our block heap, I forgot what I was to say. And yeah, the final goal that can be achieved for this is like a one standard API where you can start from different machines. It's completely decoupled from the application layer. We can use JavaScript, we can use bare machine code, and the security is ensured by the protocol itself. One effect that we like very much, and which was like a goal of us, is that based on this system where blocks are assigned and where identities exist, we can implement a universal basic income very easily. And we are currently implementing the reference implementation. The paper will be finished like within 14 days. You can check the name out, and I'm happy for you to attending me. Thank you.
Great, that was about exactly 2 minutes, so let's thank Philip. And Next up, we have Albert and Ashley, if you could be ready, please.
Hello, everyone. I'm Albert Chan, and I'm the CTO of Injective Protocol. So we are building a fully decentralized and front-running proof DEX, which enables trustless liquidity sharing. Now, the way this works is that we match and execute trades on a layer 2 sidechain, which prevents front-running using verifiable delay functions, or VDFs. So the nodes on our sidechain aggregate orders per block and then submit them to 0x for actual settlement. They also serve as relayers, which also share liquidity in a trustless fashion. So this, of course, allows for more liquidity, more efficient spreads, and a better DEX experience. Now, to go into a bit more detail about how we prevent front running, I'll walk through a simplified example of a trading scenario where 2 traders submit the same order at 2 different times. Now, suppose at the beginning of block 1, taker A sees an order from the order book and wants to take the order. So he begins computing a VDF time proof on top of a hash of the order, and then continues to submit it until the end of block 2. Now, suppose later on, taker B decides he wants to take the same order. So he begins computing a VDF time proof and also submits it to the sidechain. At the end of the block, the sidechain will then determine the correct sequence of orders based off the VDF time proof length, where orders with longer time proofs are prioritized first. Now, since the front runner can't create a longer time proof, he won't be able to beat taker A from taking the order. Now, for time purposes, this is a very simplified model of how our protocol works, but we also use commit reveal, both interactive and non-interactive, and prevent against grinding attacks, and we also plan to integrate VDF ASICs in the future. Thank you.
Okay, thanks, Albert. That was a great demonstration that you don't have to use all 2 minutes. Ashley.
Hi, everyone. My name is Ashley Landquist. I work at the World Economic Forum on our blockchain and distributed ledger technology team there, which is located in San Francisco, which is the tech headquarters of the forum. Previously, I was at UC Berkeley and blockchain at Berkeley. I thought I'd share with you a project that we're running at the forum, which is trying to use Ethereum and smart contracts to reduce corruption in the public procurement process. So public procurement is actually the largest source of government corruption in the world. About $2 trillion is diverted annually from global taxpayer funds and development aid to line the pockets of corrupt officials. So what we're trying to do is develop a pilot, and it's in partnership with the government of Colombia and with the Inter-American Development Bank. And we'll run this pilot over the summer in a live procurement process. We're specifically designing this in a public permissioned Ethereum environment where citizens and journalists and the public can review a procurement process after it happens to evaluate and sniff out any fishy activity and hold the participants accountable. But the participants in the system are in permissioned nodes, and they're the vendors, the bidding agency, and the government. So we're trying to see if the censorship resistance, transparency, and automated smart contract functionality of Ethereum and smart contracts can help with the situation in procurement. On the left, you'll see a bunch of locations where corruption tends to happen in the procurement process. So we're specifically designing to solve for some of these. And we're operating in a very multi-party process where we have a lot of support from technical experts like QuantStamp and from academic experts and economists to support this as well and design the best solution that we can. Thank you.
Very much. Okay, so next up we have Pedro and then Stefan.
Hello, my name is Pedro Moreno Sanchez, and if you ask me, actually, I'm really surprised by the amount of advances and different challenges that appeared in the last 6 months. So I'm pretty sure that in the next 6 months, there will be many other technologies and many other things happening. So if you really want to know about them, I have the solution. So it's the International Blockchain Summer School that we are preparing in Vienna. So it will happen in September, the first week of September. Vienna has been chosen as the most livable city during the last 7 or 8 years in a row. So if you have never been, you should actually definitely think to come. And if you really want to learn about blockchain technologies and the security and privacy of them, we are preparing an excellent lineup of speakers that will tell us about the cutting-edge research of security and privacy problems, blockchain and distributed ledger technology, as well as we have keynotes and hackathons from the leading companies in this area. This thing is being organized by leading researchers like Matteo Maffei from Tübingen, Edgar Weipel from SBA Research, Kevin Borgolte from Princeton, Martina Lindorfer for Tübingen, and yeah, myself as well. In order to organize that, obviously we need sponsors. For that, we offer a couple of different packages. We can offer you to talk in the main program if you are interested. You can also host a practical session in which you can show your technology and teach the students and the attendees how the technology works, and obviously speak with them and have social interactions with them. These are only some proposals, so if you have some other proposal, please talk to me. We have many other choices. And yeah, if you're interested, here's the website, contact in this email, and you can contact me also in this Twitter handle. Thank you very much.
Thanks, Pedro. So Stefan, and then actually Adam is not here, he told me, so sorry to spoiler alert, but Emily, if you could be ready after Stefan.
Hey everyone, I'm Stefan. I'm the systems architect at Numerai, and what I'm going to talk about is libsubmarine. So libsubmarine is an implementation of submarine sends, which is a framework for preventing transaction reordering attacks on Ethereum. Those attacks can affect stuff like front running. And this library allows anyone to do things like seal bid auctions and temporarily hiding transactions on Ethereum. So the way that it's implemented is quite similar to a traditional commit reveal, except that the commitment is hidden by a large anonymity set. And so there's kind of this anonymity attached to the commitment that the miners are not able to observe. This implementation is standardized kind of in the same approach as an Open Zeppelin library, and you can find it by looking at libsubmarine.org. There's both a on-chain and off-chain component to it where you have to generate a proof off-chain and then submit it along with the reveal, but all that is already figured out and is ready to be implemented in your project. Thank you.
Thanks a lot. Okay, so Emily, we'll have you go now. Too bad we missed that. That looked like a lot of fun. And then Carl will be next.
Great, thank you. Hi, everyone. Are we, okay, so hi, my name is Emily Pillmore, and I am a Haskell engineer with Cadena. I am also the lead maintainer of the Pact smart contract language, which is a Turing incomplete, formally verified language targeting the Cadena stack. So today we'd like to announce the fact that we've actually incorporated the notion of theorem proving with interfaces. So sort of like your Java style or your Solidity style interface. But you can actually specify the laws that you would like the functions that you're going to ask people to implement directly in the interface itself. So for instance, you can say things like, my transfer function should be mass conserving. We want the amount credited to the receiver to be the amount debited from the sender. This is not a common thing that you get just by specifying the function signatures for a given function. You need additional structure in order to enforce this. And what we want to leave you with here after this lightning talk is the question of, what do we want people to implement, and what do we want to enforce as invariants of the programs that we write on the blockchain? So for instance, if I want every balance to be greater than or equal to 0, I can do this with a type, or I can write a model that satisfies that all balances in my contract are greater than or equal to 0, or greater than 0. Or I can talk about custom escrow behaviors where, after so many steps, certain invariants must hold, or relationships between functions and the data, like sending X many dollars to you and you sending them to me means nothing happened. Or proportions of funds that go to owners and stakeholders in some contract, according to some distribution that you write. So for instance, just as a sort of low-hanging example that you can all think about, blackjack. It has rules. You can talk about anteing must be greater than 0. At each round, a user can bet greater than or equal to $0. If you hit 21, you win, and so on. You don't want people rewriting this code every time someone needs to implement the blackjack contract. So you can extract this and throw these in the interface as models that each of the functions must satisfy. For instance, a round function must satisfy that betting has greater than or equal to 0 bet, for instance. So if we don't have this, we lead to mass code duplication and pollution. And this helps us reuse the code that we write, maintain a standard for contracts written on our blockchains, and more importantly, enforces trust so that you don't have to know who to trust. You simply know that the contract that you're implementing satisfies these laws. Thanks.
Yeah, great. Thank you, Emily. So we have Carl, and then Ram will be next.
Hello, hello. I'm Carl. I'm an Ethereum researcher. And last time I was here, I was talking about the release of the hybrid Casper testnet and all the trials and tribulations therein. And so a lot has changed over the past year, but one thing remains the same. I'm back again talking about a testnet release. And so I'm happy to announce that the Plasma testnet that we've been working on, myself, Kelvin, Ben, Jing, for the past 2 months, day and night, we've been creating a Plasma implementation for the community, by the community, that you can play with, and it is a lot of fun. And so what is Plasma? This implementation includes not only a easy to deploy operator and get started, at least on my computer it's like 5 minutes, and it also includes a specification, so please read it up and tell me what's wrong with it. It is amazing. It is way too long, and I want you to read every bit of it. And so the final, the Plasma implementation is, what is Plasma in the first place? Well, my God, I'm a little nervous. This lightning talk, I'm not used to this pace. Anyway, what is Plasma? Really quick. Okay, Plasma is essentially a framework for deploying scalable blockchains that are actually secure, and the security is based on a root chain commitment, and that a commitment is an accumulator with the Merkle tree. I had more to say than I could, but please do check out this Plasma implementation. It is a testnet. It is for you to play with. It is real because we need more real things, and we also need more, people with their eyes looking at the protocols, because my goodness, this is a hard protocol, and research is hard, and my goodness, please, Plasma group. Oh yeah, I forgot. Plasma.group for all of this. Plasma.group.
Thank you. I think we need more lightning talks with that energy level, for sure. Okay, so we have Ram, and then followed by EJ.
Good afternoon, everybody. I'm Ram Golambudi from ZAG Protocol. So we started actually looking to solve a business problem for many of our customers and enterprises. Right? Most of them want to actually adopt a public chain, but they had two key considerations. While they said, one, they needed transactions to be confidential, source, destination, and value, because they didn't want their competitors to know who they're transacting with often. Second, they wanted smart contracts. And when we looked around in terms of the current blockchains available, public chains, you either had Ethereum, Stellar, wonderful projects, but they handle privacy off-chain, or you have privacy coins like Zcash, Monero, which have limited scripting and smart contract facilities. So that's where we said, okay, can we solve it in a more integrated fashion? So that's where ZAG protocol origin is. Our approach, our proposal is to have a blockchain which tracks both account balances and UTXOs, very similar to having a wallet where you have your debit card and also cash, and give an ability for the user to move money between his account balances and UTXOs freely, publicly validated. Third is whenever he wants to do an anonymous transactions, use node commitments and zero knowledge proofs to actually do anonymous transactions. All again, using zero knowledge proofs get validated across all the nodes. This gives the flexibility for developers because now there's an integrated chain where they can do both private and public transactions with smart contracts.
Thank you very much. Ooh, okay, so after EJ, we have RZ345.
Hi, my name is EJ Zhang. I'm an associate professor at the University of San Francisco. I'm totally channeling Carl here with the speed of my speech. This is a joint work with Jean-Philippe Martin, or JP Martin, known for bar fault tolerance, Byzantine altruistic and rational user tolerance. And the image credit goes to Amhayan. All right, so I want to talk about the gatekeeping attack, and the attack is the existing block producers prevent a new user from becoming a new block producer. And how do they do it? Every proof of stake-based system is asking a new user to make a deposit to a special smart contract or account so that their deposit can be flushed if they misbehave somehow. If the deposit transaction never goes into the canonical block, then the new user cannot become a new block producer. And as block producers, they have a right to do so in some sense because there's essentially no penalty for ignoring a transaction and just leaving it in the pending transaction pool. And why would they do that? If they foresee that their expected block reward is going to diminish when there are more block producers, this is a rational behavior. And when do their block reward expectation goes down? Let's say it's a turn-based consensus algorithm or turn-based block producing, then having more block producers mean that it's going to take longer time for me to get my turn. And if it's like a probabilistic choice, proportional to the stake amount, by having a newcomer in, having more stake in total reduces my probability of being chosen as a block producer. So gatekeeping attack is real if it's not well managed, and this is also rational behavior, meaning that it's very difficult unless you make it incentive compatible. So how do we prevent this attack? You have to have a penalty for ignoring a transaction, but how do you impose a penalty if your network is not reliable and/or asynchronous? And even if you can actually impose a penalty, how much penalty is enough? If the block reward is infinite amount that they can earn for the infinite amount of time, then essentially what you're doing is that by reducing the probability of being chosen or increasing the time to become a new block, to make a next block, your penalty has to be actually almost infinite. So this is a very difficult problem to solve in asynchronous network and make it incentive compatible. And I'm just going to plug in that this is a new consensus protocol that we're designing to make this attack not so feasible. And if you're interested, I'd be happy to talk.
Thanks very much. Okay, RZ. Okay, last call for RZ. So could we have Phil then, please? Phil, is Phil Chen here? Okay, moving right along. Leftharios, I know he's here. And after Lef, we'll have Elaine. Maybe those were just really lightning talk.
Okay, so I'm here to talk about data management. And I think we all know that right now our data are just hoarded in a data center and are used without our knowledge to do stuff like sway elections and other kind of things. And when we move into the blockchain land, we see some applications that use the word blockchain as magic, like voting on the blockchain or using genomics on the blockchain or storing health records on the blockchain to do stuff. And if you try to actually implement these kinds of protocols, you're going to see that they have the problem that you have to put some data transparently on the chain, and that is not very privacy preserving. So I'm here to talk about a system called Calypso that we have built, where our goal is to create data management under Byzantine adversaries. And the basic idea is that we use some flavors of verifiable secret sharing, and we combine that with blockchain technology to get properties like enabling data owners to share their data, but at the same time be able to maintain control over them. Meaning that if at some point I want to revoke my data, I can just do it. I don't lose them once I put them on chain. I also get a guarantee that I can audit the chain and make sure that I know exactly who accessed my data. So if my data is leaked, I know who to blame, or I know if I can claim payment for someone using my data. And we can actually use all of this cool system while being able to manage our identities in a decentralized way. As a result, there is no actual trusted third party in the system. And if that's not enough, we have other cool applications that can use Calypso. Other than data management, we can build secure decentralized lotteries that don't need any collateral. We can build exchanges that don't need to do order book matching in a centralized way. Or we can do systems like secure drop where you whistle blow in case you do not, in case you have some data and someone kills you, and the Calypso is guaranteed to actually give the data away. Thanks.
Thank you, right on time. Okay, so here's Elaine, and after Elaine, we'll have Alex.
All right. I would have liked to talk about this yesterday in my 30-minute slot, but I would have really worried this would have taken 1 minute, and I wouldn't have known what to do for the remaining 29. So here's a fully functional distributed consensus protocol from scratch. Imagine messages get delivered in 1 second, and every epoch is 2 seconds. In the first second of the epoch, a proposer proposes a block extending the freshest notarized chain it has seen. In the second of the epoch, I vote on the proposal I've received. If the proposal satisfies certain nice properties, you only need to check 2 very natural properties. Number 1, the proposed block extends from a parent that has already been notarized. Number 2, the parent cannot be too stale. It must be reasonably fresh. Okay, when the block gains votes from majority people, it becomes notarized. Notarized doesn't mean final, so what is final? If at any point of time, I see some fully notarized chain ending at 6 consecutive epochs, and I haven't seen any conflicting notarization at these 6 epochs, I will chop off the trailing 5 blocks, and the prefix is final. So that's the protocol. We can prove that it secures against minority corruption in a synchronous model. And with a couple more touches, we can achieve optimistic responsiveness and the robustness property called best possible partition tolerance, which I introduced yesterday. Okay, so I just want to say, okay, distributed consensus, say yes to simple, say no to complicated. Propose, vote, boom, 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 confirm, confirm, confirm. Remember the name of this protocol, it's called Pili. Pili means the sound of thunder in Chinese. Thank you.
All right, thank you. So Alex, and then we'll have Yifan after Alex.
Hi, I'm Alex Lebet. I'm founder of Stable Unit. With my friend James Key in collaboration with Beam team, we made a prototype of Ethereum Mimble-Wimble bridge, like almost finished. So it's able to convert any ERC-20 assets from Ethereum into privacy representation of Mimble-Wimble. It has several real-world applications, for example, for stable coins adoptions. If business accept DAI as a payment method, because it's public, it's the same as showing competitors list of your clients, or if you use DAI as a user, it's same as a posting credit card history in a social network, which might be undesirable. So how does it work? If you have a 15 DAI, for instance, you deposit in a special smart contract piggy bank. And when you do it, you specify additional information to show you ownership of these funds in Mimble-Wimble. In Mimble-Wimble chain, verifiers, there are no slides, sorry. Verifiers have access to the state of a smart contract on Ethereum, and once for a while added into UTXO set these 15 privacy DAI, and you can spend it, receive it, do whatever you want, and if you would like ERC-20 tokens back, you just burn it by depositing in a special like 0 address and show proof of burn into piggy bank and get ERC-20 tokens back. Despite simplicity, it has several very interesting properties and advantages. First of all, like Mimble-Wimble is awesome, and you can use all wallets and DEXs and future infrastructure stuff which we're gonna build with minor improvements. And also it's very, very cheap in terms of a gas in comparison with ZK Snark's proof implementation, like Aztec, for example, like order of magnitude cheaper, and you pay it only twice while you convert it into privacy and while you cash out. If you would like to learn more, just approach me here in conference or find stable unit in a Telegram. I'll happy to answer all questions. Thank you.
Thank you. There were slides, apparently. Okay, so Yifan, and then we have Rylan next.
Okay, cool. You can just look at me. You don't need to read my slide. So hi, I'm Ifan. I'm from Mohawk blockchain. So at Mohawk, what we try to build is a new blockchain where the architect will be like you have one mother chain at the top, and then you can have a bunch of subchains at the bottom. And ideally, we want every DAPP deployed to one of the subchains. And sometimes they can even deploy to multiple subchains if their business logic needs. And one thing we try to achieve with cross-chain IPC is that very often those DAPPs are kind of isolated within that one subchain, so they don't talk to each other. But that's something that we really try to encourage people to do. So that's the rationale behind cross-chain IPC. So that in the future, those DAPPs, you can imagine those subchains, they will form these kind of like a mesh network where those smart contracts deploy on different subchains that can just calling each other across the chains in terms of sending transactions to each other. And so to facilitate that, I'm currently working on this project called Cross-Chain IPC, where you can see I have a list of the engineering challenges for us. For example, like how do we routing those cross-chain transactions correctly and efficiently? And also, should we validate those transactions as the same as a transaction from a real person, a account? Or how we do nonce, should be nonce be do like differently comparing to a nonce for a account? Or like at last, like those transactions, they are from chains. So if A chain sends transaction to B chain, then who's gonna pay for those costs that executing those transactions on chain B? All these kind of things. And we have some ideas about how we're gonna implement this. And currently, I'm working on a experimental implementation of cross-chain IPC on blockchain to tackle all these challenges. And I know those ideas are not perfect, so if you are interested in the topic, please come to talk to me offline, and I'll be very happy to talk to you. Of course, you can also send an email to my email address, basically my name at mohawk.io. Thanks.
Okay, thanks again. Rylan, I have to correct me on that, and then Lisa.
Yeah, that's a wrong spelling, so that's why we need error correcting code, right? So my name is Roland, so I'm the co-founder of IoTEX, which is a startup here, working on the scalable and privacy-centric blockchain for Internet of Things. So there is like one very concrete research problem we face actually when doing this IoT apps. So the problem is like how a blockchain could authenticate its state to a client. Like the client is so lightweight, we call it like the lightest client. It has no previous states of the blockchain. Also, it has very limited computation resource, storage resource, networking resource. How would you do that efficiently with low cost and also in real time, right? So that's a very very typical research challenge. So to overcome this issue, like we design a crypto protocol, we call it a B4R, meaning like a place for reward. So the intuition behind this is pretty simple. So we give like the full nodes in the network a new role. Basically, they generate a place for blocks. So for blocks and states. So basically, place is like a new succinct proof to us testing certain amount of effort has been spent on certain type of data. That means like this can be constructed using VDF, using password hashing, and also using some even hash function, for example. And then this place will broadcast in the network. The latest client will pick up these places and try to verify if this is correct, and also assess the effort behind all these places, right? Collected efforts. So if they are certain about like basically like the more effort it has been spent on this data associated with, the more trust like the client can put into the data. So that's how this client authenticates these block states. So there would be like a very interesting problem would be like how would you make this ethical or maybe hardware resistancy. So that's why we also introduce like crypto agility into this design, which means like the blades can be generated by different constructions, different like password hashing function, even like a VDFs. So also we introduced a concept called like a scarcity when it comes to assessing like how effective and also how much effort it has been put into that blades. So like the full paper will be released soon, I guess probably next month or even like in a few weeks, and we'll be happy to talk more about details. You can find me anywhere. All right, thank you.
Thank you. Okay, so we have Lisa and then Aniket.
Cool. Hello, my name is Lisa. What I'd like to do is walk you through an alternative way of looking at zero-knowledge proofs. But in order to do that, first we need to go through a quick primer on the nature of reality. So first, we live in a multiverse. Physicists will recognize this as the many worlds interpretation of quantum results. From this, experiments in reality becomes the process of locating the nature of reality that you currently inhabit of all possible. I'll say that again. Of all possible realities, which do you presently inhabit? So the nature of existence, then, is the process of fixing or discovering the particular nature of your reality. There are a number of ways to fix the reality that you exist in, two of them being observation and time. Okay, so what does this have to do with zero-knowledge proofs? I'm so glad you asked. So let's consider a range proof for a single bit. It's the construction of two values such that you can prove that you know the discrete log of one of them. In other words, the existence of such a proof fixes our reality to one of two options. And the proof is a commitment to one of the two in this set of possible realities. So it is possible to observe this reality via the revelation of the blinding key. An outside observer can verify that we exist in the reality where either of these statements is true. However, only a person with the blinding key knows for certain the actual nature of the reality that we presently exist in. Thus, the crafting of zero-knowledge proofs is a practice of obfuscating the observability of the nature of our present reality while fixing it definitively via a bounded set. So in another way, a zero-knowledge proof is like a Schrodinger's cat, with the caveat that selected parties are privy to knowing the cat's fate, and the rest of us are not. Thank you.
Okay, Aniket is here, and then Shashank.
Hello, everybody. My name is Aniket Kate. I generally work on different things in privacy with blockchain, but today I'm going to talk about one particular topic which is very close to my heart, that is credit networks. So you might have heard about companies like Ripple and Stellar, or maybe a project like Trustline Networks, where the idea is we can build such networks of a graph of IOU links between different networks and perform transaction that goes from one node to somewhere else through such transitive links. And they provide different values which go beyond payment channels because we can create depth links and other things. So they have been found to be useful, and Ripple and Stellar IOU networks demonstrate that there is a huge value in this space. But through our research, we try to ask questions and try to bust some myths in that case, in the sense that one of the key things that we want to study and demonstrate that we don't require any kind of tokens in such credit network systems, and they could be built in a completely distributed manner. So as one of the intermediate experience, what we did is that can we build such a system on Ethereum and have a complete contract which is ready and built, and all the transaction value cost that's going to occur are just basically the gas value that we observe in that space. And we did that. It did not require any token. It's just gas values for Ethereum implementation could be implemented and scaled for the second layer solution. And what we observed that these are the values from maybe I think November or something like that, that indeed if we just rely strictly on the gas values in Ethereum, the values for most of the things which are decided by that value are significantly lower, even for things like just path-based transactions as they happen on Ripple as compared to as they happen on our Ethereum-based smart contract. The values are not huge difference, and we don't decide them. We just let the market decide that, and we find this to be a nice, thoughtful experience. More to know about what we did, our contracts, as well as information about what research we do, go to the transitivenetworks.com. And I want to end my talk by saying that, in fact, even for such a credit network, implementation based on such Ethereum or any such blockchain is not necessary. Such systems could be built just purely having two-phase commits, or what we can call as local consensus. If you are interested in this space, come and talk to me afterwards. Thanks a lot.
Thank you. Okay, last two speakers will be Shashank and then Remco.
All right, hello. Yeah, hi. I'm going to take maybe like a minute and a half. Just quickly, we were originally trying to build essentially a decentralized high-frequency derivatives platform. And when we started building that a couple of years back, we realized that building it on the Ethereum network was very impractical. And the impracticality came from multiple things, including scalability, the costs attached, the high frequency, and so on and so forth. So we segued into essentially trying to build a layer 2 solution and didn't want to reinvent the wheel, so we took where Plasma was and started building on top of that. So we have a version of Plasma called Gluon Plasma, which has been out there on the E3 search community, and we've received some fantastic feedback from people on that. And we have a testnet running with this Gluon Plasma version for the last 3 months, and we're ready to go mainnet pretty soon. The idea of this version of Plasma is based on an account-based model as opposed to UTXO-based model. But it does build on most of the things that Plasma Cache, Plasma MVP, and a bunch of other Plasma variants have done. So it's not completely fresh. It just kind of improves on that and adds a few additional things. It is provably secure. There are things that are in our paper. I don't have enough time to talk about it. I think there were a couple of slides, but don't worry about it. You can just maybe Google for leverage Gluon Plasma, or just go to E3 search and look for Gluon Plasma. You'll probably find the links. And then last but not the least, we'll be open sourcing it in the next few days with the implementation, with the code. And we'd love to get feedback. All the feedback we received so far is fantastic. That's how we've been able to improve. We'd love to hear more. And folks who are interested in Plasma and the Plasma community, I would love to talk to you folks during this conference as well. I know that many of you are here. I've spoken to some of you, and many more of you are interested in this space. So find me, and we can have a good chat there. Okay. Thank you.
Okay, keep it going. Remco will be our final speaker.
Hi, I'm Remco, and I have a polynomial. I'll prove to you that it has degree at most n. First, I generate a large set of x coordinates, and I evaluate the polynomial on this set. Now I create a Merkle tree of these points and give you the Merkle root. If you interpolate these points, you can see that, that the degree is as I claim. However, this set is large. Now let's look at a fun property of polynomials. If I negate the variable, this is as if I negate every odd coefficient. If I sum it back to the original polynomial, I've effectively filtered out all the odd coefficients, and I'm left with the even ones. With a little bit of algebraic manipulation, I can use this to create a linear combination of the odd and even coefficients. So now you give me a random value beta. And I do this coefficient folding to create a p prime where the new coefficients are a linear combination of the old coefficients. However, the degree of the polynomial is now half. Another thing to observe is that I've only used values that were already in the set of points that I committed to. So now I have a new set of points that I can commit to with a new Merkle tree, and I can give you this commitment again, and we're back to where we started. So we can repeat this process, halving the degree at each step, until we're left with a constant, and I can just give you the constant straight away. This works for a set of x coordinates such that when x is in the set, the negation is also in the set, and this is closed in the squaring. This set is the roots of unity, the same as you use in the fast Fourier transform. Now, you have all these Merkle roots that I committed to, and you know the betas that you gave me. You can now point check different points of this, this set of value of these points, check the computations, and convince yourself that I did them correctly. The Frey theorem will tell you that you need actually very little of these point checks in order to convince yourself that my polynomial is indeed of degree at most n. Thank you.
Okay, that's it. So it's now officially lunch. Thanks everybody who stuck in here, and I believe we're back on at 2 p.m.
Hey everyone, we are about to get started with the next session. So if you could wrap up your conversations, find your way to a seat. If you are going to keep on talking, I would ask that you make your way to the hallway. And we'll get going in just a minute or two. All right, everyone, welcome back from lunch. We're going to get going with session 8. I am your session chair. My name is Jeremy Rubin. You'll hear more from me later in the next session. To start off, we're going to have a really excellent talk from Martin Lundfall. He currently works at MakerDAO, and he does formal verification of contracts executing on the EVM. So I'm going to invite him up to tell you more about formal verification and the road to complete security of smart contracts. All right, round of applause for Martin as he makes his way to the stage.
Thank you, everyone. It's exciting to be here speaking about formal verification. The road to complete security of smart contracts is a very sensationalist title. So I'll spend the first couple of minutes sort of making a huge disclaimer on how this can only really be interpreted as either a very long and winding road or a very narrow sense in which the complete security is actually achieved. But there is still a sense of completeness, and that's one of the aspects that I want to focus particularly on this talk. But as a start, I would just like to sort of set the context in which we're doing formal verification and the sort of assurances that one can reasonably expect from this type of procedure. And to do that, I would like to organize various assurances that we can have, not only of smart contracts, but of dApps generally, into a little bit of a taxonomy that involves at least four categories or 4 flavors of things that you might want to protect yourself against. But first, let me just say a little bit about what formal verification is. Might not come as a surprise, but it is the process of specifying and verifying the behavior of programs. And so that's 2 aspects. So the first one is specification, which is writing specs. That's a mathematical description of the intended program behavior. And once you have a specification, you can proceed with the act of verification, which is something that has the following type signature. It takes the operational semantics of the language in which you're writing your program, and it takes the specification of what you intend that program to do. And then if they happen to actually conform, if the implementation matches the specification, you can produce a proof that this is indeed the case. And this is what is being done when you do formal verification. So yeah, let me talk about these 4 different flavors of assurances, or sort of problem categories that can exist in a decentralized application. To me, I like to think of them as being, the first one is really the parts that might be most common to formal verification as it is being done in other fields. It's really just looking at the bytecode. You know, if it's in the case of the Ethereum virtual machine, we'll look at the EVM bytecode, and we compare that with a specification that we have written in some higher level language or some mathematical description of what we intend this EVM bytecode to do, and then we can verify that it actually matches the specification. And so generally what we're talking about there is what can happen during the course of one transaction. And the second one is a little bit related to the first one, but we're talking about system invariance, and now we're not considering only what can happen over the course of one transaction, but what can happen over the course of many transactions, and in particular which system invariants or DApp invariants are being are actually in place in this set of contracts. And then there comes the really sort of nasty categories that we can't really, that are really hard and open-ended. So the first one of the sort of difficult categories, I would just call like blockchain-specific flavored assurances or problems that we might encounter. And this is a really open-ended category like Eclipse attacks, minor front-running or front-running by other actors, if your DApp is safe to chain reorderings, replay attacks, and all these sort of things. I mean, in many cases, you can provide assurances against them once you know, once you've actually thought of what they are and how they might present a problem to your particular DApp. Like if you want to protect against replay attacks, then you know, it might be very easy once you've done the specification to actually see that your contract is safe against this sort of attack. But to provide a formal method by which you can exhaustively check against all of these possible things that can go wrong with an application in the distributed setting, I think that's very difficult and very hard to make formal tools to do for you. And the last category is incentive reasoning, or sort of the game theory behind your application, and to make sure that the incentives that you expect the different actors in the system to act according to are actually well-founded in the game theory of the system. So if we look at how to approach these various classes of bugs or behaviors in a formal methods sense, then I'm gonna unlock my computer. Yeah, here we go. So here's what I would say is the efficacy of formal methods to approach these various problems. For the first two, it's very effective to use formal methods, especially when we're working with a sort of intricate virtual machine as the EVM, where there's really a lot of cases to consider, and accounting for various stuff is not a very creative pursuit, but there's still a lot of cases to explore, and it's really something that you want to make a machine do and not a creative mathematician or somebody that might have a more high level, might be skilled at different tasks, let's say. And for the second type of flavor, I would also say that it's really kind of effective. Some formal methods really start with these invariants, and then of course, you know, the formal methods are very effective at proving these sort of properties. For the methods that we are using with the K framework, these invariants come out at the second stage of the whole procedure, after starting with the first one as a sort of bonus. So they're not that difficult to prove, and the overhead of doing a formal analysis of the types of proofs or reasoning that you would make is a little too high with respect to how difficult that proof is. So I would say it's kind of effective. And then the last two are really difficult to handle with formal methods. The fourth one, might have some interesting tools that can be developed. I know that there are a couple of frameworks that allow you to automatically find the Nash equilibrium of various games and stuff like that, but I haven't seen how well they could be applied to this particular use case of decentralized applications, but that would be super interesting to explore. And also there's a fifth category here that one might want to mention, which is ensuring the correctness of various cryptographic protocols that might be involved, and that's not something I'm even gonna talk about. Let's just leave that to the professionals. That's a little bit annoying. Okay, so going into depth into the first category when we speak about the verification of EVM bytecode. So for this talk, I'll mainly be speaking about the EVM, but many of the methods can be used to talk about different virtual machines as well, and I'll speak about that later. So if you remember the type signature for verification, we needed the operational semantics and the specification, and then we get the proof. So here's the operational semantics. The operational semantics of the Ethereum virtual machines, the Ethereum virtual machine has been defined in the K framework, which is a very nice framework for analyzing and designing and specifying programming languages and virtual machines using rewriting logic. And so the K specification of the EVM is also known as KEVM, or the Jello paper, and it's like an executable version of the yellow paper that passes the complete VM test and the general state tests. So it also discovered some faults in the tests, some operations of the VM that weren't touched by the test. So it also expanded on what the tests were actually meant to do. And the beauty of K is that it's a very general framework that after you've defined a language in it, you automatically get these a suite of tools that you can use for analyzing that programming language. So already by having defined the virtual machine of Ethereum in K, you get a debugger and a symbolic execution engine and a prover and all these things. And so for our work, we're using the verification engine, which takes the following form. So K, as I said, is based on rewriting theory. And in rewriting theory, you usually deal with rewrites, and proofs also look similar to the rewrites of the programming language. So a reachability claim, which is sort of the nature of a specification, really, when you write it in K, takes the following form. You have this little rewrite arrow that looks like the implications arrow, and you say that S and then some condition on S and leads to S prime, and then some possible condition on S prime, or some property of S prime. And the way to understand this is that any pre-state S in big S, and now the reason why you can sort of speak about both small s and big S here is because you can abstract as many properties as you would like in big S. So we can think of big S as really a set and then a particular instantiation of a state that conforms to that more abstract version of the state would be a small s, being in big S. So any pre-state S in big S satisfying P of S will evaluate to a post-state S prime in S big S prime such that P prime of S prime holds. And then the proving engine is kind of simple in the sense that it just starts at this particular state and symbolically explores all of the possible paths of execution. And it either makes sure that all of the states that are being reached are conforming to the post state, or it tells you that your claim is actually false, or it runs out of memory or something. And what the state is here, the whole sort of configuration that we're speaking about, is the whole state of Ethereum, which is a large state. And when we want to prove properties of smart contracts, we usually want to, start with one contract and not talk about the whole blockchain entirely. So here comes the part of the whole process that DAPA MakerDAO that we've really added to this whole process, which is in making sure that this process goes a little bit smoother. Because if you're trying to write your reachability claims directly in K, they will be large and unwieldy. And just to convince you of that, here's a slide of how large and unwieldy it is. I would actually need a couple of more slides to fit the complete specification claim of what this little token transfer is actually doing. So let's look at how we would write the same claim instead. Here's a simple token contract. And we want to verify that the transfer function of this smart contract does what we intended to do, which is to increase the balance of the receiver and decrease the balance of the sender by the amount that we want to transfer. So what you see on your left here is our specification format that we have developed that we call ACT, which is really abstracting away all of the parts of a K-reachability proof that are sort of boilerplate and not that interesting to the particular method that you want to prove. And it's a literal specification format that we think is fairly intuitive, and so it shouldn't be requiring too much explanation to see what's going on here. I'll just say something about storage. So this is, of course, referring to the storage of the smart contract in which this is all occurring. And the dash, the vertical bar dash greater than sign is the notation for the key value storage in this contract. And then the rewrite arrow is the equals greater than sign that we saw before. So this is really just saying that the balances of the caller ID is going to move from a variable that we call fromval to fromval minus value, and the value of the balance of the receiver is going to increase by the same thing under the condition that all of the variables are not overflowing, because as you can see in the code, we have overflow safe arithmetic. And crucially, we also want to say what happens in the case where these conditions aren't being met. So when we take this ACT, we compile it to two K-reachability rules, which we call pass and one fail. And the difference between them is that we either assume the conditions in the if and only if clause to be true or false. And we say that in the fail case, the whole thing must revert, and nothing is going to be updated in that case. And then we add, if there's an if clause present, we add those conditions to both specs. And so in the fail spec, we also account for the case where we might run out of gas, but only if we run out of gas while the conditions of the if and only if clause are assumed false, which means that to really be covering the complete behavior of this method, we also need to generate two more cases, or really refine the passing case into a proper pass, and a case where you have assumed all of the cases in the if and only if clause to be true, but you don't happen to have enough gas. And the reason why we need to do this in two steps is at compile time, we of course don't know what the gas expression is going to be, but after running through the proof once, since we're really exploring all of the paths, we get an exact condition for what gas really is in a case of successful execution, and then we can refine our spec to either assume that the symbolic value that we start with in our gas cell is equal to or greater than this expression or lower than. So if there is no if header present, then these three specs, the fail spec, the out of gas pass, and the pass, are going to be exploring the complete behavior of this method. Does that make sense? Okay, so that's one part of what KLab is. So KLab is one of the tools that we have developed in order to make the verification process of Ethereum smart contracts a little more intuitive and fun even. And the second part is a debugger. So as I said, K already provides you with a proving engine that you can see whether your reachability claims holds in. But it doesn't actually give you that much feedback when you try to run these proofs. It basically outputs true or false. And that doesn't help you very much if you want to verify some smart contract to just know that your spec is actually false. So we built a command line tool interface that allows you to step through what a K proof looks like. So you're really stepping through a symbolic execution of your smart contract. And that allows you to see precisely where things go wrong. I'll speak a little bit more, I think, later about how it can be used to explore unknown bytecode also. But just to give you a little preview, I was not brave enough to do a live demo of what it looks like, but here's just a screenshot that looks a lot like any Ethereum debugger, only that now you should notice that on the stack we have some symbolic values and not concrete instantiations. And we're also at a branching point, so we're able to explore multiple branches of execution by working with this little graphical interface. You know, we have hotkeys for exploring the state that the execution space of this method, really. Okay, so here's a little interlude from the formal verification side of things. I believe I was also asked to talk a little bit about how to write smart contracts so that they're safe and in particular provable. And here comes in a lot of opinion of how to write contracts. This is opinion that has been formed from, of course, writing many smart contracts and working with it for a long time, but also looking at the formal verification process and see how you can make smart contracts as safe as possible. And so the first one I shouldn't even have to mention, you know, keep code modular and as simple as possible, but no simpler than that. So the other points might be more interesting. If you're writing contracts that are going to be deployed on Ethereum, at least for now, for better or for worse, you're going to be working with the EVM. And even if you write your contracts in Solidity, the EVM is going to be what matters. So you should be thinking in EVM code when you're writing your implementation. Not at the design stage, then you should be thinking, you know, in whatever sort of paradigms that makes the most sense to you. You should be exploring many different ways of expressing what your contract should do and what your dApp should do. But when it comes to actually implementing that behavior in EVM bytecode, you should be thinking about EVM bytecode. The next point is a very opinionated thing, but I'm going to still propose it quite hard, which is that your methods, which is what I call the functions of your contract, they should do one thing under the right conditions, and if those conditions aren't being met, then it should revert. And this is getting back again to how we write acts and how we write the specification of our functions. You know, in almost all of our specs, we don't have this if clause. We only have an if and only if clause, which means that we only have to write one spec per method, and then we make sure that we have actually explored the complete behavior of that method. So if your methods don't do this already, then maybe rewrite them so that they do. Otherwise, you can just write more specs, but that isn't really the ideology that we subscribe to. Avoid calls to unknown code as much as possible. There's a lot of people that disagree with this point, but really, if you want to have strong guarantees about what your contract should do, then it's good if you know what the code of that contract is doing, because it's very hard to say anything about random code. And also, this relates to the point that you should be thinking in EVM code as well, which is even if your contract may look really sleek if you use a lot of libraries and stuff like that, it hides a lot of complexity, sweeps a lot of complexity under the rug, and you should be thinking about the bytecode and not the Solidity code. And this slide is just to scare you, I think, of the fact that I'm really urging you to not write complex contracts because contracts are complex enough as it is. This is a sketch of what multi-collateral DAI might look like, the various contracts involved. And this is actually as simple as possible, and it's still fairly complex, so we don't need extra complexity, so try to be simple. Okay, so the interlude is over. Let's go back to exhaustiveness and really what I mean by complete security of smart contracts. As I said, once we have written specifications for methods and we have made sure that we account for all of the possible cases, which in the best scenario is just one case, then we really have an exhaustive specification of the behavior of that method. And if we have that for all of our contracts, then we have a complete specification of the behavior of that contract. So if we do this for all of the contracts in our dApp, then we've essentially defined the behavior of that dApp. So the sort of non-standard models that I'm speaking about here is borrowing the metaphor of the standard models of arithmetic. After defining the axioms that make up arithmetic, you can also explore what models can satisfy those axioms in the same way that you can explore what bytecode satisfies the standard axioms that your specifications make up. And this gives you an indicator of how much coverage your specification and verification process really covers. Because if you actually do this spec exhaustive well enough and you have complete description of the contract behavior, then essentially you should be protected against adversarial code. And by that I mean if some code is written so that it matches your specs, then it should be as good as any code, and you should be willing to deploy that code as your application. Now, of course, there are some reservations there when it comes to gas, but the way that we write specs, we have abstracted this away, so it should really be as good as any code. So you think of the canonical implementation as the standard model of your dApp, and then consider the non-standard model of your dApp as any bytecode that somebody will use. And so this is something that we've been working towards continuously when we're doing a formal verification work to really make sure that everything is exhaustive. And the ultimate test that we can make to make sure that they are is what I call a reverse bug bounty. And so that would be a process by which we ask for people to submit bytecode that passes our specs but still is faulty in some way. And now faulty is a little bit hard to define because our specs is essentially defining what is not faulty. But if there's still something that we have missed, then that would be great to know. So this would be like a bug bounty for our verification process, but it's really asking people to write buggy code instead of finding bugs in our code. Yeah, and when you have exhaustiveness, you can also do gas optimization. Let's see how I'm doing on time. It's pretty much up, so I'll only skim through system invariance. This is like the second flavor of assurances that you might ask for. And really, as I said, some people take this as the sort of primitive that they first try to verify the invariance of your contract code. But if you have this complete specification, you can essentially reduce the whole complexity of what your dApp is from this bytecode to the specification. Essentially, you can think of the specification as defining the atomic rewrites of a relatively small state machine. And now if you want to have higher level guarantees, then you can only reason about this a relatively small state machine. And then proving these invariants is fairly simple. You just think of what may happen during the course of the lifetime of your contract as a list of calls, and then you can, by induction, prove that these invariants hold for these various calls. Here's a couple of invariants in the MakerDAO system that I don't have too much time to talk about. Let's just look at the one fundamental equation of die. It's kind of nice. Okay. So here's some things that we want to do in the future. Some particular point that I'm excited about is WASM support. We're currently, as of very recently, starting to work harder on doing a K specification of WebAssembly, and that's really going to be one of the first steps into having formal verification of smart contracts that compile to WebAssembly when that gets deployed. So I'm really excited about that. Oh, let me just say something about this exploration that I hinted at before. So what you can do once you have these reachability rules and this symbolic execution is that you can essentially write a reachability claim where the post state, so the right-hand side of the rule, is something that you're never really going to reach. And the prover is still going to operate in the same way. It's going to start at your pre-state and explore all of the possible paths. And until it reaches the end of the execution, it's going to tell you that your proof is wrong. But that doesn't really matter because we're interested in what the actual proofs, what the proof did explore, so the paths that we went through. Because if we have some unknown bytecode, for example, this is going to allow us to investigate the behavior of this contract and reverse engineer it or see what it does, really, from a symbolic point of view, which is a very interesting thing, I think. Yeah, and I think I'm out of time. Here are some resources. Thank you very much.
Thank you very much. We have time for maybe one quick question. If anybody is dying to ask something, just raise your hand. All right, we got one over there.
Okay, hi. So I had a question about, let's see. Okay, so Rice's theorem states that all non-trivial semantic properties of a program are undecidable in a Turing-complete language. Mm-hmm. So how do you actually formally verify a Turing-complete language like the EVM bytecode or Solidity? And aren't these reachability relations just accessibility relations, which are only valid in the Turing incomplete subset?
Yeah, so that's a good question. First of all, we do have the notion of gas, and for any finite value of gas, the execution is actually going to halt in the Ethereum virtual machine. So whether you think of it as being Turing complete or not is a matter of interpretation. But also, when it comes to verifying applications, we're always verifying a very particular subset and a program written in a Turing-complete language, and so that doesn't have to be Turing-complete at all. It just has to do the things that we ask this program to do. So we're not really verifying the EVM as much as we're verifying an application written in the EVM. And then there are techniques of proving properties of code that contains loops, and the process is known as co-induction. And it's quite an interesting thing. But there you actually do have the property that when you do a proof with co-induction, you're proving that either the code loops forever or it exits in this particular state that you have specified. But for the Ethereum virtual machine, we still have the notion of gas, so everything is relatively finite. And that is to say that it is finite.
All right, let's thank our speaker once again. Thanks, Martin.
Yeah. What do I do? Can you plug it? Okay, and then you can type slideshow here or something.
Yeah, I think it should come up.
Can you do slideshow here? On the
Yeah.
thing? Maybe there is a slideshow here.
It's just right here. From beginning.
Yeah, hopefully.
Is that good?
Something, yeah.
Yeah.
All right.
All right, our next speaker comes to us all the way from Tel Aviv University. He's working on a project called Sir Torah. Please give a warm welcome to Muli Sagiv.
Thank you very much. Thank you very much. I'm excited to be here. I'm going to talk about a new baby company which was established just in November, but it's actually leverages a lot of research that me and my colleagues have been done in the last 30 years, and I also acknowledge generous funding that we received from the European Foundation. Also I would like to acknowledge the team. I have not done anything here. That's the R&D team in Israel, in the company, Shelly Grossman, Marcelo Taube, and Sagi Katz. They developed these tools, which I will be able to demonstrate for you, and actually you can use it. It's a tool for formal verification. So what is formal verification? Formal verification is a technology which accepts two inputs. It accepts the, this doesn't work, but it accepts the contract on one hand, and it accepts the requirement on the other hand. And formal verification can do two things for you. One thing that you've seen in the last talk, which is very interesting, that formal verification can produce a proof that it's correct. But the other thing, which is equally interesting, and in some cases more interesting, it can reveal bugs. It can reveal subtle bugs of your system. And you will see that our tool actually produced for you a concrete execution, not just symbolic, that demonstrate the bugs that happen. So smart contract, it's a domain that really needs formal verification, and I'm sure I don't need to convince you that in this audience, but it's important to understand that because we think that code is the law, so if we have a buggy code, we have a buggy law, and in some sense it makes the situation worse than it happened before the blockchain. And another problem that happens, since we are in a decentralized world, actually once you identify a bug, it's a race to mitigate and actually find out, look, it's not like in a centralized session. So what happens if you find a bug, it's really hard to mitigate this bug. And what we do with formal verification, we really look for bugs. And we can identify subtle bugs, like we enter this bug, hijacking bugs. We can identify these bugs with formal verification. And also, as you have seen in Martin's talk, we can show their absence. We can do both of these things. And that's very interesting in this domain. So since I come from this domain, I would like to point out to you something that some of you are aware of, but not all of you are aware of, that formal verification in the last 20 years actually have made a lot of progress despite the difficult problems. And one area where it was very fruitful is the domain of verification of device driver. How many of you knows about the verification of the device driver? Maybe you raise your hand. It sounds like few of you know. So what is the case of device driver? The issue is that Microsoft Corporation, they actually allow third party to actually produce their own device driver. So they write device driver, and these device driver, they interact with the operating system. So this means that if you have a bug in your device driver, it can actually crash the operating system. So you've probably seen it if you are old enough. You have seen these kind of things. You have seen this blue screen. Maybe they are not as bad as stealing your money, but they're still devastating. And in fact, the last few years, we are seeing fewer of those. And part of the reason, believe it or not, is formal verification. And what happened? The Microsoft research team has actually taken a huge effort, which actually also followed by the University of Berkeley and others, and incorporated many techniques, including my own algorithm for my postdoc. But the idea there is that you take rules. These are correctness rules. These are rules that says that every time you take a driver, you actually
every time you acquire a lock, you release it. So these are some of correctness rules for the driver. And basically what happened is that the Microsoft team, they developed this very, very nice algorithm, and this algorithm is fully automatic. The user is not aware of anything. The user only has to write the slick rules. It's a fully automatic method. And this method, it's true, the problem is very hard. We heard about the Rice theorem and others, but in fact, these algorithms solve it on C programs. You write your C program, you download it, you check this thing, and basically the tool either gives you an error or it actually shows you that the program obeys these rules. And this is a very nice quote from Bill Gates about this technology. I hope you can read it from the back, hopefully. But basically what it says is that this area of formal verification, which has been the holy grail of computer science, in fact, the Microsoft Corporation developed this technology which can be useful of program of medium size. And that's a very nice technique. And what we are trying to do in this company is doing something which is inspired by that for the blockchain. We are trying to build this automatic technology that can reason about your code, either prove properties or find you automatically bugs. And one of the things which is not very clear for people in program verification, I should say, my background is academic, but I spent like 3 or 4 years in IBM, and that shaped my whole thinking. And one of the things they told us in IBM that there are no such things as obstacles. There are only challenges. So in program verification, there are actually 2 challenges. One challenge is the technological, but the other challenge, which is equally interesting, is the challenge of the specification. How do you specify the right behavior? Okay? And what do you mean? How do you specify the right behavior for contracts? How do we know which contract is correct and which contract is not correct? And this is somehow analogous to the Microsoft device driver rules. And in the Microsoft driver rules, I do not know if you are familiar with, these are all informal rules. But in fact, we need to have some kind of rules that say what is a correct smart contract. So in this talk, I'm going to focus on the first one. I'm only going to talk about the specification. I will talk a little bit, I will tell you about our technology, and of course, the articles based on our technology are all public domain. But I will focus mainly on the problem of specifying the correctness. How do you even say that the contract is correct? Okay. So I will talk about 2 kinds of properties that are interesting for smart contracts. And both are interesting. The first one are generic properties. So what do we mean by generic properties? This is something which is known in this community, and it comes in different domains. The idea is that we want to have some correctness property that will be fulfilled by all contracts. So it means if your contract do not fulfill it, you actually don't want to deploy this contract. And the question is, what are these properties for smart contract? The second thing that I will talk about are properties which are specific to a use case. For example, suppose you are building a stable coin or you are building an ERC-20, what are the properties that you want to satisfy there? So let's go into the re-entrancy attack. We have heard about it many, many times. You have someone depositing your money, you deposit some coins, and then later on somebody else deposits the coin, and then all of a sudden the thief comes, he or she deposits a little money, and then it all depletes all your money. That's not a good thing, and we would like to prevent it. This is a kind of problem that we would like to prevent. And in fact, interestingly, we can prevent this, and we can prevent it in all contracts. So what is the idea? The idea is, in fact, that we want to avoid this kind of situation. And the interesting thing is that some of these situations, for example, today, they are avoided in the EVM by the guards. But that's not a good idea. We have seen it in the Constantinople, because it means that when you upgrade your EVM, you're going to have these bugs coming. So you want to prevent these kind of bugs. And what we do in the company, we have a method which we actually enforce, that we check that each contract obeys this property. And if this contract violates this property, we will produce a bug for you. And if your contract obeys this property, we can actually prove to you that this kind of bug cannot happen. And it also has another interesting thing that says that your code is somewhat isolated from the code that you are invoking. So it gives you this nice software property. And the property that we enforce, maybe I cannot sort of explain it in details here, but the idea is that, in fact, we enforce something which is very similar to what happened in the database. It's the idea of atomicity. So what happened? You see that I have the blue contract, and the blue contract executes occasionally, and then there's a purple contract, and then there is the green contract. So basically, in the Ethereum, they can all run separately. But in fact, the system is showing that there exists an equivalent execution in which they all occur continuously. So this is something that our tool enforces. It enforces the fact that all of the contracts, they appear as atomic. Even if they are not atomic, you, as a programmer, you can think about them as atomic. So this gives you some kind of criteria for correctness. And we can prove that statically, before the code is executed. Or we can identify the bugs for you. So that's the first thing that we do. That's good. That's generic. But as we know, generic properties are not the end. We need to, in order to get the good benefit of the verification, we need to reason about many things. And that's what we are doing with this. We have a method to define, we have a language for defining the properties of the contract. And we call it the contract vulnerability language. It's a language that we are currently designing. It is publicly available. And it actually allows us to express the property that we care about, like ERC20, like properties of a money market, or other properties. And this is a language that defines the property that we care about. And we are hoping to define this language as a joint effort with the community. And the interesting thing about this language is that it's reusable in the sense that one contract, one CVL actually covers many contracts. So when you write this one CVL, for example, we have this one CVL that covers all the properties in the ERC20. And now we are developing another one for 721 and so on. So basically we have a language and we have the ability to write reusable specification. Another property of it is it's verifiable. And we think about it as some kind of a system test, in a sense that you check the interactions between your contract. I'll give you some examples. It will be a bit technical, but hopefully you will get at least the feeling of what we are doing. So before I go to this, I'm not able to point. So before I go to that, I want to somehow explain to you how the technology works. So you see, we have, on the right, we have the technology AEV. We have our technology. We run the compiler. We compile the smart contract into the EVM. And then what we do, the programmer or somebody else, it can be us, you write the CVL on the other side, and then basically the technology either gives you a verification report telling you the vulnerability does not exist, or it gives you the exact vulnerability and it gives you an input that shows you the vulnerability. And you notice again that somehow this is how these technologies work. It compares the smart contract according to the way you write it to the specification, to the requirement of what it means for this contract to be correct. So in the design of this language, and we should say it's a language is being currently developed, at the moment we have 3 principles, and probably we're going to add more. The first principle is generalization. The other one is mass is a law, which actually goes back to James Bjorner. And the third one is relating state, which actually takes care of the problem that Martin was telling you about. So let's see the generalization principle. The generalization is a very, very nice idea that came from verification. So here is a quiz for you. You have 2 programs in Solidity. Are these programs equivalent? You probably don't care. But these are programs that people write, and they write this kind of code. For example, they try to optimize gas, and they're trying to check that these two pieces of code are equivalent. So these are pieces in Solidity. In order to see if they are equivalent, what happened, you see, we show the CVL. Okay, we are showing the CVL here. Okay, so the first thing that you see, the first command that you see in the CVL, we havoc the first two arguments. What does it mean that we havoc the first two arguments? This looks probably weird to you. It's some kind of assumption that we say, we don't know what's these values. We want to actually verify this under arbitrary scenario. Okay, it's like kind of we havoc the value. And then you see that we actually execute the first, we call the first function, we call foo, and then we call the second function, we call bar. So we are basically, it's just like a test harness. We run this code. And at the end, you see that we execute a command which is called static assert. Static assert is like the Solidity assert, but it's executed statically. Okay, so it means that it's going to be checked on all execution passes. And basically, it will be checked against an arbitrary value. And we can run this tool, and we ask if this is correct or not. Again, I was not brave enough to run it. So you see, this is the output of the tool. A bit hard to read now. But what happened is that the tool actually identified cases. It's identified a corner case. It basically told you that for one corner case, foo and bar are not equivalent. So it's automatically identified the error for you, and of course, we're going to make sure that you're not going to exploit it. But we can give you a contract, and we can automatically identify the error for you. Okay, for example, here is a fix, also taken from the internet. So you see people are using something like the safe bus, and you see that they are using complex logic. Again, you see the CVL, it's exactly the same kind of CVL. And I'm running the same CVL again, and here it will tell you that it automatically proved, without the help of the user, that this kind of vulnerability cannot happen. So it's actually proved that for no input, this can happen, okay? And what it essentially proves is for all the arguments, arg1, arg2, arg3, it must be the case that foo arg1, arg2, arg3 is equivalent to bar arg1, arg2, arg3. And you can identify and you can give it all kind of complicated code, and it will tell you this answer. So that's the first principle. The second principle is actually more interesting. We want to shift from the case that code is the law, because for us and for our customer, mass is the law, not the code is the law. So basically, we want the programmer to write the spec in mass. And that's, of course, something that we borrow from VDM and other cases. So you see this example. This is, again, code. And this code is actually, you see, it's a function that iterates over a list, and it basically sums the element. So what we see is that we havoc the coins. We generalize the coin. We don't care about the particular coins. And then you see that we check that the result which is produced by the code, is equivalent to the mathematical definition. Notice that on the right-hand side, we can write arbitrary mathematical definition, like you are familiar with math, sum and product and everything. And they are evaluated according to the mathematical semantics. And on the left-hand side, there is the code semantic. And by the way, again, I'm not going to check to you, but in fact, when you run it, our tool will find a bug. And our tool will find corner cases, and there are many, many corner cases. So it will find a corner case and tell you that this equivalent does not happen. So just to sort of give you another application of it, here is another example, and it's a beautiful example that came from Jeff Hayes. Jeff Hayes is the CTO of Compound. Compound Finance is a company that builds a money market. So what they do, they have a complex code. You see on the right-hand side, they have a complex code, and this complex Solidity code, it determines the new price of the shares. And basically, what they want to know is they want to guarantee to the customer that nobody will be able to steal the shares, or nobody will be able to steal the money. And the way they are doing it, of course, is by using human. So there is a human which is actually has a kind of a 24/7 that it checks this property. But in order for the human to be successful, the code must adhere to certain property. And the question is, what is the mathematical property that the code needs to adhere? So the idea is that what we want to make sure, we want to make sure that the derivative is bounded. We want to make sure that at any point of the time, there won't be a big difference in terms of the money market. So that's basically what will happen. We write this mathematical requirement. We write a mathematical requirement that says that between any 2 points of time, the price cannot change too much. And guess what? You will feed it to the tool, and the tool will identify for you a very interesting case, corner case, in which this is not the case. And you need to fix it. And once you fix it, it will tell you that it's correct. But this corner case is something that will be very, very hard for humans to identify. And this is something that the tool automatically identifies for you. Okay, so it automatically identifies this property. The third property, which is related to what Martin said in the third problem, in the context of the blockchain, the miners can do many, many things. And we want to avoid it. Hopefully, we want to avoid it when we write the contract. And in fact, Satora can help you to do that. So what happened, for example, here are two functions. And one of them, it buys something, and the other one, it sets the price. And what you want to know, for example, you start with a state, one state, then you execute F, and then you execute G, and in the same state, you can start with G, and then you execute F. And what you want to prove that these two they commute. So you want to prove that the purple state is equivalent to the brown state. And this is something that you want to mathematically prove. So once again, you see the CVL. This is the spec that we write in order to check that. So basically, we generalize the product, we generate the price, we generate the initial state, and then we check if there are two executions which start with the initial state and satisfy the property. And once again, the tool will identify a bug for you. It will identify a case that, and I'm not showing you this, but it will identify a case in which this bug occurs. So this is something that you want to write. You write this CVL, and you can check the properties that you want. And the interesting thing is that this CVL, it suffices, you notice in this case, this CVL suffices to check all the reordering. So this is what you are doing. So just to summarize, the CVL, it's allows you to ensure smart contract properties. At the moment, we are focusing on safety. It's an ongoing effort, so it means that we're probably going to add some more things into that. And we have these three design principles. And we think it's useful for verification, but it can be used for testing, it can be used for other things. And the idea is that you write this CVL, and then we check your properties. So what is the technology here? So as we say, there is a big technological effort. And what we do, we build on the fact that we are actually leveraging academic experience to build the most precise method for verification. And the interesting thing that we really don't want to have verification has been deployed, been developed and been used. But the biggest problem in verification that we avoid in our tool, we want to really give you real errors. So we want to come with zero false positive, basically zero false positive and zero false negative. It means that we're not going to give you any false bug, and also we're not going to miss bugs. And this means that our technology must be very expensive, and in fact it is. But what happened is, what helps us is the modularity. The fact that we can actually verify each of the contracts separately. So basically, this is what happened. We analyze each of the contracts separately, and again, the property of the DAO help us. So this is sort of just the core idea in the technology. So here is a demo of the tool. You see it's a web-based tool. You see that I write here the contract, I write the name. You see now I have to compile, so this is just application of the Solidity compiler. You see you get the EVM. You get the EVM. You see you cut the EVM. And then you run the EVM. You select the CVL file. You see now you select the CVL file. And you submit it. Okay, don't run it now. Okay, but you see, you check all of these vulnerabilities. So these are all the vulnerabilities of ERC20 tokens. And you see, we show you for each of the vulnerability. If it cannot happen, we actually can produce a proof that it cannot happen. And when it happens, you see we display the counterexample in terms of the input and in terms of the values that have the error. Okay, so that's it. So how are we going to do it to make it a real thing? So here we need the community. We need you. In the same way that Microsoft Device Driver, we need to understand what are the correctness rules. And this is what we are doing. It's a joint effort, what we are doing with customers and with everybody who's agreed to help. We are actually understanding the correctness requirement. And these are all public domain. These are the CVL. And we are doing it in two ways. We are doing it by formally verifying certain domains, like, for example, stablecoin, money market, ownership, all kinds of properties which are important in this domain. And we are also doing it by developing what we are called continuous verification, in the same way that Microsoft did. So if, for example, if you are deploying a contract that you did not develop, it's actually very important for you to know what properties it satisfies. And this is what we're going to do for you. So by this, we will establish trust. And so what I presented today is a language for enforcing smart contract security. And we think it's also useful for testing, but we haven't tried. There is also this core technology for verification. This is already available for our customer. Basically, they take a simple jar file where they can run this thing. And also, we are thinking of developing this freemium service, which I demonstrated, and this will be available in March. So thank you very much for your time.
Thank you very much, Muli. We now have time for a couple questions. I guess we can give it to Matsuo.
Thank you very much for the talk, sir. I would like to ask you two questions. So first is, what is the target of verification? That is okay. Relationship between the specification and code or protocol specification itself. And the second question is, how do you verify?
I didn't understand your first question.
So, what is the target of verification?
So the target
the relationship between the specification and code or the protocol specification itself?
So it's the verification of the code. Okay, we want to verify the code.
Okay, and then the other question is, so how do you verify the correctness of formalization?
So that's a great question. So we don't verify the correctness. So you're asking, how do we know that the specs that we wrote are correct? So the answer is we don't know that our specs are correct, and that's why specs are very, very difficult. And spec can be, but the interesting thing about spec, it's a joint effort. So what happened, for example, with our customer, one of the values of this spec is it's a useful thing. So this is the value of that. And also, I should say, we have actually technology that we are showing that give you some kind of sanity check for the spec. For example, if your spec is something that actually is held in a vacuous way, we can actually give you that. Because believe it or not, we also make mistakes.
Do we have any other questions? Hands? All right, thank you very much for presenting to us. Big round of applause, everyone. Our next speaker really needs no introduction. However, I am contractually obligated to deliver an intro in any case. And I'm not just trying to avoid it, to not try and pronounce his last name, which is known to be unpronounceable. But I am actually really honored today to be able to announce Peter Wheel coming to the stage to share with you his research and development, along with his collaborators, on Miniscript.
Aha,
Are
it's
you
already working.
Are you good? Set up?
I think I am.
All right, take it away.
Thanks, Jeremy. I'm Peter Welle. I work at Blockstream. I do Bitcoin things. Today I will be talking about Miniscript, which is a joint effort with some of my colleagues at Blockstream, in particular Andrew Polstra. And before I start, I want to make sure to tell you what this is not about. Despite having released a software library a while ago called Mini-Sketch with a very similar name, it is completely unrelated to this, so I hope you weren't expecting me to talk about that. This is also not about any future soft forks or research into improvements to the Bitcoin consensus layer. This is all about stuff that is ready and available today, and it is very practically focused. So let's dive into it. I'll first give you an introduction, trying to explain what problem I'm trying to solve, trying to draw your attention that this is a problem space of contracts and scripting in general that's been overlooked. Then I will design a policy language for describing things in Bitcoin script, mapping it to Bitcoin script and describing how to spend it, and then conclude and give some future work. So, introduction. At a very high level, Bitcoin script is a fork-like stack-based language with no loops and is not Turing-complete by design, and it is untyped. Bitcoin uses a UTXO model, so UTXO stands for unspent transaction output, which is a conceptually very simple model to reason about. We simply have outputs or coins. Every coin is associated with a script. That script defines the conditions under which that output can be spent, and they're always spent in their entirety. So really, the ability to spend an output in Bitcoin is finding an input that makes a particular script in this stack-based language evaluate to true. And that's it. When you can do so, you can spend your output. Unfortunately, this language is pretty hard to reason about and to use, despite being around for, well, since Bitcoin's creation 10 years ago. There really aren't all that many interesting scripts being used. Give my own reasons why that may be the case. And when thinking about script, the sort of things we want from it when designing new scripts, new policies, is something that is, of course, correct. We want to make sure that it's only spendable under the intended scenarios. We also like it to be size efficient, because size efficiency directly translates to low cost on chain. And we also want to avoid malleability, despite having upgraded to segregated witness a while ago, which removed most of the concerns of malleability or unwanted malleability in Bitcoin. There are still a few reasons why you may want to avoid it. So let's talk about some of the things that you actually can do with Bitcoin script. The most easy example would be a specific public key must sign off on spending this coin. That's what most typical addresses in Bitcoin encode, but it is not the only possibility. There's others like escrow, also known as multisig or 2 of 3 threshold, where you say person A wants to pay person B, but they don't really, and in return for which B is supposed to return some service or good, but they don't really trust each other, so they rope in a third party in escrow, C, and you say, whenever 2 out of 3 agree, the money is released. So the sender sends the money instead of directly to the receiver, sends it to a policy or a script encoding the policy of 2 of the 3 of us must agree, and then the escrow can agree to which of the 2 it goes. The nice thing about this is the escrow cannot on its own run away with the money. He at least needs to collude with one of them. You can go further and you can add conditions like 2 out of 3, but after some amount of time you only need 1 coin, say one of the coins was lost, so we have some timeout built in. A common scripts used in other constructions are HTLCs, where you have two keys and either one key and a hash pre-image is revealed, allowing a spend, or after some time, just a key can spend. And really, this seems to be what Bitcoin script can do. It is Boolean operations over keys, times, and hashes. And the language seems a bit overcomplicated for actually just being able to do this. In particular, something that I want to focus on in this talk is composability. Say you have the example of a company wants to store its funds in a 3 or 4 multi-sig construction where a number of employees or directors of the company need to sign off for spending, but one of the participants already has a fancy hardware setup construction that has a time log built in, maybe is a multi-sig of its own with a cold storage key. Why can't that setup as a whole be one of the participants of those 4? This is, this seems like a very natural thing you'd want to do. I have my one application that I am confident with protecting my own funds. Why am I forced to just stick to these number of small predefined policies? So the goal of what I'm trying to achieve here is take any policy and within that policy being able to replace any key with another policy. That's what I call composability. And that on itself is an interesting goal, but practically speaking, the hardest part is how do you let software and hardware that are designed for different policies actually interact and accomplish this. I want to point out a tool called Ivy. I think the author had his talk earlier today here. Hi. So tools like that do help you construct more complicated scripts already, but I don't think they really give you a solution for this composability problem. And when we're talking about this, you may think, well, really designing a new script is something that only happens very rarely when someone designs a new protocol on top, designs a new application on top, and so on. But if we want this composability, that is not necessarily the case anymore, and that may be something you need to do on a continuous basis. So I will start by designing a policy language to just describe the sort of things I am talking about here. So as I started off, really the primitives we have in Bitcoin are you can spend with a public key. I'm going to call that PK and write it as a function that takes a key as argument. Multi for multisig, where you say k out of n of all these keys, then time t, or a hash preimage that needs to be revealed. But as I said, the goal is to be able to replace keys with other policies, so we need an analog to the multisig construction, which I'll call a threshold construction, which is exactly the same, except the arguments are now not keys anymore, but they are sub-expressions. And I have 3 specializations for that. One is the AND construction, which is just a 2 of 2 threshold that takes 2 expressions as an argument. And 2 versions of OR. And the reason for that is the second is the asymmetric OR, whose goal is to express that the first sub-expression is much more likely to be satisfied than the second, which I'll talk about more, but we have a probability model, and this lets you do actual optimization for minimizing the cost under certain circumstances. I want to point out that nowhere here am I talking about the witnesses. So there are no signatures in this language. The preimage never appears. So it is not really something that computes anything. It is really a combinator language for designing conditions, and that's all. And this lets us choose the most efficient way of expressing how those things need to be spent at a later stage. So here are some examples of what we can do with that. PK, yeah, that's the generator of our group. I'm not going to write them all out in hex. I'm just going to use letters, but in the actual language, anytime you see a letter, you will have to actually provide a public key. So simplest version, 2 of 3 multisig is just multi-2 with 3 keys. A vault construction, which is something that after some time you can spend with 1 key, but there's another key that can always spend. HTLC can be written as an AOR of an AND and of a public key and a time, or another public key and hash. And to go back to our earlier example of the 2 of 3 setup that is part of a 3 of 4 setup, so you use the threshold construction, but the third argument is not a public key anymore, it's a multisig. I believe that this language conveys pretty much everything useful you can do with Bitcoin script today, with one maybe not all that useful exception. I can't express hash collisions, so there are some puzzle outputs in the Bitcoin chain that can be spent if you can find a collision for SHA-256, for example. That's not something I can represent, but if you are at all familiar with recent work in Bitcoin Core about output descriptors, you may notice some similarity. That's justified because I plan to treat this as an extension for the descriptor language that we use in Bitcoin Core for expressing all knowledge about how to spend a particular output. Ooh, so the next big thing is, well, how are we going to map all these policies to scripts? I'll first talk about the basic scheme, then some optimizations, and then define what I actually call mini-scripts. So the basic construction is pretty simple. You treat every sub-expression as a part of the script, a sequence of opcodes that expect its inputs, so its signature or whatever is needed from the top of the stack, and replaces it with a 0 or a 1. And obvious way of doing it is you translate a public key to just a key and a check sig. Multisig turns into check multisig. If you want to combine 2 sub-expressions, a way of doing this, run the first one, which will put a 0 or 1 on the stack. TAS on my slides, unfortunately, I didn't have space to write to alt stack there. So TAS stands for to alt stack and FAS stands for from alt stack. This is because during the execution you have access to 2 stacks, but the only thing you can do is move something from the top of one stack to the other and back. So to execute an AND, you run the first one, put the result on the alternate stack. Now you expect the input for the second one on the top, you run that one too. Now you bring the result of the previous one back and you Boolean and combine them. And analogously for OR and thresholds. Okay. Now, let's look at an example. What if I were to want a 2 of 3 multisig for a number of keys, but then also require a 4th key, D, to always sign? Following this naive execution scheme I had before, this would turn into this rather long script. And if you have looked at the semantics of script at all, this is really unnecessarily long. And The way we went about improving this is realizing that we can really execute or convert these sub-expressions using different, what I call calling conventions, about in what way does it expect inputs on the stack and how does it return them. So the original one, which takes its input from the top of the stack and puts it a 0 or 1 instead, is what I call E from expression. There's a second one that I'm introducing here is W, which stands for wrapped. And this is a version of converting to script where you expect the inputs to one below the stack. So you expect something at the top of the stack you're supposed to leave untouched. And for almost all constructions we have, the wrapped version is really the same as a normal version, but preceded with to else stack and suffixed with from else stack. This obviously accomplishes that goal, but for the simple checksig with a single key, this is overkill. We don't actually need to move to the else stack and back. You can just swap the two input arguments because you know you're only going to consume one. So what we're doing is really for every construction in our policy language, we now have two versions, an E version and a W version, and the arguments to threshold, for example, invoke the wrapped version instead, which means that we get rid of the to else stack and from else stack. Another improvement we can make is realizing that the overall script at the top must always succeed. There is no, by definition, because it will only run when you actually satisfy it. And when you have something that always succeeds, we can actually find more efficient versions of the particular code. The V version is something that always succeeds or aborts your script if it failed, but doesn't put anything on the stack. So it's often the equivalent of the verify version of certain opcodes in the Bitcoin scripting language. And if you, for example, have an AND at the top of your policy, you can really just compile it, the first argument as the V version, and then the second version as if it was at the top again. And this again lets you make more optimizations. So the result here is something significantly shorter. But we go further. Remember that I told you the policy language does not describe the actual encoding of the witnesses. So what you put on the stack we can decide later. And it turns out there's a whole bunch of ways in which you can write an OR. The one I showed you before is the parallel OR. You just run both and do a Boolean combination of the two. But this has the downside that you actually need to provide inputs for both, even knowing that only one of the two will succeed. So there's an alternative, which I'm calling a cascade OR, which is you run A, and if it succeeds, you return 1, and otherwise you run B. So this means you no longer need to provide the inputs for B if A is going to succeed. Switching, you can actually introduce an extra argument, an extra witness that tells you whether A or B is the one that is going to succeed, and now you only need to provide one. And you can go even further, where you say, I give you a value up front which tells you whether the whole expression is going to succeed at all, and if it's not going to, I'm not going to execute anything. Yep, a few more things. I told you earlier I'm trying to avoid malleability. In order to do so, the problem is if you look at the switching OR, there's really two ways of making it not succeed. I can tell you A is the one that's gonna not succeed and then give an input that does not succeed A does not satisfy A, or I can tell you B and then give an input that does not satisfy B. And this leads to a malleability because it is presumed to be easy to find inputs that don't satisfy certain conditions. So in order to solve that, we actually need to introduce yet another calling convention, which is something that does put a 1 on the stack, but can under no circumstances produce a 0. And then yet another step is, what if you have an if-then-else, which has a check-sig operator in both of the branches? It would be nice if we could move the check-sig out. So in order to deal with that, there's yet another calling convention, which instead of immediately evaluating the check-sig, actually leaves a public key on the stack with which we still expect a signature to happen. So through that convention, we can optimize here and there a few extra opcodes. And the important thing why these things matter is because different scripts have different trade-offs between how big is a satisfaction, how big is a non-satisfaction, and how big is the script size. Sometimes you can find a longer script that needs less input and so on. So depending on the probabilities that something gets executed at all and the probability that it succeeds, you may want to pick a different one. So overall, if we look at all the things we looked at, we end up with 6 calling conventions for each of the policy constructions. We ended up with 58 combinations of different execution semantics combined with different semantics, including 14 ways of expressing an OR. We had a lot of fun writing a lot more and then trying to reason about this one can never be better than this one because this script is always this much longer than that one. Anyway, the overall subset of Bitcoin script you can obtain by composing all of these 58 constructions is what we call miniscript. And it seems reasonably efficient. In particular, we did find a slightly better script using it than a handwritten one that we're using in Liquid. I don't know if we've actually adopted it yet. There's a few limitations. Due to our composability construction, certain opcodes are really not usable, in particular depth, which tells you how big the stack is. Clearly, its semantics change too dramatically when you compose things, so it is certainly possible that more efficient scripts exist that use depth, but we will not find them. And a much bigger limitation is we really have no way of doing common sub-expression elimination. I have thought about that a lot, but I have not found any generic way of dealing with this. If only there was one opcode to oproll, but in the other direction, which is suspiciously missing, and if we had that, we could do common sub-expression elimination. We also found an efficient algorithm that actually finds the most efficient miniscript given a particular policy. It is exponential in the number of nested ORs, but in practice, that's pretty usable, and I have to tell you, I am not a web designer, as you may notice. Really, this is just my C++ code converted to JavaScript for a demonstration, but so I could start by writing, for the demo here, there is a dummy public key, C, so I don't need to write a whole bunch of hex, and yeah, I will indeed tell me just use a public key and a check sig. What if you have 2 of them? There you go, we will turn it into a check sig verify plus another check sig. If you want to do something like an HTLC, or and time, let's say 1,000 blocks and a public key, or some hash h and a public key. There we go. I hope that's readable. So it does construct a relatively efficient script for that. And it also tells you all the particular version of every policy it uses. So down here I also have a reference for all the various ways of how an OR, for example, is compiled. I'm not going to go into these details, but you're free to have a look at the website. We also have a Rust implementation, and this was pretty interesting. While writing this compiler, actually we sort of ran a competition between Andrew, who wrote a Rust version, and mine, and trying to see who came up with the more efficient one. And in the end, found out that we had significant flaws in both of our constructions, and eventually converged, so that's good. Okay, so I have so far really only addressed how do we deal with constructing a script that is a composition of certain policies, but I set out to do a bit more ambitious goal. How can we now actually make different tools that are designed for different policies interact? And to explain that, I am first going to briefly mention partially signed Bitcoin transactions, or BIP 174 by Andrew Chow. It is really a key value file format with metadata, which anyone with all information you may possibly need for determining how to sign a transaction. It gives you, if necessary, the outputs being spent. It will, if it's a P2SH output, it will tell you what the script is involved. For the public keys involved, you can encode what HD key path they are derived from, so a hardware wallet can derive them on the fly or anything. And there are 6 different roles associated with PSBT implementations. There's a creator who creates a transaction template, then an updater who fills in all the necessary information, and you have multiple signers who actually have access to private keys and produce signatures, and a combiner, a finalizer that constructs the actual inputs, and an extractor which produces a full transaction. In practice, most implementations implement multiple of these roles and often simultaneously, but what I want to point out here is that in the typical PSBT workflow, it's really only the updater and the finalizer that needs to understand anything about the input scripts. This is somewhat surprising, but it does make sense because when signing, you generally care about where the money goes, not whether it was already yours. Worst case, it's not, and your signature will be invalid. So an obvious way of thinking about it is, well, we have this nice annotated policy form. We could just store that inside PSBT records. The updater who knows the script could do this, and then others can actually sign. Actually, that doesn't even seem to be necessary, because not only is our policy language composable, the subset of script is also composable. And what this means is you can actually, there's a very simple parser you can write that, given the script, can tell you the policy again. And this means that we really don't even need to add any metadata to a PSBT to enable integration with this. That's somewhat of an artificial restriction. We very much could propose as an extension for that, but overall it doesn't even seem we would gain all that much by using a non-parsable or not easily parsable script instead. So how do we imagine interaction to work? As I said, the scripts can be easily parsed back into an annotated policy, and given the annotated policy, you can figure out what subset of scripts of keys can sign, meaning you can tell PSBT, hey, these are the keys that need to sign. You can figure out what a policy does. You can also verify that a particular policy is a composition of the policy you desire with another that you don't care about, and the composition is always sound. And given the annotated policy, you can assemble a fully signed transactions from the signature. So at this point, I want to mention really how all this work came to be, and that was from a discussion among some people contributing to the Rust Bitcoin library and wondering what to do for signing. And someone was very much against a template-based signing that's like, oh, these are the few types of scripts we support, and only these are the ones that are supported. So we went on this roundabout way to design this thing, and in the end decided that really the language to describe the structure of a script can be the script itself, as long as it is within this subset that we call miniscript. Okay, so I want to conclude by saying Bitcoin script is mostly useful for simple policies, but there's a lot more possible than it is being used for. And part of this is because it's really hard to make things interact well. This sort of interaction, for example, also could over time mean letting things like a Lightning client and a multisig client trivially interact without needing to redo a lot of the protocol work, though I'm not an expert on the details here. And we can define a subset of script which can be generically signed for, which can be constructed easily, which can be analyzed easily, and as long as we don't have common sub-expressions, is reasonably efficient to work with. So I hope that makes this sort of technology more accessible. So the future work is we need to open source our implementations of the compiler and the parser. Right now, the compiled JavaScript on this site is probably not what you want to look at. It's around 0.5 megabyte. But once we clean up the code, we'll release that. We want to integrate the generic signer logic in common wallet software, which will immediately mean that it would interact with anything that supports BSBT or others. And could even mean like I have a hardware wallet that wasn't even designed for any of these things, but it will probably not give you a useful address in what is going on, but at least some of them will likely support this without needing to know. And obviously there's further optimizations. We use the relatively exhaustive approach in trying to find out all constructions, but there's obviously a whole bunch of things possible in scripts that we're not using. And maybe a bigger thing is use the things we learned from this for future improvements. Like, as I said, if only there was an op roll that rolls in the other direction, you could pre-compute a value that's going to be used multiple times and then inserted in the right position in the stack. And this is the only time I'm going to mention the other ongoing work into researching future improvements to Bitcoin's scripting language. Taproot and Mast can pretty much directly reuse the policy language. So the annotations will be different, but this should make upgradability easier as well. So you could write a policy now and presumably later it will just be translated in a different way to a future script version. Thank you.
Sorry about that. Thank you very much. We have time for questions.
Why not call a subset of subscript instead of miniscript?
So I am, I think, notoriously bad at naming things. Actually, originally I wanted to call it descript, as it's script with something removed from it, and it interacted with our work on descriptors, but people found that too confusing. I actually considered that name too, but
so because you can't reuse witness arguments in different expressions, you can't do pay to public key hash implemented within this.
Yep.
If you were to extend it, I mean, I thought that was remarkable. Definitely that. As I think you pointed out, most useful stuff you actually don't need that, and I hadn't really realized it before.
Yeah.
But
Yes.
if you extended Bitcoin script, there's more I think you could add that would, like Merkle, like if you could do Merkle proof verification things that would make it useful to reuse arguments. So is there a way to do that while still preserving the composability of the language?
I would like to hear your opinions on this. In particular about pub key hashes. So in an earlier iteration, we actually had a pub key hash construction. But if you think about it as expressing policies, the policy that a pub key hash implements is the same as the one that you do a hash at the top, but there's really no reason why you would ever want a hash inside. So, but yeah, reusing witness things. So we do have, let me see if I can show you, say the wrapped W version of the hash lock. We found that actually the most efficient and really the only way you'd want to do it, if you also want to include a guarantee that the maximum size of the pre-image is 32 bytes, because otherwise you may not be compatible across chains, is something that just takes a single argument whose size 0 refers to non-satisfaction. So there is a limited reasoning on reusing arguments in various places, but they're all encapsulated within a particular combination of, but I'm sure this can be improved.
All right, so that's about all the time we have for questions. We're about to hit a break though, so you can find Peter and ask him whatever you want to ask him if he wants to be asked.
Sure.
We'll be back here at 4:05, and I'm going to be handing it off and relinquishing my duties to Jonathan over there. So he will be taking care of you, and I will also be presenting to you. So be sure to be back in your seats at 4:05.
If you can take your seats, please, and close the doors, if you're near the doors. Thanks. So the last session for today, I'm happy to introduce Jacob Leschno, an economist at Chicago booth. He'll be talking about monopoly without monopolist, economics of the Bitcoin payment system. Go ahead.
Thank you very much. So I'm an economist, so that's out. So I'm gonna stop apologizing about this, and I'll give you let me tell you what we thought about Bitcoin and blockchain system generally, and maybe hopefully it's a slightly different perspective. So I should first say this work that I'm going to talk about is joint with two co-authors, Gur Huberman and Siamak Mualemi. Both are in Columbia Business School, where I was until last year. And we got really interested, started thinking about Bitcoin, and my perspective is a market design perspective. I usually study market design, and we got interested in that Bitcoin gives us new opportunities to how to design marketplaces. And let me just also say about the title, Monopoly Without Monopolists. By no means we want to claim that Bitcoin or any other cryptocurrency will be a monopoly, but we want to say that it will have different properties. Even if it were to be a monopoly, it will behave very differently than firms. So in order to kind of talk about this, let me first try to talk about a benchmark system, the more familiar traditional payment system. So Bitcoin enables us to send money electronically over the internet. We know how to do this for a long time now. Digital systems that allow us to transfer value has been around for a while, and they usually look something like this diagram here. There's a company that manages a system. This company decides how many servers to have, how to manage them, and users just interact with this company and provided services such as holding balances and transferring money. So what's wrong with this? So two things that an economist will tell you might be issues with this is that those companies would have pricing power. So one issue that I'm ignoring is the fact that you need to trust this company. Well, like most people trust the Bank of America account or the SWIFT account. So in practice, it seems like we somehow got over this problem. Like we trust Bank of America not to cheat on our records, for whatever reason most people do. But because we trust Bank of America, it means that I can't start Jacob's Bank now and just compete with Bank of America. I can't start a competitor to PayPal because PayPal has a network of people that use it, and it will be hard for me to start competing with it. In this kind of business, it's really hard to enter and compete, and as a result, the businesses that run those systems have pricing power. PayPal can charge me more for transacting on a PayPal, and I will still use PayPal, because nobody is in Jacob PayPal. Well, so PayPal has some pricing power. They can raise prices, and in economics, whenever a firm can raise prices, you think this is going to be socially inefficient. It could result some losses because monopolies will generally want to raise the revenue at a level that's above what would be the social optimal. Okay? Generally, not serve low willingness to pay customers or leave a lot of people unbanked. The second problem is a holdup problem that when a company can't commit, it's hard to make long-term investments. If you have a startup that promises you that they're going to provide you this great service now, and don't worry, in 3 years when we're well established and everybody uses us and you're locked in, we're not going to raise the prices, just trust us. You may not want to go with them because you don't trust them that in 3 years they're not going to raise the prices on you, and you shouldn't, right? So blockchain provides kind of an alternative that can mitigate those two economic problems. Okay? And to tell you maybe a description of how to think as an economist at the marketplace for that blockchain facilitates, let me do 2 steps. Okay? So first, users get the same kind of services, approximately. You can have an app on your phone, you can hold a balance, you can make transfers using this app. Okay? So for users, you get very similar functionality. But from the provider side, it's very different. You can think of Venmo as the bus company, while Bitcoin is Uber. So in Venmo, like there's dedicated servers that process all the transactions. In Bitcoin, anybody can be the server that processes the transactions and provide the infrastructure for the system. So in that sense, we sort of decentralized this into sort of a two-sided platform where anybody can be now a service provider. Anybody can provide the computing power to the network. But we go a step further than Uber now, because in Uber, there's still an entity that controls all the network, all this marketplace. And Uber can decide on changes in pricing, or what are the rules, or how to allocate drivers to riders. In Bitcoin, there's no company that owns the marketplace. In Bitcoin, the marketplace is determined by the protocol rules, and for the purposes of this talk, I'm going to think about this as fixed, as like we have the blockchain protocol that we have, whether it's Bitcoin or Ethereum or whichever protocol that you want. This is something that's fixed, and nobody has a power to change it. And this will entail a different market structure. So we're going to ask the standard economic questions about this two-sided market, about this marketplace. Under the firm, we know that the firm will get to set the rules, get to set prices, and will control the amount of infrastructure, how many servers it needs, according to whatever specification the firm needs. What will happen under Bitcoin? Under Bitcoin, we'll have a two-sided marketplace where we'll have service provided by the miners, and there's going to be something that determines their compensation and how much users will pay. So what we do in this paper is to just go through the Bitcoin protocol and say what will be the compensation to miners in the equilibrium that will result under the rules set by the Nakamoto blockchain protocol. What will be the level of infrastructure? And third, how much infrastructure will there be? And just to highlight like the results that I'm going to detail a bit more further in a few slides, the amount of infrastructure that will be deployed by Bitcoin, how much mining we'll have, will be determined by an entry and exit condition and the revenue, how much in total is paid to miners. And how much is paid to miners is going to be, of course, the block reward. And the other part that we're going to focus on is how much transaction fees users are going to pay, which is going to be something that's going to be modeled pretty well by congestion pricing. And as a result of those two things, the amount of infrastructure, the amount of mining in the Bitcoin network is going to vary over time and fluctuate, and basically nothing in the rules of the system makes sure that the amount of mining is appropriate or optimal in whatever consideration you have. So I'm going to try to highlight some good properties of this protocol, but also some things that may require more considerations, and we'll have some design suggestions towards the end. So I guess here there's no reason to talk about how Bitcoin works, but let me just glean a few properties that will be important for the economic structure of this two-sided market. So first, in Bitcoin, users choose whatever transaction fees they want to pay, and this is visible to the miner. On the miner side, the miner can decide which pending transactions to process. And overall, all the miners together try to generate blocks, and by a lot of trial, a lot of hashes that are roughly modeled as independent trials, altogether the arrival rate of new blocks is going to be 10 minutes on average, but the distribution is going to be a Poisson distribution, and there's going to be randomness between the inter-arrival of two blocks. Because of the difficulty adjustment, more infrastructure, more mining power does not result in more capacity on the network. So I'm going to talk about pre-SegWit Bitcoin, just to be concrete. And during this period, you could process 1 megabyte of transaction data per 10 minutes on average, regardless of how many miners you have. So more miners will maybe get you more security in some sense, but not more transaction processing capacity. And last, I'm going to assume free entry and exit. So this is a simplification that makes the modeling easier. Of course, this is a stylized assumption with caveats that if you want to ask me after, I'm happy to talk further about what happens when we consider ASICs or something more complicated. But I'm going to think of miners as just renting the equipment and entering and exit as they wish. Okay? Okay. So when I translate this to an economic model, I have the following model. So I'm going to count how many miners there are by computing units. And there may be some miners that are big and have a cost advantage. If somebody has a mining rig in Iceland, that's perfectly fine. All I need is that there's a lot of small miners that can potentially enter with some cost of mining. Think of this cost of mining as I'm renting a mining rig for 10 minutes. What's my cost if I want to rent a mining rig for 10 minutes on the open market? I'm going to call this CM. Okay? And I'm going to assume that for those guys, there's free entry and exit. They can start or stop at any time without paying anything. Okay? Altogether, the system adds new block to the blockchain at rate mu. Each block will process k transactions. I'm assuming for simplicity all transactions of the same size, and when I plug in a number, I'm going to use 2,000 for pre-SegWit numbers, roughly 2,000 transactions per block. And together those two numbers say that the system's capacity is k times mu. The system can process, on average, 2,000 transactions per 10 minutes. On the user side, I'm going to think that the users get some reward from using the system, which is this R. This may be high or low. You can think that some people will really want to use Bitcoin because they want to buy something on the darknet and they don't really have any alternative way of buying it. So the value of sending this transaction is really high. But some users want to just pay for coffee or furniture or something, and the value of using Bitcoin versus something else is low. So we're going to have heterogeneity in value of payments. A value of getting my payment processed. And there's going to be two costs associated with a payment. One is the C times W. W is going to be how long the transaction is delayed because of the spots on arrival, and sometimes there's going to be congestion on the network. Some transactions will have to wait. This wait entails the cost to users. Different users have a different kind of cost depending on whether I'm ordering something online or whether I'm sitting in the coffee shop and I have to sit there until my transactions gets processed. And last, the B is how much I pay in transaction fees, which is also going to be a cost for me. And whenever I write anything, unless I explicitly say so, it's all in US dollars equivalent, like my waiting cost, how much I'm willing to pay to get my transaction processed. That's going to be denominated in Bitcoin, but the valuation consideration should be relative to US dollars. How much transaction fees or how much my time is valued should be US dollars. Okay? And I'm going to assume that there's a heterogeneous willingness to pay. Some have high, some have low. And this is independent of the user's willingness to cost of waiting C. Okay? That just makes the models simple and nice. It's not supposed to be realistic. It's supposed to be a stylized example that shows a clean example of what's going on. And last, the transactions arrive at some Poisson rate lambda, which assumes to be below the capacity of the system. So I'm going to assume that the system has excess capacity. Because of the stochastic in the system, there may be periodic backlogs. So sometimes I'll send transactions, and at the point, maybe my transaction will still have to wait because the block took 15 minutes to arrive instead of 10, and by that time there was a buildup, and some transactions got delayed and not processed in the next block. But on average, the system has sufficient capacity to process everything. Okay. So before I analyze what will happen under Bitcoin, I'm going to give you some common economic benchmark, which was what will happen if I take the same users and let a firm serve them, like let Bank of America or PayPal serve those consumers. And it's a very common result in economics that the firm's optimal pricing will be socially inefficient. So the firm would like to price high enough to extract the willingness to pay of the high-value customers, and as a result, it would exclude the low willingness to pay customers. And that entails a deadweight loss. It means that some of the customers that the system could have processed and generate some value from were not processed because it couldn't price discriminate. If it were to process the low-value customer, it would have to charge the low price from everybody, and then those revenues will go down and profits will go down. So the firm, or a monopolist, or any firm that has pricing power often wants to raise the price over the socially efficient value, and that entails some inefficiency. And also, if the users are locked in and the willingness to pay goes up, the firm will raise its prices. Okay, so I have some loss under the firm, which means that Bitcoin is in business, right? Like there's something that Bitcoin can potentially improve on. So let me move and analyze what happens under the Bitcoin protocol, and hopefully we can get something that will help us with this deadweight loss. So I'm going to start by asking what the miners do. So in Bitcoin, there's going to be two sides, what the miners do, what the users do. I'm going to start with the miners, because what they do is actually pretty simple, and then that allows me to solve the other side easily. And a result is, under the conditions that I stated, that you have this free entry condition, miners have no pricing power. So miners cannot affect how much users will pay for their transactions, and are kind of acting like price takers. So this is probably not surprising if you think that all the miners are really small, because if I'm a small miner, I can't really do much. Right? The only thing I can say is I can threat users that if they post low transaction fees, I'm not going to process their transaction. But if I'm a small miner, I get selected very rarely, and even when I get selected, not processing somebody's transaction just delays it to the next block. So there's no reason why anybody will listen to anything that I say. But suppose I'm a relatively big miner. Suppose I'm 20% of the mining pool. And suppose now I say that every transaction that pays less than $10 in transaction fees is not going to get processed by me. So that means that I give up a bunch of transactions, I don't process them, but now users may want to increase the amount of money they pay on their transactions. Because if they paid below $10, they have 1 in 5 chances of getting delayed for the next block. Users who don't want to wait may want to increase the transaction fee to this $10. And this result says that the miner, the relatively big miner that can do this, will not want to do this. And the reason is the free entry. The free entry disciplines all those miners, because if the miner will do this, it will pay something in transactions that he doesn't process, and will gain something by increasing the transaction fees that users post. But the increase in transaction fees that users post and a bigger reward to all the miners will just induce more miners to enter. Because more miners enter, the profits from this will get dissipated to the other miners, and the big miners will just lose as a result. So this free entry condition creates very strong discipline on all miners. Even if they're big, this free entry condition means that all miners are price takers and cannot affect pricing. Okay? So what do miners do? All the miners just process the highest paying transactions until they reach the block capacity, or all of them if they can process everything. And that means that all miners, small or big, actually do exactly the same thing and get exactly the same share of revenue. So each processor that I have will get the same amount of revenue per unit time, regardless of whether I'm small or big. How much revenue per miner will I have? Well, the revenue comes from two things. One is the total transaction fees that user post. And the second is the number, like the amount of new coins that the system prints and gives the miners. So the revenue that they get from the transaction fees is going to be denominated in dollars. I'm going to think of the dollar equivalent of this and denote by rev. The second part is the coins. The coins are going to be denominated in the currency, in Bitcoin, and that will be subject to fluctuations in the exchange rate. Okay? So that's the only place where I have an exchange rate compensating the miners via this coin reward will mean that the compensation will fluctuate over time because of the exchange, and therefore both, I show later, hopefully I'll get to this, both as a result will be volatile and the number of miners will fluctuate. But whatever this number is, it's just shared equally per processor. And that just gives me that if the free entry holds, it must be that the marginal miners break even, and that gives me how much revenue, how the revenue in the system will give me the number of miners, the number of equivalent mining units that are deployed by the system. Okay, so what is this revenue number? For that, I need to go to the user side. This is the equation for the user. User wants to first decide whether he's in or out, whether I want to send my transaction or try to use another means of payment. If I send my transaction, I need to trade off how much I pay in transaction fees versus how much I bear delays. And we get that because miners all act in the same way and all process the top K transactions, the users actually don't care how many miners there are. Regardless of how many miners, they see it as a congestion queuing game where blocks arrive at rate K, at rate mu, and whenever a block arrives, the K highest paying transactions will get processed, or basically my transaction fees is paying for priority. If I pay more, I get more higher priority in transaction processing. And we can characterize this function, how much the delay, how does the delay look like, and we can solve for the equilibrium payment. How much should I pay depends on how everybody else pays. The equilibrium of this will give us the following properties. One is that if willingness to pay is high enough, if my value of sending the transaction is high enough, it doesn't matter. Okay? Once it reaches some threshold, I don't care what it is, and all the users participate. The users who are impatient will pay more, and not surprisingly, will get less delay. So the allocation of this delay is going to be conditionally efficient. And how much do you pay? Turns out that you pay exactly the externality that you impose on others. So when I post a high transaction fee, I get priority, I get to cut the line in front of others. What I pay is exactly how much delay I impose on them because I cut in front of them. So that means that what I pay has nothing to do with how much I'm willing to pay. So I may be willing to pay a lot of money for this transaction or a bit, it doesn't matter. I just need to pay how much I impose, how much delay I impose on others. But it will change with how much congestion there is. Because if there's no congestion and I cut in front of somebody else, I'm not going to impose a lot of delay on them. If there's a lot of congestion and I cut somebody in line, I may impose a lot on them. And that's exemplified by this graph, where the horizontal axis is how much congestion there is in the system. You can think of this as either the percent of the capacity of the system that is utilized on average, or another way to think about it is think of the period where a block in Bitcoin was 1 megabyte. What percent of this megabyte was used on average, like let's say throughout the day? So if this average is about 0.5, it's very unlikely that a block will ever get full. It sometimes happens, but it's very rare. And whenever it happens, it's like the next block will clear all the backlog. So whenever I cut in front of somebody in line, I usually don't impose much of a delay on them, and therefore nobody pays much. You see that the line is basically at 0. But when I approach 100% utilization, where blocks are almost always full, and I cut in front of somebody in line, and I create some congestion, then like it takes a lot of time until the backlogs will get resolved, and therefore I can potentially impose a lot of delay on somebody else by taking their place, the last spot in the block, and the payments explode. And you can see that there's sort of a sweet spot, about 85% congestion, where the system has excess capacity. The system has excess capacity, but because of the randomness, there's still going to be delays. So I have excess capacity, but some delays, so people will pay something to avoid those stochastic delays. So I told you this is kind of the theoretical motivation, and this is something that's actually common in a lot of stochastic systems. Let me just add on top of it the data. So now what I did is just add blue dots, where each one of those blue dots is 1 day in the Bitcoin blockchain during the period before SegWit. And we calculated the horizontal position of the dot is what percent of the 1 megabyte blocks were full during this day on average. So how much of the capacity of the blockchain was utilized a day. And the vertical axis is how much transaction fees per block were paid on average per block over the day. And you can see that roughly the features that I talk about the line actually appear in the data as well. So if we have a lot of congestion, the payments explode. If we don't have congestion, nobody pays. And there's some sweet spot of 85% where payments are actually positive and can fund the system. Okay, so I guess I should conclude in a couple of minutes, but let me just let me just talk about a couple of points of why this is good. So the system can raise revenue, but not excluding everybody. And everybody gets served. And the system can give positive net surplus to all users, which is something that the firm will never do. It's possible that we can raise prices and everybody will still be on. The firm would like to raise prices, but in Bitcoin, we have those mechanisms that prevent the miners from raising prices, which is a social good. And we have some fluctuations, though, because how much fees the system raises will vary because of the level of congestion. The congestion varies over time. The level of payment that the miners receive varies over time. And therefore, there's no reason to think that the amount of mining that's done on the Bitcoin blockchain is in any sense optimal. The amount of block reward is valued in an exchange rate that fluctuates over time. The amount of congestion-based pricing that we get fluctuates with the demand. It's not related in any way to whether you need this revenue or not. It may be that everybody is paying more for the blockchain where we say we're doing too much mining. So that's not efficient. And what we suggest and start thinking about is maybe we can get a steady stream of payments to the blockchain by just targeting congestion. Instead of having a difficulty adjustment that targets a block every 10 minutes, have a difficulty adjustment that targets 80% full blocks. Okay? And then you can target the congestion, you can get a steady revenue. There's a question of whether you want to control congestion by changing the block rate or the block size. And I guess I need to finish in a minute, so let me just give you this slide where if you increase the congestion, you'll increase both the revenue that you get as well as the delay cost imposed on users. If there's no congestion, then nobody pays anything and nobody waits. But as you try to get people to pay you, you need to inject some congestion, and that's costly because now you're going to make all those transactions wait, and that's a cost on all the users that use the system. So those lines in this curve use an analytical formulation to ask what kind of combinations of revenue and delay cost can you achieve for different block sizes. And what we show is if you want to raise even a little bit of revenue, you need to impose significant delay cost on the users. You can see that close to zero, this line is almost vertical. And the other thing that you can see is that lower block sizes will actually give you a better curve. So if I want to raise $2,000 per unit time, I can do this at a certain delay cost to the users under a block of size 20, but if the blocks were of size 200, I will need to impose more congestion on the users to raise the same amount of revenue. Okay, so let me conclude with that. So as an economist, looking at the blockchain and all the solutions, I think it's interesting because it gives us a new way to design markets, or markets for payment system. And I think of this as a new design for a marketplace which has committed rules and no owners. And fees are going to be determined in equilibrium, miners are going to be price takers, and the way that the rules in Bitcoin now generate revenue is through congestion pricing, which I think is an interesting pricing mechanism by itself. It's important that there's stochastics in the system. It's not perfect. It requires a lot of delay cost. It's inefficient raising low amounts of revenue, but I think it's a very interesting mechanism. And I only glanced on this, but we have some suggestion of how to modify the design to achieve more stable stream of revenue for the system, and smaller blocks generally seem to be better for the pricing, from a pricing perspective. So thank you very much.
Okay, thank you for a nice talk, for the courage coming here as an economist. We have time for a few questions, one or two. Any questions? Yeah.
In other markets, more mature markets, typically they handle these kind of tail events by buying and selling options. And wanted to get your opinion. It seems to me like in the future, miners ought to, if we can produce such a system, sell options on block space. So essentially, you can pay potentially in some sort of cryptographically verifiable way that the miners are reserving some sort of amount of space for you, and that might be a way that miners could raise additional revenue, and we could coordinate congestion a little bit better. If people are seeing that like all the optionality has been like sold on a block, that they ought to bid into that market, and I don't know, just wanted to know your thoughts on that.
So I'm not sure I understood your
I guess
question.
the quick version of it is, do you see a market around miners selling block space options as being able to coordinate some of these issues rather than tweaking the block size down?
So I'm happy to understand more, but like you need, whatever you do, there's going to be some payment from the users of the system to the service providers in the system. And you can structure it in options, you can structure it in many ways, but you have to have some rules in the system that will say how much money are we going to transfer from the users of the system to the infrastructure providers. And an option market may help regulate it in some way, but you need to also answer like just a fundamental question of like what's the basic payment stream.
So from an economic perspective, what's the benefit of a smaller block size? Like you said, design modifications?
So one of the, like I skipped this slide, sorry, but if you can think of this blockchain as maybe less efficient computational environment, because the decentralization is costly, we need to do all this mining. But on the other hand, we get a competitive landscape. We get a place where we don't have one company that can decide on pricing. We can get the system that operated by a lot of miners that are interchangeable. So you can think about this roughly as building 2 power plants in the city and letting them compete. It's costly to build 2 power plants, but it's costly to have 1 power plant that can change like the prices of electricity in the city. How much is each option costly? That depends on different kind of stuff. Same here in blockchain. You can think that if welfare loss from firms not serving or pricing too high and not serving low value customers, then it's going to be worth it to impose something like a blockchain here. Yeah.
Okay, let's thank the speaker again. Further questions offline. Happy to invite Stephanie Herder from Prison Group. She will be talking about governance, blockchain upgrade as a coordination game.
All right. Good afternoon, everybody. Thank you for coming to the economics session. My name is Stephanie Herder, and today I'm going to be talking about my paper, Blockchain Upgrade as a Coordination Game. So this is taking an economic lens to the eternal question of how to design blockchain governance. So this is a paper that's joint with Kathy Barrera. Kathy and I are both founding economists at Prism Group. So at Prism Group, we work with blockchain projects to help them with their economics and governance design. And so I have a PhD in economics from Harvard, where I was actually office mates with Jacob, who just spoke. So having spoken at a lot of blockchain conferences, I like to come in as a bit of an economics evangelist. So I want to talk a little bit about why economics, I think, is a really good complement to computer science when we're thinking about the design of blockchain platforms. So, at a fundamental level, computers are programmable, right? So if we think about when we're writing a program, we have to think about what are all the different conditions that can occur, what kinds of variation might come up that we need to take into account, but we know that the computer's going to do what we program it to do. On the other hand, people are not programmable, right? They have free will, and they make decisions based on what they perceive to be in their own self-interest. So, a miner is not just going to come and mine because we tell them to, right? It has to be in their own interest to contribute the resources, and the rewards have to, balance out any costs that they'd receive. However, blockchain platforms need users. They need people to contribute resources, and they need users. So the economic design of the platform needs to be such that the platform aligns the individual incentives with what the platform needs. And so we really think of these two disciplines as great complements, along with lots of other fields, legal, marketing, business strategy, lots of disciplines need to come together to help blockchain succeed, but we think these are two of the big ones. Now, and today I'm going to talk a little bit about an economic view of blockchain governance. So as many of you know, the design of decentralized governance has been a bit of a challenge for the industry. And I think that this is a place that economics as a field can help contribute. So economists have been studying collective decision-making for almost a century. So for those of you who follow the Nobel Prize in economics, Kenneth Arrow won in 1972 for his impossibility theorem, right? And this is based on work that he did in the 40s and 50s. And this has been extended to looking at political economy and all other organizations and different types of decision-making environments. So this is a place where there's potentially gains from applying economic thought. And what's really interesting about a blockchain environment, it's actually distinct from most settings in which governance or decision-making has been studied, is that we have the possibility of hard forks, right? So in most of the collective decision-making contexts that we are in a regular basis, whether it's government elections or organizations, secession is costly, right? So for example, I live in LA, and as many of you know, after the 2016 election, there was a lot of discussion that the 3 western states of the United States were going to secede and attach themselves to British Columbia. Lots of people said they were going to move. As far as I know, a lot of that didn't happen because secession is costly, right? So, but instead, in a blockchain environment, the question doesn't become, can I afford to leave? It's, can I get enough other people to go with me that my alternative setting is going to be an attractive one, in which to do business. And there are a lot of, hard fork evangelists in the blockchain community. This is one of my favorite diagrams. Forking is freedom. Forking is, and there's a lot of people who say that hard forks are always good. And so, when thinking about, this fundamental question of, do we want hard forks to happen? As an economist, it's always kind of weird to hear that something is always good or always bad, right? There are very few things that are always good or always bad. And if we look at the history of hard forks, and this is by no means comprehensive, right? This is sort of a partial list. We've got a couple of, just looking at Bitcoin forks, we have a couple of Bitcoin forks that have done relatively well. They've sustained themselves. Actually, since we wrote the paper 6 months ago, we've had one appear, that's Bitcoin SV, and Bitcoin Private, I believe, has met its demise. And on the other hand, you have, about a bazillion Bitcoin forks that have died. So it's not immediately obvious to me that we can say that all hard forks are good or all hard forks are bad. And so the questions we want to raise come from debates that we've seen, in the blockchain community. So the first one is, all right, how do we think about whether a fork is good for a community or not? Rather than just getting into an argument and, fighting to the death based on our ideologies, is there some way that we can bring sort of a rigorous framework to thinking about when hard forks are good and when hard forks are bad? And then the second question I want to raise is, how can governance procedures, and specifically voting procedures, impact when hard forks occur and when they don't? So one thing we hear a lot as the blockchain community explores governance is, if we could just find the right voting procedure to make decisions, this would cure us of bad forks, right? If we just found the right voting procedure, forks would go away. And so again, addressing this question rigorously and saying, like, let's take a couple of the voting procedures that we see being used all the time, and let's see to what extent they can actually coordinate us on good forks when we want them to and prevent bad forks from happening. And again, just to step back and talk about this in a little bit more of an economic framework, building on what I said before, that people make decisions that are generally in their own best interest, is that when we design governance, the governance procedures have to be what's called incentive compatible, right? So we want governance procedures that lead us to a good community outcome, but they need to be designed in such a way that it is in individuals' best interest to participate, and in some cases participate truthfully, right? So we always have to keep this in mind. And the other thing I want to spend just a couple minutes talking about before I dig into the math of the paper is this question of the role of economic design. So we talk to a lot of projects who say, they've developed their technology and they don't want to talk about the economic design because they think that it will impede the freedom of the users of their platform, right? That freedom is good, freedom is helpful, and if we impose economic institutions or constraints, this will lead to a lack of utility on behalf of the users. And ignoring economic design is a choice. You're just saying, I'm not going to deal with this. And so I want to spend a few minutes just illustrating one of many examples of how imposing economic institutions actually increases welfare for users, right? So it's not necessarily the case that by restricting freedom, you're actually going to result in worse outcomes. So I'd like to take a detour through the world of market design and tell you a little bit about the residency match. So this is actually work that is done by Professor Al Roth, who's 2 buildings down. How many of you have known someone who has been a medical doctor, a medical student, and has gone through the match? All right, so a lot of you are familiar with the match. So for those of you who aren't, if you're in the United States and you're a medical student, your first job after med school is what's called a residency. And you get your residency assignment through a centralized algorithm, right? So you apply and you go for interviews, and then all of the jobs and all of the applicants submit a rank order list, right? They say, here's my first choice, my second choice, my third choice. They run this big algorithm, and then you get a letter in the mail that says, congratulations, you're moving to, University of Hawaii or wherever you were planning to go. And so this system has been in place for over a century, and it's gone through phases of sort of success and failure. It sort of goes in and out. And so in the mid-90s, this match was having the problem that people were not using it. And the reason was actually that medical students were marrying each other, right? But they had to enter the match separately. So spouses would enter, and one would get assigned to California, and the other one would get assigned to Ohio, and they'd say, this is terrible. So they'd try to find jobs on their own. Right? And what's actually been documented in subsequent studies is this is bad for them. Right? The jobs that they were getting through the centralized mechanism were actually better for their careers than the ones they could find on their own. And so the organization that runs the match came to a couple of economists, including Professor Roth, in the mid-90s, and they said, no one's using our match. Can you please help us fix this? Right? And we want people to come and use the match and enter it, and then we want people to abide by their recommendations. Right? And so the team that was designing this took a fresh look at the algorithm that was being used to match doctors to jobs. And they formed a hypothesis, which was that marketplaces, they looked at many different marketplaces that were using these kinds of centralized algorithms, and they said, we have this hypothesis that marketplaces that are using algorithms that result in what are called stable matchings are going to be successful, and they're going to persist, and ones that don't are not. So there's a lot of observational data, you can see it in this table, that supported this. And the idea of stability is basically that you don't want an outcome where 2 people want to leave their match and run off with each other, right? As long as there's no sort of job and doctor pair who want to run off and not abide by the recommendation, the match is stable. And so through a combination of observational data and lab experiments, they hypothesized that implementing a stable mechanism would result in a marketplace that persisted. And so they tried this, and it worked. And this algorithm is now used in countless matching markets in multiple different kinds of disciplines. And so what I want you to take away from this is that this actually, imposing this kind of centralized design, actually improved the outcomes for everybody. right? The doctors got better jobs than they would have if they had to look on their own. The hospitals got better applicants. This was structure that helped people achieve more value. And so with that sort of economic lesson in mind, I want to talk a little bit about the problem of governance and governance design. And so the thing I'd like you to take from this is that designing governance and imposing institutions is not necessarily a bad thing, and in fact, it may be necessary for blockchain platforms to survive. So we're thinking about a world where we have a unit mass of blockchain users. So these are people in the community who are using a particular blockchain. And a debate comes up about a policy change. And you can think of this as like a change in the block size, right? And there's going to be the status quo, which is what's going now, and then there's the proposed upgrade. And so we're going to use this value function called Vij, which is the value to a user I, so that's just their index, of participating on a chain with policy J, along with a fraction of the community X. And the key thing here is that this system exhibits network effects. Right? I don't want to be on a blockchain by myself. I benefit from having people with me. So when I'm thinking about the value I get from a particular blockchain, there's a trade-off of how much do I like the policy and how many other people do I have with me. And there are going to be two types of users. So one type of user prefers the status quo, the other one prefers the upgrade, and the variable beta, which you will see later, is the fraction that prefer each. And so the first question I want to explore before we get into the governance design is, when are forks good for the community? So how do we think about when a fork is socially optimal in some definition? And we also want to think about when forks can be Nash equilibria, right? So as all right, there we go, thank you. I'm just going to keep going. So first, we want to understand, when do we see a hard fork as an equilibrium? So when do we have it that two chains are what we see as the equilibrium outcome of individuals making decisions? And then when is having two chains what we would call social welfare maximizing? And we're going to look at two different definitions of social welfare that come from an area that's called welfare economics. So one definition is called total surplus maximization. It's literally just what maximizes the total value in the community. And the other is called Pareto optimality, which just means that you can't make one group of people better without making another group worse, right? And so what we find, and again, this is a high-level diagram, and the way I want you to think about this is that this line is beta. So this is the fraction of the users who prefer the status quo, right? So if we're all the way over on this side, everybody prefers the upgrade. If we're over there, everybody prefers the status quo. And so what you see as very stylized results is that a hard fork, in some circumstances, can be total surplus maximizing. So this is sort of the gold standard of what we're looking for. But this doesn't always have to exist, right? And it is rare, in fact, that hard forks are total surplus maximizing. Secondly, we can have a set of outcomes where hard forks are not even a Nash equilibrium. So what happens here is that if you were to take the blockchain community and were to split it into two chains, they would actually just by themselves combine back together, right? And you see this when one of the two policies doesn't have enough support, right? So the 5 people who prefer one policy are on their own chain and they say this is terrible and then they go back. The third set, and I think this is really interesting, is that these are, a hard fork can be what's called Pareto optimal. So you can have a hard fork where, if you were to take the two chains and combine them back together, one of the two groups would be strictly worse off. And this always exists. So there's always a case that for a certain population, or a certain composition of the population, a hard fork can be Pareto optimal. So that's good to know, and that's the definition of optimality we're going to use going forward. And finally, we have this section, which is what one might call the Brexit section. So this is when a hard fork is a Nash equilibrium, but is not Pareto optimal. So the users of the community have ex post regret. Everybody wishes that this fork hadn't happened. But without some kind of collective action mechanism to sort of bring everybody back together again, people are stuck in this suboptimal outcome. And no one individually has the power to reconcile the two forks. And I just want to point out that, to us, one of the benefits of economic theory and economic modeling like this is that it helps with the clarity of, if you think about, is a fork always good? Is a fork always bad? Under what circumstances are hard forks beneficial for a community? This gives us a framework for thinking about that question, which is way better than just arguing, ad nauseum. And so with that in mind, we then look at the question of, suppose that we have a single blockchain and we're going to implement a voting procedure, right? And we're going to say we're going to have, this proposed upgrade, we're going to have people vote on it, and then we're going to see if people fork after they see what the outcome is. And the question here is, is there a type of voting mechanism that can prevent suboptimal forks from occurring? And so the two types of policies we're going to look at here, one of them is majority rule, which you're all familiar with. Whoever gets more votes wins. And the other one is called quadratic voting. So this is something that's gotten a lot of momentum. And basically, quadratic voting implements the policy that has the higher, results in the higher total surplus. So basically, if you have a very, very passionate minority, they'll never win in majority rule, but they could win under quadratic voting. And so what we find here is, this is one of those results that has like 18 parts of inequalities. So rather than walk you through that, I'll just tell you that this is a parameter space, and I'm going to walk you through the types of results. And as you move from left to right, the proposed policy change gets bigger, right? So if you're all the way to the left, it's a little policy change. If you're all the way to the right, it's a big one. And so what we find is the following. First, there are areas where voting is not going to impact, the type of voting procedure you choose is not going to impact whether forks exist. And this happens when the policy change is tiny and the policy change is huge, right? So if the policy change is tiny, the voting procedure that you pick can impact the policy that gets implemented, but nobody's going to care enough to leave, right? And then on the other hand, all the way to the other side, you have the area where hard forks are socially optimal, right? We want them to happen. These are the forks that are on net beneficial for the community. The type of voting procedure you're going to pick isn't going to impact anything. We want the community to split under these circumstances. In the middle is the interesting section, and this is the section where people have this ex post forking regret. This is the section where if a fork occurs, at least one of the two groups says, wait a minute, I don't like this, can we please reunite? And so if you use majority rule voting, you get these undesirable forks here. If you use quadratic voting, you get undesirable forks here. And so this is really the area where your choice of voting mechanism is actually going to impact when you're going to see undesirable hard forks occur. But just a couple of comments on this. First, there is, at least among these two voting procedures, neither of them is sort of the bad fork panacea, right? You're always going to be in some situations where you get a fork and you wish you didn't have one. The second piece is that, well, you might say, if you go back one, let me see if this works, you might just say, okay, well, why don't we just figure out what box we're in, and we'll design the voting system that way, right? The difference between these boxes are these very tiny population parameters. There's pretty much no way you would know in advance exactly where you were, right? So it's not like you can just go back and pre-design this. And so I think what this shows is that, the voting mechanism will impact the procedures the policies that get implemented, but they're not going to cure undesirable forking as we know it. And so, what do I hope that you take away from this? I think one big piece, just from stepping back from a different view, is that blockchain is really a new economic environment in many ways, right? And what we see now is a lot of the voting mechanisms I was talking about and the ones that we see in practice are taken from other settings. We say, well, this is working great over here, let's try it in blockchain. That's not always going to have the results we want because the economics of the setup are different. And so economic thinking is extremely valuable, but you also have to think about the fundamentals of the system. Another piece here is that for those of you who are thinking about how to design your blockchain governance, you need to think about more than voting. Right? So one thing you might think about is when does a policy get brought in for voting? How big does the change have to be? Right? Do we stick with really small and really big changes? Do we allow changes in the middle? How does that process work? You know, a final piece that I didn't get to talk about but is also important is communication, right? So for those of you who, again, keep following the sort of Brexit debacle, there's a lot of discussion about how the information that was presented by the Leave campaign may or may not have been misleading and then, you know, affected the outcomes of the votes. So there's a big piece of this is thinking about how do we disseminate information and make sure it's accurate so that people vote in the way that they want. And then finally, I'll just end with a warning that as we think about the design of mechanisms for governance, we should beware the theoretically perfect but the practically unimplementable mechanism. So there's a mechanism in economics called the Vickrey-Clark-Groves mechanism, which is perfect and is rarely, if ever, implementable, right? So we need not just mechanisms that do theoretically what we want, but also ones that we can actually use. And for those of you who might be interested in reading more about the type of work that the residency matches in, that Jacob was talking about in his talk, I recommend this book by Al Roth. Economic design is used everywhere now. There are lots of books about it. There's lots of interesting research. And, you know, you can highly recommend it. So, in conclusion, if you want to get in contact with me, this is my information. Prism Group will be doing several events at South by Southwest, so if any of you are there, I highly recommend, please come and see us. So I think that's it.
Thanks for a very interesting talk. Questions? Okay.
Very good presentation. So I have a question about, I don't know if you're familiar with the governance design for Polkadot. So basically they have a design where if there's a unanimity, like within the committee, like there's a very high probability of adoption of policy, but like as long as one person disagrees, the probability of adoption is like decreased by a lot. So to accommodate for the possibility. So the argument is that if everybody agrees, then it must be a software bug. Like it's something that people, like it's an unintended error, but as long as one person disagrees, likelihood it's software bug decreases by a lot. So what do you think that kind of design?
Right, so I won't comment too much without having their stuff in front of me, but it sounds like that one potential person has an awful lot of power. So there's definitely, it sounds like there's an opportunity to sway the results significantly.
Hey, thanks, great talk. I'm an economist too, political economist. In the end, you were saying that, yeah, it's a new economical environment, but so the question is, don't you think that the economics should change too? You know, that maybe there's opening a possibility that we can rethink what value is, what rational behavior is.
Well, unfortunately, we don't have an hour to answer that. I think it's a great point. I think that a good amount of the work that's been done on how individuals make decisions, and that includes both sort of standard theory and behavioral economics, will be very useful. And I think that there'll be a lot of ways, there'll be lessons on what not to do. But I do think that, you know, it will be interesting to see, for example, how behavior of actors changes in sort of a crypto setting compared to other ones.
Hi, thank you for the talk. It's good to hear from more economists. I'm curious if you have any thoughts on governance outside of a fork situation, again, more of a continuous, ongoing setting of a parameter, like say the block size or a savings rate or an interest rate, things like that.
I think that's a good question. I mean, just ex ante, that would be very tough to design because there's going to be sort of the nominal number and the practical implementation of it. So you probably want to think about things sort of more in buckets. But just in general, I think the takeaway from this is that, you know, whatever you implement is probably going to need to be pretty bespoke, right? There's probably not going to be a system out there that you can just copy and paste and do what you need.
I have one question. Did you look at the notion of correlated equilibrium, which is like a relaxation of Nash equilibria? And presumably it assumes like a founding team that designs, when you design the blockchain, you have the core client that you're designing, and then it serves like a public sort of beacon of coordinating party.
Yeah. No, I think that's a great point. Obviously, coordination mechanisms play a big role in a lot of communities, and you even see them forming in blockchains that don't have formal governance, whether it's through meetings in hotel rooms or eminent thinkers who we all know. So I think it's a really good point. We haven't formally looked at correlated equilibrium, but I think those types of mechanisms are really important to think about and include.
Okay, thanks a lot. Let's thank the speaker again.
All right. Thanks, everybody.
Happy to invite our last speaker, Jeremy Rubin. Jeremy, I don't have time to list all of his projects, things he co-founded, initiatives. So I will just say he's co-founder of MIT's DCI and a good friend. And he'll be speaking about Spork, which is soft forks in Bitcoin.
Oh, okay. Thanks. Oh, okay. Yeah, I want the presenter view. All right, thank you for the warm introduction. I have a secret to start. I'm not an economist, so you'll have to forgive me if I don't have any of your favorite notations for you today. I do have my own notations, so I'll be sharing this with you. I originally gave this talk, or the predecessor to this talk in Japan, so you may have noticed that my title is actually a haiku. So these are protocols that are used for changing Bitcoin network protocols. Unlike the previous talk, we're kind of considering a model where people do actually highly value staying together as a single chain. So we're just trying to coordinate the activation of a rule. If you've had a chance to visit an office in Silicon Valley, you might know that computer scientists really like food. And this is also kind of apparent in the terminology that computer scientists adopt. We have cookies, we have bytes, and we have famous problems that we model after eating dinner with our colleagues. The first problem in computer science, that is a dining problem, is the dining philosophers. And it's used to show how you can coordinate concurrency in programs. Later on, we also had the dining cryptographers, which are used to demonstrate the coordination of privacy among a party. Today, I'd like to share with you the dining Bitcoiners. And the dining Bitcoiners, well, this is used to show how we coordinate protocol changes. And for the dining Bitcoiners, they're all trying to have a picnic, and there are no forks on the table. And the question for them is how they coordinate what kind of utensil they should all use. So what is a fork? In the Linux world, or GitHub, we know that there's a fork, and this is kind of an easy thing. You run whatever you like. You don't need to get a central maintainer's approval for something to happen. But if you did want that central maintainer's approval for it to happen, in this case Linus Torvalds, it might be vitriolic. They might be really angry. They might say, no, get your crap code out of here. We only want high quality stuff that conforms to this standard that we expect. But if you decided, well, I just want to run this for myself, you can still do that. In cryptocurrency, it's a little bit different. We all have to run the same code. If we don't, we're going to break compatibility. And so we have to get our patches, to a certain extent, merged on master in order for it to work. And it becomes extra vitriolic because we're not just trying to convince one maintainer or our own little group, we're trying to convince everyone. And there really is nobody who has that key control who can just say, this is the change that's going to happen. There are two basic types of Bitcoin fork. There is a hard fork and a soft fork. And they exist on a spectrum, but these are two useful categories to think about. In a hard fork, it's a breaking change that requires the entire network to update immediately. So an example of this is if you have a hard-coded rule that says no block may be bigger than 1 megabyte, changing it to say the block size is now 2 megabytes requires everybody to change their software. On the other hand, a soft fork is backwards and forwards compatible change, and it's only kind of an additional rule on top of the existing rules. An example of this, if we have hard-coded 1 megabyte, we can soft fork down to half a megabyte. Everybody who accepts at least a 1 megabyte block will accept a half megabyte block as well. Each of these types of fork has a pro and a con. There are trade-offs. In a hard fork, it's actually possible to get better code quality. When you're changing everything, you can get rid of a lot of the bad practices that you had in the old code base. In a soft fork, you have to maintain compatibility, so you're stuck with whatever you had before. However, in a hard fork, you're suffering from centralized decision-making, and it's impossible to make everyone happy, and especially when there's more types of changes that can happen, you might spend lots and lots of time trying to figure out exactly how things should change. Some projects that go on a hard fork basis continually debate what exactly should happen. On the other hand, in a soft fork, you don't have this coordination issue. In fact, not everybody has to even be running the latest version, because you're compatible with the old one. But this does lead to some kind of weird considerations where perhaps a small majority, so like 51%, start enforcing a new rule that not everyone else is aware of, and we have some sort of closed source fork where now not everybody can get their transactions through, or they're more expensive. But because there's fewer types of change that are a restriction on the current rules, maybe there's less arguing about what exactly can be done. Other altcoins have solutions for how you coordinate these changes that are maybe worth mentioning. Tezos is built on the premise of making the entire protocol like a game of Nomic, where the rules themselves are amended in the protocol. And Stellar will prevent progress if you don't agree on what the new rule should be. And so any set that agrees, that has one of these blocking sets that agrees on what it should be, can prevent forward progress until this new change is adopted. But let's talk about Bitcoin soft forks and what they look like concretely. So in a typical Bitcoin soft fork for enabling a new feature, what you'll do is you'll take a no-op operation in the virtual machine or the script interpreter, and you will change it into something that verifies some property. So for example, you'll take some no-op operation, and you'll say you want it to check a SHA-3 hash. Right now there's no SHA-3 in Bitcoin. And what you'll do is you will check both of those arguments, that x is the preimage of the SHA-3 of x bytes pushed on the stack, but you won't remove anything. And so from an old client, it will have the exact same execution semantics. Those two elements will still remain on the stack, and so you might just choose to discard them afterwards. Except a transaction that doesn't include the correct preimage, maybe y instead of x, that will be invalid and not be able to be included once that fork has been adopted. Peter, who you heard from earlier, made a lot of this process a lot nicer with the way that he implemented SegWit, because you can just say that there's an entire new interpreter version, and all old nodes think any interpreter version they don't know about always yields true, always gives us a valid script, and when you upgrade the client, you add one that has a new rule. And so as a user, you really shouldn't use a script version that hasn't yet been defined, because it will always be true and you don't know what the semantics are yet. So that's a little bit on what these forks are actually doing, but how do they get made and proposed? Right now, there's two core mechanisms. One is called BIP8. This is kind of simple. Everyone agrees at some point in the future, based on height, let's say a year's worth of blocks from now, we'll activate a new rule. There's also BIP9, which is version bits. And in version bits, you have this state flow diagram where you first define a fork. Once it's kind of defined in the software that everyone's running, it becomes started at a certain time. And then you collect signals on each block to see whether or not there's enough support for the fork to activate. And you look for, under the standard version bits proposal, you look for 95% threshold of miners approving. And it's 95% threshold, but if you had a 51% attack at the same time, it would only be 51%, right? So it's 95% assuming there's no network attack. This didn't really work. So we use version bits reasonably well sometimes in the past, but when there's a controversial change like SegWit, people end up delaying this process for a really long time. Why is that? So there's this small misunderstanding in the notion of signaling versus voting. And that was kind of the key thing, I think, that delayed this process for SegWit's activation. So when you're using BIP9, you're supposed to signal for readiness. You're not voting to accept or reject a change. So once the soft fork is in the BIP9 process, Once it's there, developers have assumed it's going to activate. They've done so much work already. They've re-engineered the entire code base, and it's ready to go. It just needs to be ready for industry to adopt the practice, right? Everyone's assumed it's going to happen. But miners interpreted this a little bit differently. They thought that this is going to be a vote for or against the protocol at this stage. This is their time to interact with the protocol. They're really supposed to vote before it ever gets to this point. The engineering effort is simply not worth it, and the developer should invest their time otherwise. The notion of having signals be this sort of free-to-do thing is kind of penny-wise because there should be a cost, but it's pound-foolish because it ends up making this big engineering delay for getting everything activated. And so how might we fix this? Well, we could use something from game theory called honest signaling. So in BIP9, it doesn't cost miner anything to signal yes or no, or even to change their vote, but we can impose a cost so that we know the signals are true. Now, if we don't do this, what do we get? We get this game of chickens. And so what happens is there's a face-off between have the developers gotten enough support from the miners to activate, are the miners signaling, so on and so forth. And these timeout, and this process actually makes for delay, because you kind of push for another round. So because the remaining amount of time is known, if you remember that state diagram, there's a case where we reject the change and it doesn't ever end up activating. So behavior gets conditioned based on whether or not developers are panicked about this fork being adopted. And this creates a sense of urgency. Because as the timer runs short, there's urgency for those who want to modify it, who are making this trade-off on the change that they've pushed and that they really want to get, and another change a miner might request. So we can show this in kind of a normal Nash equilibrium game that the thing that should happen if there's some benefit of a change to a developer and there's some cost of that change to the miner, and they have some requests that they could also additionally make, that nothing ends up happening. And because this is a unique solution, even if you play this in an iterated game, still nothing should happen. So no change actually ends up getting adopted, which is a kind of nice result. It's not a perfect result, but at least shows us that something is kind of wrong with this mechanism. That leaves us with a question, like SegWit did activate, so what happened? The answer is we really don't know. So it activated, but there are like 30 different things happening when it activated, all these different agreements, all these different things. So for whatever happened, we got it, but we don't actually, can't retroactively point and be like, this is exactly what happened. In fact, in the code base, what people end up doing is when a soft fork activates via BIP9, eventually they get rid of the BIP9 checking and they turn it into a BIP8 fork. They go, yeah, let's just activate it at this fork because it doesn't matter. It did activate. But I think that we'd like to fix this problem, and we'd like to have a method for activating a fork where we can point to more rigorously and say, here are the economic conditions that led to this thing activating. Here's how people had their right to express their vote. Here's what it cost them to vote. And today I'm going to propose to you Spork, which is sort of probably a fork. This is a mechanism for making these forks a little bit more incentive compatible when people do decide to activate. It's actually really easy to understand what happens. Every time we mine a block, the hash of the block, that's the main proof of work, we just add an additional proof of work, which is with the name of the upgrade that we're trying to do at that time. And so this is a probabilistic block filter. So 1 out of every some amount of blocks will activate based on this filter that I've written there. And that is not really gameable because the original proof of work is inside of that hash. So if you wanted to just grind on that using your existing hardware, the best you can do is normal Bitcoin mining anyways. So that's maybe a little bit abstract. Let's walk through a concrete example of what I'm proposing the flow of making a change would look like under this new rule. So I'm going to introduce this new operation that we want to get, which is check block hash verify. So we want this new operation, maybe because it's going to give us replay protection. It's going to allow us to invalidate transactions if there's a fork or if there's a long reorg. We can say, yeah, don't reuse that transaction if something weird happens on the network. But this requires some complicated changes, so it's going to take a little bit of engineering effort to go through. Someone will go ahead and draft a BIP which says, okay, here are the semantics. We're going to take this NOP8 and we're going to turn it into this operation, check block at height verify. And we're going to set the expected activation of the rule to be 6 months. And what that looks like in our probabilistic block filter is that the hash of the block and the string concatenated to it, check block at height verify over 2 to the 256 minus 1 should be less than 6 months of blocks. Now it goes into a feedback loop. So what we should do is we've defined what we want this change to be, but now we should collect feedback from the community. Hey, what do you actually think of this? And what should happen, hopefully, is they would catch it there's a bug. They would say, well, actually, when you introduce this new feature, you introduce an unintended side effect of being able to parse the block header inside of a transaction. So let's do some new mechanism that accomplishes the same goal, but without this downside. And so the solution in this case, it doesn't really matter for this talk, but you would do a non-SHA-256 hash, and that would address this issue. Once it's gone through this feedback loop where people have raised all their possible concerns, then we put it into a reference implementation. And we'll implement it in, say, I think this version's passed, but version 0.18, and we'll do backports of this feature onto the last couple of versions. So if you're depending on specific behavior or APIs available in an older version, you don't lose that. You just enforce the new rule. Then here's what the rollout looks like. It starts at block 0, or with some offset, and we expect it to take 6 months to activate. After a few blocks, how much time do we expect it to be? Still 6 months. At a certain point, it actually does activate, and that's where I've drawn the dashed pink lines. Those are blocks that activate the new rule. But at any time before that, we still expected it to take 6 months for it to activate. So let's do some basic analysis on this, and we'll do a little bit more of a rigorous analysis later. By the time an upgrade is on Spork, so it's in the software, we've kind of reached this rough consensus. We have an idea of if there's support or if there's strong opposition for this thing. Every miner actually has the ability in this process to vote against the fork. And they can do this by refusing to build on blocks that activate the fork. And that should be like 1 out of every T based on 6 months. So 1 out of 6 months blocks will activate it. A miner can just say, I'm not going to mine on that, and that's their vote. However, this voting can be costly because it might require orphaning their own blocks. A miner's own blocks, 1 out of T of them are going to activate the rule, and if they really don't want to activate it, they need to throw away their own block. This isn't a permanent problem. You might be thinking, but what about all these lost blocks? Isn't this bad for the network? Bitcoin has difficulty adjustment, so eventually, if we're abandon a fork for a very long time, it's just going to manifest as a change in difficulty. And I would guess with a parameter like 6 months, it's going to be well within the variance of hash rate anyways. Every miner has a large incentive to want to activate the fork. When they mine that block, if they don't want it, they're throwing away an entire block reward. They've spent a lot of money on the hardware, on the electricity, on the data center cooling costs, et cetera, to get that block, and they have to throw it away. So they really don't want to do it unless it actually means something. There's no influence for influence's sake. The probabilistic filter is an independent trial process, so it's time invariant. The expected activation is constant. So for all time, we expect it to be in 6 months. Now, we actually do get kind of a conditional information outside of this where if we expect it to be 6 months and it's taken like 100 years, we're probably pretty sure people are just politically opposed to it. But we let this emerge naturally. We don't force it to happen via a direct vote. And that what this means is that making someone wait doesn't gain a miner any influence. So a miner doesn't say, I'm more influential, look at this block I threw out, because it doesn't give them the ability to vote for that in the future. So let's do a little bit more concrete numerical analysis of what exactly this means. So before and after the fork, we're going to say that a miner has some probability of mining a block. And what this recognizes is that a miner is probably opposed to a fork because it decreases their probability of mining a block. So at each step, a miner starts in the start node, and with some probability, they get 1 reward, and then they repeat the process. And we discount their next round with some discounting factor. Discounting has some support in the economic literature as a reasonable model, especially exponential discounting like this. There are other models that you could plug in. Again, I'm not an economist, so I'm just using this as a model. If you want to model it using different things, be my guest. Under this, it's a simple geometric sum. So we see that after the fork, in the transient case, we are expected to be earning R times P active over 1 minus delta. And before the fork, we're going to earn R times P inactive over 1 minus delta. What is this discounting rate? Where does it come from? Well, maybe increased competition. We expect in the future there's going to be more miners trying to mine. We might think that our hardware might break. It might get too hot and burn out. Any secret advantage we have that's better than someone else might get well known across the market. Maybe we have a patented advantage, and now, 15 years later, everybody has the same patented advantage. Or maybe we think that we have to convert into dollars, and we have some uncertainty of where the price might be in the future, and so we need to insulate against that, and so we discount our future profits compared to our current ones. A simple model to do this would be to look at the actual observed hash rate on the network and look at its growth over time. And if you do this, what you'll see is that it reasonably goes 2x every year. So it does grow currently exponentially. And based on that, we can compute what a per block discounting rate should be, which is this very big probability or discount. We don't discount that much for every step in our model. Within reasonable bounds, if we were to 4x per year, you can see what that value is below, or if we were to only 1.5x per year, you can see the other value. If you have a decrease in hash rate, this model doesn't work as well, but I think it still does hold that you would expect more of your future profits if you think the hash rate is going down. What are P active and P inactive? Well, P inactive, so this is before the fork happens, should be less than half. If it's more than half, then it's not going to get the rough consensus when we're talking about it with the community, because most miners aren't going to want to get this. So we could estimate it by just saying as a straw poll in your Coinbase transaction, write a message if you're kind of okay with this fork, and leave it out if you're not. And we can take 1 minus the percentage of blocks that are signaling with yeah, we kind of like this thing, as our raw percentage that are opposed. P active should be less than, there's a typo there, but should be less than P inactive. We should be expected to lose something if we're actually opposed. If we were getting more, that wouldn't necessarily make sense, but maybe there are circumstances where that could happen. And this represents the probability of mining, but it can also represent some other factors relating to just the core profitability. Now let's look at a miner who has basically a decrease in their probability of mining. What types of strategy they might have. We're going to discuss 2 strategies. One we're going to call the bad strategy, and one the good strategy. The bad strategy is one that's maybe socially undesirable, and the good strategy is one that I'm saying is socially desirable. But that may be my own labels and not how the miners feel about it. The bad strategy, what I end up doing is I start at the start node, and with some probability I mine a block. And if I mine a block, and it doesn't activate the rule, I collect a block reward. If it does activate the rule, I throw away a block reward, so I actually lose 1 revenue. And then I start the process again. Now, there's also a chance, 1 minus P inactive, that the other miners mine a block. And so in that case, I don't get anything because someone else mined, but there's some probability, 1 over T, that they activate the fork. And then there's some probability, 1 minus 1 over T, that there is no fork, in which case I restart again from the beginning. But if it does activate, then we go into the world where the fork rule is applied, and now I get this transient state profit with P active. So one of the important assumptions here that I'm making in this model is that when it does activate, because we said P inactive is less than 0.5, you're not going to try and reorg that block. You don't have enough hash rate to do a sustained fight against it, so once it activates, it's going to activate. So we can analyze this state machine, and we can figure out what the expected value is from starting to traverse this graph. And it ends up being a little bit more complicated, but the same type of analysis as the earlier transient state. And we get some expression. It doesn't really matter exactly what it is, but it's an expression. We can do the same for the good strategy. And in the good strategy, what we do is when we get that block that activates, we're calling this good because we just go, okay, oh well, I had my run in the sun, and I'm going to activate this because everybody else kind of wants this. So here we go. And I agree to lose my higher P inactive rate. And we can analyze this all the same and get another expression. And so now we are able to ask kind of a core question, which is when is the expected value of the good strategy greater than or equal to the expected value of the bad strategy? And what this will tell us is that the miner starting this game, which again is an independent trial process, so it verifies for all time, that they would prefer to just activate the rule if it happens rather than to kind of go against the grain and orphan their own block, which might be a bad outcome for them. We wouldn't want to set things up so that the miner has to make that hard decision. We want to set it up so that the miner is okay with activating the rule, even at a decreased hash rate. So we can graph this. We can actually graph this inequality by saying good minus bad and seeing what that is. And so you can see that you actually get some kind of interesting results. So what I'm showing you is I am showing you on the x-axis the p inactive, and on the y-axis the p active over x. So I'm just showing you kind of that expresses something that is a percentage of what the p inactive is. And what you see is that there's kind of a wall. These parameters, this is for a 1-year expected activation and a discounting rate of 40% per year. So what you say is in 1 year, my hash rate is only going to be worth 40% of what it is today. You can then derive a, per the, delta, you can derive the per block discount from that. And what this shows you is, in these circumstances, something under 10% of the hash rate can be opposed to a fork. That doesn't sound too good, so let's look at a different parameter. What if discounting is 80%? So this means that we expect our hash rate to only decrease in value by 20% per year. This is kind of surprising. What you see here is this is all red. This means in this regime, everybody is willing to adopt the new rule right away as soon as it activates. Nobody's throwing away their old block. It's a little bit counterintuitive. I had to look at these charts multiple times to make sure I understood what was going on. What this is suggesting is that because of the decay, miners who have a lesser decline in their future profits are more willing to accept a change, even though it hurts them more in the future, right? They have this longer time period where their hash rate is active at a lower rate, but because they end up valuing the things as they do, and you can look at these equations and kind of convince yourself of how it works more concretely, it ends up working out. So let's look at a couple other examples, and then we'll talk about how you can apply this result. So if you put it at 6 months, and you say that they're discounting to 20% in a year, you get kind of an even picture. You get, under 20% of the miners should be opposed, and then you'll get everyone activating faithfully. If you change that discounting rate, so if you increase it from 0.2 to 0.4, then again you see kind of a similar result where now everyone's activating. And I had to pick these numbers because I wanted to show you the transition. The transitions happen at different discounting rates. So how can we use this practically? Well, recall we said that this is actually a measurable discounting rate that we can kind of assume as a variable, and we can look at what happens under this exact discounting rate. So here with 12 months and discounting equals 1/2 per year, we see that actually there's a pretty good regime of activating. If under 30% of miners are opposed, then they actually will be happy with just activating the rule and not choosing to orphan their own block. And there are a lot of other models which suggest that Bitcoin is kind of unstable if we have more than 30% of miners thinking about one thing anyway. So with labels, you can also see there's something interesting going on in the far left of this graph, which is that there's an indifference region. So that white region, that's where miners don't really care. They don't care for either the good or the bad strategy, and so I'd like to think in the goodness of their heart they'll do the good strategy, but maybe not. So let's say that we wanted to improve this, and we wanted to say, let's get it even better. Just increasing the time, that actually makes things worse. The way that miners discount things, if we increase the time, and you can think through, it took me like an hour to kind of get the intuition of this, but as you increase the time, miners' time preference changes, and then they'll become more opposed to the change. And so there's a lot of room to fail the fork because a lot of miners are going to be orphaning their own blocks, extending it, and we've decreased the overall fitness of this fork. On the other hand, if we decrease it from a year to 6 months, we've increased the space of where miners are happy, and now for all values, it's profitable for miners compared to the bad strategy to do the good strategy. So when do we use this? Have I proven that this is ready to go? I don't think so. I've given some concrete evidence which shows that this actually does let us think about the variables at stake for a miner and how we might model it and how we might change the activation timelines for a protocol change, how sometimes making the timelines longer messes with miners' discounting rates, and that we might counterintuitively not want to give miners sufficient time. We might want to put a little bit of time pressure, but allow them to organically vote on it indefinitely, because that makes it more compatible for them to activate it if they don't mind either way. There are also extensions that are worth exploring that make it maybe easier to apply in practice, and I've only modeled this theoretical version, but in practice, you might want to have a couple of these things. I can just explain really quickly with the time remaining. So one thing you might want to do is you might want to say that the rollout of this thing can't happen before a certain height. In my model, it's completely independent. It just happens whenever the probabilistic filter is matched, but that's a little bit unreasonable because people do need some amount of time to activate. So you might say, like, the probabilistic filter starts a month from now, and everyone upgrades and is ready and they have it, but you don't want it to necessarily start as soon as the binary is released. You might also want to put in an n-block phase delay, which might say, after this block activates the thing with the probabilistic filter, wait n blocks before the thing actually happens. This is for like an exchange customer where the independent trial that activates it happens in the middle of the night in their time zone, and they've got to wake up all their engineers to go be ready to make sure the migration happens correctly. You don't really want that, so you might want to say, let's have it be 1 week so that there's a little bit of time for everyone to just be ready and flip any manual flags they have to flip. You might also want to do an n-block pass enable. So you might want to say, after n blocks pass the threshold, then enable the feature. This is a little bit like a firing squad arrangement where no individual block is really culpable for the activation of this. It's just a number of blocks that end up activating it. And so the first couple miners to participate in this don't necessarily have as large an incentive to orphan their own block. And this reduces variance and gives us more warning without having to encode any concrete timeline. You also might want to have an early adopter rule. This is a little bit interesting to model. If the activating block itself is not compatible with the new rule, invalidate the block reward of that block. And what this would do is this would incentivize everyone to have compatibility earlier, because you might end up mining an invalid block if you are generally planning to go ahead with it. So the soft fork rule could take place even before, take place and be enforced by most miners even before this fork is completely activated. Lastly, you could do an orphan-proof activation where just the existence of some block that activated this at some point would be sufficient for you to make your own block one of the ones that activates. So if someone did have enough hash power to temporarily turn on to reorg out that block that activated from someone else, you could then use this mechanism to just reference it, and I would leave discussion of that to our session chair because he knows all about referencing ancestor blocks that get orphaned. Lastly, in a rich tradition of mentioning other events that are happening at events that are currently happening, this conference was announced at the last Scaling Bitcoin, and now I'm announcing the next Scaling Bitcoin, which will be in Tel Aviv, September 11th and 12th. So I hope you all can join us there. We're also going to be having Bitcoin Edge, which is going to be a fantastic event if you want to get more in the weeds on how to actually build and engineer in the space. Thank you very much.
Thanks a lot for a very interesting analysis. Unfortunately, we'll take questions offline.
Sure.
Due to we ran out of time. Thanks a lot for the speakers, and see you tomorrow morning.